happy that everybody is here. We were hoping to be meeting in person at the McKimmon Center this year, however, Delta. Hopefully we'll see everybody in person next year. First, to start off, we're going to get an introduction by our new facility director, Nina Balke. Nina is the new director of the Analytical Instrumentation Facility. She started as the director on October 1st. She is also a newly appointed associate professor in the Material Science and Engineering Department here at North Carolina State University. Before she came to us, she was working at Oak Ridge National Laboratory at a government-funded user facility. So she has plenty of experience with user facilities, which is what we are. She is an expert in atomic force microscopy, and her research focuses primarily on ferroelectric and energy storage materials. And with that, I'm going to turn it over to Nina.
Thank you so much, Chuck. I want to welcome everyone to the CSS in 2021, which is, as you can see, virtually. It would have been great to have an in-person event, but perhaps we are more lucky next year. First of all, I want to thank the organizing committee, which you see listed here on the first slide. They put a lot of work together. They put a lot of hard work into put this program together. So if you run into them virtually, extend a thank you to them. Second, I want to thank the sponsors for this event, which did not allow us only to put together the program, but also allowed us to give out a few prizes. We have multiple awards for presentation and posters for students or a best overall. So stay tuned for those. I want to highlight two specific ones. That is the AIF Best Paper Awards, where we actually looked at all the papers utilizing the AIF in the last year. And there we're giving out 2 awards to impactful or transformative papers written by a student or postdoc. And then for everyone, I want to highlight the CSS raffle. If you fill out the online survey, we will have 2 random drawings. If you submit the survey before the award ceremony, which is tomorrow at 2:30. So fill out the survey and come to the awards ceremony. Okay, that brings me to myself in my new role. So as you have heard from Chuck, I'm the new AIF director. I started October 1st. And I'm taking over from Dr. Jacob Jones, which has made the AIF into the world-class facility you see today. For people who don't know what the AIF is, it's NC State's largest shared research facility, and it's housed within the College of Engineering. The mission of AIF is to enable and lead state-of-the-art research through acquisition, development, maintenance, training, and access to major analytical materials and biological characterization instrumentation. A big part of AIF's mission is realized through building of the next generation of research infrastructure. And recently, the AIF focused on biological and soft matter research, as well as advanced tomography techniques, which can be applied to a variety of materials. Another part of AIF's mission is education and outreach. So here we are performing workshops, short courses, and open houses. We offer tours to visitors, industry researchers, and classrooms. And based on all the restrictions we had with COVID, the AIF created quite some online content, as you can see, for example, in the AIF YouTube channel, which I encourage everyone to check out. There you can see a lot of information about the techniques we have at AIF and get them explained. That brings me to the small overview where I want to give you a little bit of an insight of what toolboxes we have at the AIF as a characterization facility. We have a microscopy toolbox. Here I want to highlight our 5 existing SEMs. We have FIBs and we have TEMs. We have a suite of diffraction techniques, surface analysis, including XPS and TOF-SIMS. And I want to specifically highlight our capabilities to do sample prep for cryo-bio-EM. I want to highlight this because we're building up a very comprehensive suite of techniques, and together with our other characterization techniques, such as the bio-TEM, we will be the go-to center for cryo-bio-EM needs in the Southeast. So that's a very exciting development. Here I want to just give you a really broad spectrum of examples of different materials and techniques performed at the AIF. You see this CT scan of a beetle, which gives you these really nice 3D renderings of your sample. You see here an SEM image of a butterfly scale. You see highlighted the milling capabilities a FIB provides on smallest length scales. You see chemical information on the atomic scale, here shown for an STM measurement on a superalloy, and here an example for chemical mapping of a coated nylon fiber with the tough SIMS. And here in the middle, you see a barium titanate thin film. And here EBSD shows us which grains have which orientation. So this is just a really broad cross-section of capabilities and applications we have at the AIF. So since I only have a few minutes, I hope I could help you get to know the AIF a little bit more. And I hope you will enjoy the conference and generate lots of good ideas for research projects where you could come to the AIF and utilize our equipment. I want to thank everyone and welcome again. And I hope I meet some of you in person in the future. And with that, I want to open up the conference. Thank you.
All righty. So the way that we're doing things today is all of our invited talks, except for the very first one, are live. The first one is from Jess Jur, and it's on textiles characterization. And unfortunately, Jess could not be with us today. So his presentation is pre-recorded, and there won't be an opportunity to ask questions. After that, the student presentations and vendor presentations are all pre-recorded. So we'll watch those. And then in theory, the students will be here and we'll be able to take questions. So let's go ahead and start Jess's talk.
Good morning, everyone. Welcome to today's presentation on textile electronics design strategies. My name is Dr. Jesse Jur. I'm a professor in the Department of Textile Engineering, Chemistry, and Science here at the Wilson College of Textiles at NC State University. I'm also currently on sabbatical as the Director of Ecosystem Technology at a defense manufacturing institute called the Advanced Functional Fabrics of America, or AFOA, which is based out of Cambridge, Massachusetts. I wanted to provide, I apologize for not being able to be present today for the presentation or live, but I wanted to give everyone an opportunity to connect in with me through LinkedIn or send me an email if you have any questions. So, first of all, I always like to start off the talk with what exactly is a textile, especially if I'm speaking to a diverse audience like I am today. So a textile is a periodic structure that comprises of fibers that are spun into yarns, and then those get put into textile structures. And there's a number of different textile structures that you can make. This is an example of a knit structure, but you can also make woven structures or non-woven structures, which are very random in their orientation, in the fiber orientation. What's really cool about textiles is the fact that if I change the fiber, if I change the yarn, or if I change the openness of this structure, I can alter the breathability, the moisture control, the strength of these materials. And this is what's used within smart textiles. And this is really the foundation of it. And this is a great example of the product on the right. Is a Nike garment that has 12 different panels. All of these panels are actually sewn together. So where you see seams, these are all actually hand sewn together. But all of these structures are highly complex, and this actually creates and is optimized to improve to maximize the performance of the body that's underneath that garment. Now, when we talk about e-textiles, we think about system design. And of course, when we think about we have this textile world, we have this electronic world, we want to make sure that we can marry these two industries up together to make sure that the electronics are not necessarily influencing the design, influencing the properties that we want out of the textile, as well as and vice versa. And in fact, there's a lot of opportunities in which we can design the textile to make the electronics to work better. And that's actually one of the strategies and motivations of my research group. But these e-textile systems, which are also smart textiles, so these would be more of an active as opposed to passive technologies. These are complex systems, and there's power that can be harvested, there's sensing that's integrated onto it, and you want to be able to link all these things across the body and put these devices at the locations on the body where they work best. And then of course you have to be able to move data out to a cloud or to an aggregator that will end up then be collected and provide value to the consumer. So in the early years, this is a work out of Georgia Tech. This is actually one of the first e-textile fabricated products. It actually created a very interesting bus system that allowed for sensors to be placed at different locations and track out where what's happening at these different locations with the different sensors. This was obviously a very cumbersome and I would say pretty kludgy example of wearable electronics, especially integrated textiles, but it was actually a really great demonstration of what was possible. Today, what we're seeing, you have companies like Athos or Ralph Lauren who make a lot of or who make integrated textile electronics into garments for things like EMG sensing or biometric sensing through like heart rate or respiratory rate. And of course, these garments are much more commercially look more commercial and actually can be purchased commercially. In the future, where we're heading is there's a lot of different types of sensors around, and the opportunities to place these sensors within a single platform or multiple sensors within a platform are opening up. And this is where e-textiles definitely comes into play. There's also this whole world of sensory feedback as well, where you can have either light feedback or haptics or vibration motors. You can have electrical stimulation or even heating and cooling applied to the body through these same garments. So when it comes down to it, we want to actually be able to integrate these electronics on textiles or even within textiles in some cases. Conventional uses have always historically been to applying these materials through things like electromagnetic shielding or even clean room apparels, as I'm sure most of you all have been in if you've been in the nanofabrication facility here at NC State. But what is really exciting are some of these fundamental components or the ability to apply these fundamental components in textile electronics and smart clothing for things like biopotential sensing, energy devices, printing multi-layered structures for transistors and displays. And this can either be at the fiber level or at the fabric level, but still retain a lot of the textile structures that we want. So there's a number of different e-textile processing strategies, all the way going from the original polymer, where you can use organic materials, organic electronic materials, all the way out to the garment apparel, where you can actually apply on things like embroidered type of structures. So at the polymer to yarn stage, so polymer fiber into yarn stage, there's this whole industry of conductive fibers where you can have metal fibers or you can spin organic conductive fibers. And then you can also apply different types of coatings directly onto the fabrics. And so this would be, so you can either do this through batch processing, through dip coating or electroless plating. And then finally, if you want to be able to pattern this onto fabric panels that have already been cut, then you can do this through screen printing. You can use direct write or direct ink write technologies, as well as inkjet. And so this, of course, another way to get to patterning through the conductive yarns is through the use of embroidery. So there's a lot of different ways in which you can create these conductive structures on textiles. My research group primarily focuses on the printing processes. So whether it be screen printing or inkjet printing, and we're going to focus today a lot on the screen printing processes that we use. And so we actually started the screen printing work probably back around like 2015 or so. And the idea was that we took inspiration from the common logos that you have on garments, such as this one here that's an Under Armour logo. And these are actually stamped on or heat pressed onto a garment at the end of the process, or after the shirt's already made. So it's a nice kind of a retrofit application onto a garment. So we started to study a lot of these different types of designs of how you can apply screen printable conductive inks that you would get from places like Creative Materials or DuPont, up with TPU encapsulation that you would get, or thermoplastic polyurethane encapsulations that you put on either side of this, and you can heat laminate that directly onto textile, just similar to how we do this logo. And so this is and we can also incorporate and pick and place devices within this. And this actually got us pretty far. So we made a lot of great progress on this in terms of incorporating these devices, looking at the structural integrity of these materials. And but now we actually have to get this into a garment and try to actually start to figure out how we could end up using it, which we'll go into in a few minutes. We also are able to make biopotential sensors. So these are devices that when in combination and you have a nice analog front end that measures the Eindhoven triangle on your device. So this is a 3 electrode structure. You can measure things like your electrocardiogram. And we worked really hard on trying to develop this process in order to make it durable across accelerated wash cycles that are commonly needed if you place any devices onto a textile. And we were able to have show 25 wash cycles with this. We actually got up to about 100 wash cycles. Eventually, we were able to show a number of abrasion cycles, as well as good impedance and air permeability through these materials. We're also able to do other types of devices, such as antenna work or antennas, or basically these patch antennas. These are actually this is a dual port full duplex based antenna. We're able to apply in different materials like a barium titanate structure or barium titanate particles that go and infuse into the textile, still have really good flexibility, and then we screen print our electrodes on top of this. And these are some of the results that we can kind of get from this. So this is a very versatile process in order to make a lot of different types of e-textile designs. But what we really want to do is we really want to see how these things work on humans. And that's the whole goal. We want to try to collect data, and we want to try to see how the design of the textile and the electronic really kind of function together. So this is going to be the remainder of the talk, is focused on this. And so one of the things that we really wanted to do through the Assist Center here at NC State, which is an engineering research center funded by the National Science Foundation, was look at the development of how could you record biometrics from the upper arm. And so this is this story that I'm going to be sharing for about the next 8 minutes, is really kind of going through that process of how we came across this, as well as how we're using now modeling work in order to improve some of these architectures. So the first thing that we wanted to do is we wanted to determine electrode positions. So determine out so we basically mapped with commonly used 3M electrodes, red dot electrodes. And we looked at combinations of these to determine what was the best placement from a signal to noise, or from a R to S peak ratio within our electrocardiogram. So this is from the QRS complex. And we're able to identify not only the best location from the aspect of high quality signal, but also from the design for, let's say you don't have to rub the electrodes up against your arm, because that will end up reducing or that will end up increasing the number of different artifacts that you actually collect from this data. We also started to embark on trying to model some of an arm sleeve, because pressure is actually a large factor, or contact pressure is a large factor in reducing the contact resistance between the electrodes and the arm. So the contact pressure we were able to model using a hoop stress model, in which we're able to take a number of different sleeve diameters and analyze what the contact pressure is, and then we're actually able to go and model this fairly well. And so we can actually now go and say, like at the top of the arm or at the bottom of the arm, based on where we want to apply the electrodes. This is the diameter of the arm sleeve that we would want in order to obtain a certain amount of pressure. And the amount of pressure that is usually around 800 pascals to around 1500 pascals is the right range. If you're lower than that, you have too much contact resistance. If you're too high, you're actually restricting blood flow. So there is an optimum range that we want to observe. We can also start to correlate some of the dry electrodes to some of this pressure model. So this is the same dry electrodes that I showed earlier. We placed these onto the garments. We chose a number of different sleeve diameters in order to understand what that right range is for our electrodes in order to get a good signal to noise ratio. And this is actually a signal to noise ratio times 10 over here on the y-axis. We can also then apply, or we can look at this over multiple days period of applying this onto a human and look at some of the noise artifacts using fast Fourier transform methods to identify exactly what the origin of some of these artifacts might be. We can then use this in terms of a system design in order to take not only the raw data, but then we can actually go and filter and smooth these out. And then the power of somebody in the assist center is we can actually go look at designing new analog front ends, a new SoC, or pairing these up with really low power semiconductor on chip or microcontroller units. And we can maximize the total power of this whole system so that we can maximize the total battery lifetime of the devices that we're applying on. And eventually, hopefully, as we've demonstrated also in the Assist Center, apply energy harvesting to make these devices work full. So this is kind of a key result. It's just a few pieces of data, but it's very insightful at the same time. And we're going to be coming back to this. So this is our full sleeve design over here on the right. And basically taking out these measurements, we can start to apply these onto a number of different people. We can observe if the signal to noise ratio is too loose or if it's too tight. We have different effects, and we also have different observations of different types of motion artifacts that, and also a feeling of being uncomfortable, especially if it's too tight. So we use this methodology to do human variance studies using the standard sleeve measurement process. So then this is all based on not only the gender, but also on the arm size. We can define this range of pressure for improving the sizing of how we manufacture or make these arm sleeves. And then we can also then explore some of the motion artifacts at different pressure ranges. So these are the different studies that we have going on. So this is a great example of two subjects that we studied. So this has same basic armband construction, two different subjects that have two different sizes of an arm. Subject one, you can see here has the red is the arm sleeve, and then we also have a benchmark wet electrode device that we're applying on here as well. And then subject two, you can see that we have a significant decrease in the signal to noise ratio. And this was due to the tightness of this fit. So if you can actually go and look at this from subject two to subject one, we can actually start to identify some of the causes for why we would have a low signal to noise ratio. Now, this is all great and good, but I mean, and this is really sort of a highly iterative process on how we go through about this design. What we'd really like to be able to do is apply on new techniques that are evolving within the textile space in terms of structural modeling of garments. And this is an example of a program called CLO 3D, which is based out of South Korea, which allows for a virtual fashion studio to occur. So using very basic properties of the textile, such as this bending or stiffness, as well as the drape of a material and the density of the material, we can actually start to apply these structures onto humans and understand the stress strain properties, not only internal into the textile itself, but then also the amount of compression that this material has up against the garment, especially during and on these avatars as they move. It's super, super cool. So, so as just an example, we can take very basic, like an Under Armour garment. This is a sleeveless Under Armour, really tight fitting garment that has a number of different types of textiles involved in it that are used for for different types of breathability. They have different types of seams integrated into this, and we can put all of this into this model, and we can start to think, and we can start to see how these materials or these structures actually act. So ideally, if you do product design within the textile industry, you can actually go and take these, you can do these stress maps. You can take different panels, put different materials into a panel and see how this influences the design. So we wanted to actually take the same strategy with our textiles and see how this works. So this is the sinusoid interconnect that we started out with. So we can actually start to figure out how we can actually model these. And you can actually, it's really cool. In some instances, you can actually go and like take this little hand, you can kind of come up and pick it up, and you can see how the strain properties interact around those devices. We can then integrate these onto different types of avatars. So this is it's a smaller arm up to a larger arm. Using the same materials, we can actually look at strain mappings of our structure, and then we can note where our electrodes are optimally located based on the electrical signal. We can go in and start to look and see what the compression is up against the body at those particular areas. And so this is a kind of a good example of two different arm sleeves, and looking at the locations as well as the amount of pressure that's applied. So the strain and stress applied at those particular locations where we have those electrodes. From this, we can actually go and model our results, and we can actually see that it actually makes sense. Subject 1 has a much higher stress profile, and leading to or compressive stress, leading to higher signal to noise ratios. Whereas at the lower stress values for subject 2 leads to lower signal to noise ratios. And so now we have strategies in which we can use modeling from a textile design perspective to improve our overall system designs. And so with that, I'd like to say thank you. Please, again, reach out to me if you have any questions. I'd be happy to answer any questions anyone would have. Just send me an email, and I'd be happy to talk to you. All right, thank you so much. Have a great day.
Are you ready for vacuum? Here at UC Components, we've been pioneering fasteners for vacuum applications since 1974. Like a lot of great businesses, we got our start in an ordinary garage in Union City, California. Since then, UC Components has grown into a world leader of fasteners and O-rings for extreme environments. Today, our modern 16,000 square foot manufacturing facility in Morgan Hill supplies OEMs, government labs, universities, and other facilities around the world. As the vacuum industry grew, we've grown with it and expanded into a broad spectrum of applications, from semiconductor manufacturing to oil and gas to solar energy and beyond. Our precision components were first used in space exploration and the defense industries. Large and small companies alike now rely on UC Components to meet the extraordinary requirements of today's and tomorrow's vacuum equipment. At the core of UC Components products is the vented screw. Our vented screws provide complete evacuation of trapped volumes of air during pump down and eliminate virtual leaks, speeding vacuum chamber pump down time. All our vented screws are available in inch and metric sizes. We offer numerous vacuum-stable plating and coating solutions, including WS2 and MOS2 coatings, gold, silver, nickel-plated, and more. Our range of fasteners also includes vented and non-vented washers and nuts to offer a complete solution. We don't just stop with vented screws. You'll also find O-rings made from top-quality fluoroelastomer materials in a size to fit your needs. If you need another material like Buna, silicone, or a specific chemistry, just ask. All O-rings are ready to use in most HV and UHV applications. Our extended cleaning and vacuum bakeout process ensures that any water trapped in the O-ring polymer is removed to reduce outgassing under vacuum. You can trust that your O-rings are clean and dry right out of the package. UC Components isn't your everyday supplier of fasteners. Can't find just the right fastener? We offer complete prototyping services for items such as vented and non-vented dowel pins, captivated fasteners, cut down, turn down, and fasteners to print. We also assist our customers with a variety of special services that include custom bagging, custom hardware kits, parts recycling, wire hole drilling, and custom cleaning. UC Components also offers a range of coating and plating services designed to prevent galling and/or improve the corrosion resistance of the treated component. All our coatings and platings are vacuum compatible, depending on your specific process chemistry. Our component finishing processes include precision cleaning, silver plating, gold plating, nickel plating, MOS2 coating, WS2 coating, and electropolishing. New and non-standard finishes include colsterizing, high chromate silver plating, nickel Teflon coating, locking patch application, and more. All our components go through our certified ISO Class 5 cleanroom precision cleaning, vacuum baking, and packaging processes prior to shipment. Every product we make is a ReadyVac product, which means ready for vacuum. ReadyVac components are cleaned and packaged in our certified ISO Class 5 cleanroom environment. You'll never waste time with ReadyVac fasteners and seals. They're ready to install the moment you open the package. We may be located on the cutting edge of California's Silicon Valley, but our family-owned business never forgot its roots in vacuum or its dedication to customer service. Today, we serve the semiconductor, energy, R&D, aerospace, optics, and vacuum processing industries, to name a few. Whether you choose a standard fastener or work with our team to design a custom screw, you can count on UC Components, fasteners, and O-rings to hold fast in the most extreme vacuum environments. Call us at 408-782-1929. You'll always get a knowledgeable person to answer your questions. Or visit us on the web at www.uccomponents.com.
Well, I'm certainly ready for some vacuum. That said, I don't think my mother's ever been very impressed with the vacuuming that I do at work. We're going to change up the agenda just a little bit. Next, we're going to have Younghwan Lee, Domain Textures in Ferroelectric HFO 0.5 Zirconium 0502, which I think he calls SZO or HZO.
Hello, my name is Younghan Lee. Today I'm going to talk about the interface engineering of ferroelectric hafnium zirconia metal ferroelectric metal capacitors. As the Internet of Things and information industry are growing day by day, the global electricity demand is increasing exponentially. As a consequence, the data centers are chewing up vast amounts of energy, and many researchers are trying to make more efficient memories. There are numerous future memories that have been proposed so far, but ferroelectric memories gained significant interest these days. Here, the diagram shows that more than 40% of the talk that had been presented in the meeting of VLSI 2021 is related to the ferroelectric. Now, based on the different structures or the design of the circuits, you can make various types of ferroelectric memories, ranging from ferroelectric random access memories, ferroelectric field effect transistors, ferroelectric tunneling junction, and etc. Now, recently, among many other ferroelectric materials, hafnia-based ferroelectric memories attracted many interest due to its excellent scalability and energy efficiency, and its fast read and write speed, and so on. So ferroelectric hafnia might be the game changer to solve the global electricity demand one day. What is the ferroelectricity, by the way? Ferroelectricity is defined as the reversibility in a polar crystal of the direction of the electric dipole by means of an applied electric field. And then it can be easily verified by a simple experiment called the polarization versus electric field measurement, or PE measurement. As you can see from this schematic here, the polarization of the ferroelectric capacitor follows non-linearly with respect to the applied field. And the polarization can be remnant even if you remove the external field, and the polarization can also be oriented differently if you apply the negative field. Now, this process is referred as a switching process, And it can be considered as a read and write process in terms of a computer engineering perspective. And this is the basic concept to design the ferroelectric-based memories. Ferroelectric hafnia is an orthorhombic phase where the spontaneous polarization lies in the z-axis or the 001 direction. And although, the ferroelectric hafnia seems to be very promising, but there are some technical challenges left for the practical applications that includes the grain size control, the homogeneity in the grain orientation, and the phase distribution or the phase composition, domain wall dynamics, interface quality, and so on. But for today's talk, I would like to highlight the importance of the grain orientation, or in other words, the crystallographic textures, or a preferred orientation of ferroelectric hafnia. First, let's take a look how I made the samples here. I personally had a belief that if we were able to make the bottom substrate with a different orientation, and if we deposit hafnia on top of them, the orientation of hafnia could be easily controlled. So here we chose the titanium nitride as the bottom substrate, and we were able to control the orientation of bottom titanium nitride based on different processing conditions. The XRD pattern shown on the left is measured at a Bragg-Ventano geometry. So it demonstrates that the 001 and 111 texture, the titanium nitride, can be easily achieved from our group. And then now on top of these two different preferred orientation here, and then the hafnia zirconia could be directly deposited on top of these two different preferred oriented titanium nitride. The deposition method we used is a snap deposition, which is developed by our group. And you can find more detailed information in the paper that was published in this Applied Physics letter this year. And for today's talk, I will call this hafnia zirconia deposited on 001 nitride as 001 HCO, and then hafnia zirconia deposited on 111 nitride as 111 HCO. Okay, and then after we made the samples and we wanted to verify the preferred orientation of hafnia zirconia. And how do we do it? And I used the 2D XRD measurement to characterize the different orientation of hafnia zirconia. And then the schematic of goniometer geometry is shown on the left. And let me briefly recap a simple XRD principle to better understand how the 2D XRD works. Now, first, let's take a look at the Bragg's law here. As we all might be familiar with, when the incidence beam, which is an X-ray beam, comes into the lattice plane, and then when I interact with the lattice planes, diffraction occurs. And the scattering vector always bisects this incidence beam and the diffracted beam here. And then this scattering vector is always perpendicular to the lattice planes here. Now, if we look at the reference XRD patterns of the polar orthorhombic phase of hafnia, we see that the 111 reflection peak appears at the 2 theta of 30 degrees. So what this implies is that if we want to measure the 111 planes that are aligned parallel to the surface, now we need to set the X-ray source angle and then detector angle to be the same. I mean, like 15 and 30 degrees. So if you look at the goniometer geometry, we see that the X-ray source angle is set as 15, and then the area detector angle is set as 30 degrees. And now the diffraction is now recorded on the area detector here, and it's typically shown as a diffraction rings. And then the diffraction, the azimuth angle on this detector is defined as a gamma. And then let's say, this position is typically defined as a gamma equals 90 degrees. And then the orthorhombic 111 planes that are aligned only parallel to the surface can be measured at the position of gamma equals 90 degrees. And then if we trace the peak intensity across this azimuth angle, we can identify the degree of a texture of a corresponding plane. In this case, it's a 111 plane. Simplistically speaking, if we see a strong intensity at the center of detector, And then if the intensity drops significantly across this azimuth angle, this means that the sample has a 111 preferred orientation. Or if the intensity doesn't change a lot, this means that the sample has a random orientation. Now, this is the real 2D XRD image of 111 HCO. And these are some of the reflection peaks of our interest. And then if we integrate all these intensities with respect to gamma, we could achieve a figure like this. Again, if we slice, if we take the azimuth section angle of 90 degree, we see that the orthorhombic 111 peak appears to be the maximum at the center, and then it decreases sharply if you if you deviate from the gamma equals 90 degree. Again, this implies that the 111 HCO shows a strong 111 preferred orientation, or in other words, 111 planes are now oriented parallel to the surface in this sample. Now, on the other hand, this is another 2D XRD image of 001 HCO. And again, this is some of the reflection peaks of our interest. And then, you can also slice the gamma equals 90 degree. And unlike this 111 HCO, we don't see that much change in this orthorhombic 111 peaks here. But instead, what we see is there's a notable change in this orthorhombic 002 reflection peaks. So for this 001 HCO samples, so we believe that maybe the 001 HCO shows a 001 type preferred orientation. In other words, some of the 001 planes are oriented parallel to the surface. So what is the consequence of having two different preferred orientation then? So we measured the polarization versus electric field of 001 and 111 HCO. And then the first thing that we observe is that the 111 HCO exhibited a larger coercive field than the 001 HCO. This means that the 111 HCO is difficult to switch, which means that it requires a higher field to switch the polarization. And then we also measure the permittivity of the 001 and 111 HCO samples. And then the first thing that we observe is that the permittivity value actually falls into the range of the ferroelectric hafnia that is reported in the other literatures. So it means that we have made a good orthorhombic phase of the hafnia. And then we noticed that the permittivity at the zero electric field is higher for the 001 HCO. And then the tunability, which is simply the change of permittivity, is also higher in 001 HCO. This means that the domainal motion is faster in 001 HCO. And we also noticed that the coercive field, which is defined as the maximum permittivity, the coercive field where it shows the maximum permittivity is higher in 111 HCO. Again, it means that the 111 HCO is difficult to switch. To summarize, we have successfully made the 111 and 001 textured hafnia zirconia, and then we were also able to measure some of the electrical properties of these samples. And then it appears that 111 HCO is harder or difficult to switch than the 001 HCO. And then it shows and then it is worth to discuss why the 111 HCO is difficult to switch. And you can see that the 111 plane is actually about like 55 degrees tilted away from the 001 planes. And then this, if you imagine, if we have a domains, the schematic of the domains that are aligned in this way, you can see that the red arrows indicates the polarization axis of the domains. And then now the electric field is being applied normal to the surface. And then due to the angular relationship, the 111 textured hafnia zirconia, the polarization axis will be located somewhere around here. And then the field that is being applied to this polarization axis should always be the field times cosine 55 degree, which is always lower than the electric field that you're applying. And maybe this is the reason why we think the switching behavior in 111 HCO is harder than the 001 HCO. Whew, okay, so but last but not least, I would like to thank to my sponsor, the CDP, which is the Center for Dielectrics and Piezoelectrics, and the Analytical Instrumentation Facility and the Nano Fabrication Facility in the NC State. And I can't emphasize enough to appreciate many help from my great colleagues in my group. With that, I would like to end my talk. Whew, okay, thank you.
Okay, so if anybody has any questions for Young-Hwan, you can feel free to stick them into the chat. I have a quick question. In fact, I should have mentioned that ahead of time. My bad. So Young-Hwan, do you think it's possible to make 100 or 010 HZO? Because I can imagine, a situation where you have a 3D architecture, and if you only get switching in one direction, having a field in one direction, switch it one way, and a field in another direction, switch a different part of a device. So do you think it's possible to grow it in different directions like that?
You mean like, different switching? Like
No, is it possible to grow the HZO so that it has different grain orientations other than 100 or 111?
It could be, yeah. But due to the substrate that we choose was only like 111 and 001. So I think I think we only got the chance to see 111 and 001 type preferred orientation for the Hafnia zirconia.
Yeah, but if you had some 100 titania, you think the Hafnia would grow on it?
Yeah, because a lot of time, like this type of things are called as like texture inheritance or the like seed layer effect, so a lot of time those preferred orientation can be followed by the preferred orientation of the bottom substrate. So I think, it's possible, that you can also control the preferred orientation of Hafnia zirconia in a different direction, depending on different bottom substrate, I think.
So is this reasonable to scale up? I mean, how much extra effort is there involved with adding the extra processing step of putting the titania down before you grow the Hafnia on top of it? I mean, is that an arduous step that's going to add a lot of extra cost?
I don't think so. It's actually quite easy, I think, because one of the beauty of the deposition method that I developed here was called SNAP deposition. It's an acronym for the sequential no atmospheric processing. But just simply saying, it means that you just deposit all the sequential layers in an ALD chamber without exposing to the ambient atmosphere, without breaking the vacuum. So one of the beauties is that we have made a very clean interface of each layers. And yeah, but a lot of time, when people want to make different layers, they have to move around to a different deposition chamber, and that kind of always makes an impurity. And there was, but I think, in our case, I don't think we have to worry too much about those problems. And then all I need is just changing the recipe inside the ALD chamber, ALD reactor. So it was kind of easy to follow, I think.
All right, great. Does anybody else have any questions? I haven't seen any pop up in chat. Chris has got a question.
Young-Hwan, excellent talk, by the way.
Thank you.
I remember from looking at these samples, they have the columnar style grains from the texturing. Have you guys looked at the texture size, the crystallite size? Do you have any control over that via annealing, or how does the texture size or grain size or whatever we want to call it, how does that influence the polarization and some of the other metrics?
Okay, so I'm thinking that you're referring to the grain size.
Yes, sorry.
No, yeah, I'm okay. I think the grain size is typically like it falls into the range of like 10 to 30 nanometers. I think it ranges from the sample area to the areas, but I think it's typically under like 30 nanometer at best, in my understanding.
Do you have any control over those grain sizes to make them smaller or bigger, besides annealing?
I haven't thought about that actually,
Okay.
But it may be very interesting, research. I think, I think it's hard, but maybe it's worth trying.
You've done a lot of good work, so maybe graduate and then worry about it. So thanks, Young-Hwan. I appreciate it.
Thank you.
Well, that brings up a follow-up question on my part. How much do you expect smaller or bigger grains would be better for device performance? I'm thinking ideally you probably want a single crystal.
Yeah, exactly. Yes. Yeah, but if you want to, in particularly for the device performance aspect or the perspective, I think you may want to get single domains or single grains, because it's always good for the reliability. But it's hard to avoid, to get those polycrystalline in this ALD materials. So, but I mean, it doesn't matter, which grain size that you have, but the more important thing is that how homogeneous distribution of grain size is more important, I think. It's no matter like it's 10 nanometer or 30 nanometer, but if it's still, shows that like 10 nanometer for overall surface area, then I think it's more better in terms of a device performance, I think.
All right, great. Well, let's give Young Hwan a big virtual hand.
Thank you.
Our next talk is going to be Yao Li, who is going to talk on pedal-shaped dislocation loop cluster structures. And Yao is from the University of Tennessee.
Hello, everyone. My name is Yao Li. I'm a PhD student from the University of Tennessee in Knoxville. Today, my topic is the pedal-shaped dislocation loop clusters in BCC ion chrome alloys. This project involves researchers from Oak Ridge National Lab and the University of Tennessee in Knoxville. Fusion energy is good. It's a promising source of limited lathe, carbon-free clean power, but its structural materials would suffer high-level damage. Due to their excellent properties, vertical martensitic steels are a strong candidate for the structural material of fusion wedges. Although they have numerous favorable properties, FM steel still face challenges such as irradiation-induced hardening, embrittlement, and precipitation. Dislocation loop induced by irradiation are a significant contributor to irradiation hardening. This project focuses on 100 and 101 loop formation in ion chrome alloys, and we would like to know how chromium concentration those rates affect loop formation. I'm gonna share 4 samples at 450 degrees C at two dose levels. The right image show an overlap of shrimp prediction and TM image of one of our samples. As you can see, the damage profile predicted by shrimp matched the TM image in a decent way. The method we use here to identify dislocation loop is called classical G-B analysis method. In BCC ion system, there are 7 different types of dislocation loops. We applied 5 different G's to reveal their type. The method V stands for visible condition in this table, and I stand for invisible condition. For each single type, it has its own unique visibility criteria code as shown here. So by this table, we can fully distinguish them from each other. In the left image, you can show three groups of features. The first one is pedal-shaped clusters here. The second one is long big lines pointing to 11 direction. The third one is lines pointing to 2 o'clock direction. This image was taken along all one zone axis. Here, we only observed 2 sets of defects. Long lines pointing to 2 o'clock direction and pedal-shaped clusters. Actually, what happened here is we took sample from this direction to this direction. All those big lines pointing to 11 o'clock direction actually show their final details in the image here, like this one and this one. Essentially, all those features over here are pedal-shaped clusters. By G-B analysis, we observed that actually these pedal-shaped clusters are dislocation loops. Here are example. This feature was visible in these 2 images, but invisible in these images. By this, we fully identify by the GWN to fully identify all the dislocation, all one dislocation loop clusters. Interestingly, in 5-chron sample, we only observed the petal-shaped loop clusters. In 3-chron and 8-chron, we also saw some small features. So the formation of petal-shaped loop cluster didn't depend on chromium concentration. However, chromium concentration did have impact on the small features. By GW analysis, we know these features in 3-chron and 8-chron chromiums were also loops. In 3-chron samples, these small features actually in a very wide size distribution. In 8-chron samples, these tiny features in a narrow size distribution. It is easier to see their dislocation loop in 3-chron samples because they are quite large. But in 8-chron samples, we only observed in bright field or black spots. By weak beam dark field image, we image some of them as ring shape. This is a strong evidence to support the argument that they are dislocation loops. At higher dose, at 3.5 dPa, we see these long big lines, but we didn't see a petal shape cluster in the matrix. So in lower dose, we see petals. At higher dose, we didn't. Instead, we see the loop matrix. What happened here? So the petal shaped loop cluster must decompose at some damage level. By searching the entire sample, in this sample, we actually observed some petal-shaped cluster in the decomposition process. Here I show 2 examples. Actually, the decomposition process started from the center instead of other positions. Also, we have performed the EDEX on all those samples really at 450 degrees C, having the petal-shaped clusters. The radiation induces chromium segregation occurred on all the petal-shaped clusters. Conclusion. Petal-shaped features were observable in all iron chromium alloys at 450 degrees C. A classical GW analysis method, petal-shaped clusters were identified as loop clusters, and they were all one type. Chromium segregation had effect on loop formation, but barely had effect on petal-shaped clusters. Petal-shaped clusters started to decompose at around 0.8 dPa, and the decomposition started from the center. Chromium segregation observed. I would like to thank to the Office of Fusion Energy, U.S. Department of Energy. Without their sponsorship, this project isn't possible. Also, I would like to thank the analytical instrument facility at North Carolina State University. Due to their careful maintenance, we can get this good image by the state-of-art TM instrument.
Well, thank you, Yao. I have a quick question. We will open up the floor for questions, but I want to just confirm something. It sounded to me like the linear structures that you observed, if you rotated the sample, those linear structures were clusters of these dislocation loops that you were looking. So you look at it like this and it looks like a linear structure, and you look at it like this and it looks like the dislocation loops. Is that correct?
Yes. So
okay, great.
All those things are actually dislocation loop. So if you see the black lines there, the actual edge-on view
of the petal-shaped clusters.
Yeah, petal-shaped edge-on view. And if I tilt the sample, and actually it's close to the plan view. So it's like you can imagine it's like a card.
Yeah. Oh yeah.
Yeah.
No, I totally understand. That's one of the things I preach a lot when I teach people about scanning electron microscopy. And I'm sure Chris talks about this a lot when he teaches people TEM, is if you look at it from the wrong angle, you're going to delude yourself, and you have to look at things from more than one direction to get real ideas of what you're doing.
Yes.
So is it possible to mitigate the formation of that sort of radiation-induced damage?
Yes. So that's the one major goal of our community. So there is one way. So if you introduce some precipitates, which we treat as a recycling center of the displaced item by irradiation event. But the goal of this project is to under the fundamental aspect of the irradiation phenomenon. So we just reduce all those extra parameters that we can understand how the dislocation formed in the irradiation process.
So I've got multiple questions, and I'm only going to ask another one.
Sure.
Well, I mean, I think about materials a lot. So the chrome concentrations seem to affect the size of the loops. Does that mean that higher chrome concentrations are going to end up with better material after irradiation? Because I mean, that's really the goal, is to have if you're building a reactor, the structural performance of the reactor material before you irradiate it doesn't seem to me as important as it is after it's been irradiated by a few million, or a few billions of neutrons smacking into the material is going to cause some problems. So do you think that the higher chrome concentration will make for better materials after irradiation?
No, the reason is if we increase the chrome concentration, like about 12%, after irradiation, you will have alpha prime precipitates, which is chromium enriched precipitates. Once you change the composition of your material, your mechanical property will also change, right? So that means only by increasing the chromium concentration, it's not a good way to do to enhance the safety mechanism in nuclear reactor.
Well, that's sort of what I suspected, but I wasn't sure 100%. So does anybody else have any questions for Yao? Chris?
Yeah, excellent talk. It's some really beautiful data you took. I was happy to see it. So I had a question, and this is probably not necessarily apropos, but those petal-shaped clusters, that's really fascinating. I haven't really ever seen anything like that. For the lower displacement per atom damages, where you really have these kind of flowers, have you looked at the mechanical properties to see how those connected dislocation loops are affecting the mechanical properties, or is that beyond the scope of your research right now?
That's beyond my scope of research.
Okay. I would be curious to see what the mechanical properties are with those interconnected dislocation networks.
One of my group members, one of my group members actually worked on a similar sample.
Okay.
And what he observed, like this degrades the mechanical property of our sample.
Interesting. Okay. A similar question, and probably again outside the scope, but if you annealed those samples, do you think those dislocation loops would start to decompose as well into kind of more conventional dislocation structures?
Yes, actually, this structure has been observed by several scientists in decades. The famous scientists from Japan, I think they are the first batch of scientists observed that one. They also do the annealing stuff on this paddle shape. What is observed that once you annealing sample, the paddle shape got shrink. And the shrinkage actually occurred on their neck. So the first step, you have an entire petal here, and then after maybe like 1 minute or 2 minutes, you have a ring of your dislocation loop as a peripheral region, and then you have a bigger one as a very center. Then with the time going on, all this dislocation loop disappears.
Interesting. Cool. Well, thank you. Yeah, that's all the questions I have. Again, really, really excellent talk.
Thank you.
All right, let's give Yao another big virtual hand. Next, we're going to have a vendor presentation by Protochips.
There are many steps in the day-to-day operation of your TEM, and so many of these involve adjustments and settings that can bring your work to an abrupt halt due to unintended instabilities they induce. Then you're just forced to wait until the system recovers enough for you to proceed with your work. There are many causes for these instabilities: inserting a new sample holder into the column, selecting different modes or conditions, even just minor adjustments to your sample's position. And these wait times haven't traditionally been viewed as a problem since they're unavoidable, and therefore they have been considered just a necessary part of the operation of this complex scientific instrument. Before high magnification is possible after sample insertion, the holder needs time to equilibrate with the column, and full stability won't typically be reached for hours, sometimes overnight. Coarse and fine stage movements typically performed through an experiment to optimize imaging tend to cause some amount of backlash or hysteresis that results in you sitting and waiting for things to settle before you can move forward with the experiment. And switching between TEM and STEM imaging modes, as well as the use of different accelerating voltages, can add powerful information that may be vital to your experiment. However, these decisions can come at the expense of the loss of a significant amount of time while you wait for the microscope to return to stability. The accumulation of wasted time from these various delays stacks up quickly. But what if you could eliminate these delays and recover all this lost time instantly at the press of a button? Well, we're here to tell you today that this is now possible. The new Protochips Axon system connects your TEM's optical column, imaging detectors, and any sample holders, allowing them to work in perfect synchronization so you can command instantaneous stability of your system at all times. Now, this will allow you to eliminate all the wasted time spent during drift settling and recovery, greatly increasing the productivity and throughput of your microscope. Now, a statement this bold typically feels too good to be true, but for once, this is exactly what it claims to be: a revolutionary inflection point in the operation of your transmission electron microscope. Suddenly, sample insertion can now instantly be followed by direct access to your TEM's ultimate imaging performance. There's no waiting. Moving the position of your sample in any axis is no longer followed by any residual drift. The sample stays as stable as if you'd never moved it in the first place. And switching between detector modes or accelerating voltages to better attack an application with the full arsenal of your system is now possible without that soul-searching decision of whether or not you can afford the wait times from the resultant instability. Even the use of dynamic heating, cooling, and other in situ holder systems is no longer impacted by instability. There simply is no longer any instability. So, now that we've shown you your future, we'll ask the question again. What are you waiting for? Minutes wasted lead to hours, hours to days. And how much time would you reclaim for your lab if you had Axon? Now's the time to find out.
Our next talk is going to be from Milad Shamsi, and his talk is on ultrasoft and stretchable thermoplastic elastomer gel nonwovens.
Hello, everyone. Thanks for watching my presentation. My name is Milad Shamsi. I'm a fourth-year PhD student at Department of Chemical and Biomolecular Engineering in NC State. I work under Dr. Dickey, Dr. Purdami, and Dr. Spontag. And as you can read, my project is about making ultrasoft and stretchable thermoplastic elastomer gel fibers or nonwovens. Our overarching objective is to modify the morphologies and properties of thermoplastic elastomer gel fibers through the strategic use of physical additives. By doing that, these materials can be stretched up to 20 to 100%, and we predict these materials can be used in different applications like stretchable electronics or smart filters. The main problem with these materials is such nonwovens or fabrics are their surface tack is very high, and that makes processing of these materials a little difficult, and we're working to solve this problem as well. To make thermoplastic elastomer gel fibers or nonwovens, we use a triblock copolymer named polystyrene ethylene butylene or SCBS. Depending on polystyrene fraction and molecular weight, these block copolymer can microphase to different morphologies from spherical to cylindrical or lamellary or even more complex structures. By adding oil and aliphatic oil, which has a very low molecular weight, around 500 Dalton, we can solve these chains and change the morphology. And by doing that, we would have gel. Unlike a chemically crusting gel, here we have a physically crusting gel, which make these materials recyclable. The main question we should ask is, what would happen for surface tackiness of these materials when we add oil to these systems? These thermoplastic elastomer gel nonwovens are very sticky. We're still working to quantify surface tackiness of these materials. Like I said, polystyrene end blocks microphase separate from the ethylene butylene part, and depending on volume fraction of polystyrene and incompatibility parameter chi n, according to theory, we can have different morphology from spherical, cylindrical, lamellary, or gyrate. And all the materials, all the grades we use here, we predict having cylindrical morphology. We use a simple setup at electrospinning to make these fibers. It's a little tricky to make these materials in metalloying. And another point is, we think because of confinement in electrospinning, probably we can have some effect on morphology, and we're curious how adding oil can change this morphology and properties of these materials. In electrospinning method, the most important parameter for fiber formation is concentration. It's very crucial to find a relation between concentration regime and microstructure formation. After dissolving our SCBS in a good solvent like chloroform or THF, depending on concentration, we would have three different regimes: dilute, semi-dilute, unentangled, and semi-dilute entangled. The most important feature in this graph is understanding where is the critical overlap concentration of polymer coils. So for example, if we be in dilute regime, we would have a porous film. By increasing concentration to up to two times of the critical overlap concentration, we can make particles. And if we increase the concentration up to 4 times of C star, then we can make fibers or nonwovens. So actually we change film and particles to fibers by changing from electrospraying to electrospinning regime. The next question is how oil concentration and process parameters or confinement in fibers can affect morphology. To better understand the effect of oil concentration on SCBS morphology, first of all, we should study phase behavior of SCBS fibers before adding oil in equilibrium condition. To do so, we ran a small angle X-ray scattering for different molecular composition. For the first 4 molecular weight between 35 to 95, we understood that we have a cylindrical morphology by comparing second, third, and fourth peaks to first peak or principal peak. And by understanding the morphology and after calculation, we realize these morphology and repeat distance of these cylinders can be changed between 20 to 30 by increasing the micro weight. For the too high micro weight, 144 and 267 kilodalton, we realize we can get lamellae. The reason here is confinement, because we can reduce our fiber diameter up to 300 nanometers, which is 6 times of repeat distance, which can be changed from 45 to 50. These results are consistent with previous work people have done before. But the question is, what would happen for phase behavior of SCBS fibers after adding oil? From previous work, we know by adding oil, we can swell mid-segment of SCBS, and by expanding the chains, these morphology can change from lamellae to cylindrical and even to spherical by adding oil and more oil. Now, the next question is, what would happen for properties of thermoplastic elastomer gel nonwovens or fibers by changing these morphologies? We found these thermoplastic elastomer gel nonwovens become more transparent by adding more oil. And we could quantify that by measuring how much light can pass through these nonwovens by increasing oil concentration. But what would happen for mechanical properties of these thermoplastic elastomer gel nonwovens? By adding more oil, we can swell our SCBS chains and change the morphology from lamellae to spherical. And as you can see, by doing so, by adding, for example, 80% of oil, we can stretch these materials up to 2200%, which is very stretchable. Then we found we can make very soft and recoverable thermoplastic elastomer gel nonwovens, which the modulus can be tuned by adding different oil concentration. For example, if you compare hysteresis of our thermoplastic elastomer gel nonwovens, when we have 80% oil, the hysteresis is much less than when we have 60% oil. At the end, I would like to thank all my friends and colleagues in Dr. Spontag and Dr. Dickey groups, and also all my industry advisors from Creighton, Dow, Halyard, and Nonwoven Institute for their support all these years. Thank you all for watching my presentation. Please let me know if you have any questions.
All right, I'm going to open up the floor for questions, but first I have a couple. Milad, why are the TPEG nonwoven so sticky? I don't have any clue about that, and I'm not sure that I got it out of your talk.
Yeah, it's the properties of elastomers, actually. Have you ever worked with latex?
No, well, I mean, latex? Not really. No,
all elastomers, because of the chains movement, yeah, okay, they're sticky. So we work with the same kind of materials, thermoplastic elastomers, and they're sticky like elastomers.
So is the oil transparent or translucent?
Yep.
Okay, so that would make sense as to why increasing the oil concentration increases the light.
Yep, it helps too. Yep, it helps.
Okay, too. Great. And I want you to comment on any practical applications on stuff that stretches that much. I mean, that's awfully cool that you can stretch it that far, but what do you do with that stuff?
I have no idea, but we try to use that. So after adding some other materials like crystallizable hydrocarbon, we realized we can make them shape memory. So probably we're trying to have a pattern on that for making some smart face masks. So imagine you putting those face masks on your face. This is that much, and then you put in your face, it can fit your face and stay there, something like that. I think this is more comfortable using such materials in some application like that. People will find that.
Are there any other questions, Chris? Looks like you're turned your video on.
Milad, I had a couple questions. The first one was you mentioned how by changing the concentration during your electro spinning process, you could go from electro spraying films to the non-woven fibers. Are there any applications for the films you guys make, or are the properties just terrible?
For sure, we can do that. I didn't have enough time to do that because my project is about non-wovens. But that's the thing. For example, when you try to have some coating on some special structure, I think that electrode deposition setup can be useful too. Yep, I agree with that. But I didn't have enough time, and my advisor were interested in non-wovens than coating of those film.
I understand. Okay, my second question is related to the transparency. So obviously the oil concentration, as that goes higher and higher, you'll get slightly higher transparency. Obviously there's a plateau there. Are there other strategies besides aliphatic oils or hydrocarbons that would increase the transparency? Because you can imagine some applications for ultra stretchy windscreens on sorts of vehicles and things. So
actually, this is very new, so I'm working on that, but I can relate that to morphology we have. So I think because we be opening those morphology from lamellae to spherical, it's much easier to light to pass through. So, but probably I should work on it to understand better that thing. I couldn't find any literature on that. It's very quite new, so we'll see.
It's an excellent talk, by the way. Sorry.
Thank you. I appreciate it. I appreciate it so much. And thank you for all your help, all of you guys, Charles, Philip, Chris, Roberto. You helped me a lot in my PhD. I forgot to mention that, but you did a great job for me. I appreciate it, guys, for all your help.
Thank you, Milad. Thank you.
Thank
You're
you.
very welcome.
Thank you.
All right. Are there any more questions for Milad? If not, then I think it's time to move on to posters. Our first poster is from Anitha Jayapalan, and I hope I did not pronounce Anitha's last name terribly wrong.
Hello everyone, this is Anita Jayapalan from Joint School of Nanoscience and Nanoengineering. The topic of my research that I am presenting today is hybridizing carbon dots cobalt oxide nanoparticles with doxorubicin and selective ligands for targeting anti-cancer effect and studying their cellular uptake mechanism. The schematic representation of the work is shown here, and it involves a coupling of cobalt oxide nanoparticles with carbon dots and evaluating these hybrid nanomaterials for biological properties such as bioimaging and anti-cancer therapy. The experimental approach here is shown for synthesizing the cobalt oxide nanoparticles with a modified microwave technique, and then using the synthesis of carbon nanodots to form a hybrid nanomaterial with cobalt oxide nanoparticles as core and carbon nanodots as shell layer. The particles were collected, dried, and characterized using transmission electron microscopy, X-ray diffraction, X-ray photoelectron spectroscopy, and UV visible and PL spectroscopies. XRD and XPS results confirmed the elemental composition and also showed that presence of both cobalt oxide nanoparticles and carbon nanodots in the hybrid nanoparticles that was synthesized, confirming the formation of hybridization. Also, the TEM data shows core shell nanostructure with darker cobalt oxide nanoparticles in the inner region and lighter carbon dots shell region in the outer. These particles are spherical in shape and they have an average size of 14 to 16 nanometer. Hence, they are very small and they can be used potentially for the biological studies. So, their cell viability was measured in EAH592-6 normal human cell lines and A549 lung cancer specific cell lines, and the results were compared with carbon nanodots and cobalt oxide nanoparticles individually as the counterparts. So the results showed that these hybrid nanoparticles are more biocompatible and also having some anti-cancer efficacy. The cobalt oxide nanoparticles are more toxic to the human cells at higher concentrations, and their toxicity was considerably reduced to a greater extent by the formation of hybrid nanoparticles with a protective carbon nanoshell region. But still, these nanoparticles have some toxicity to the human cells uh, in comparison with carbon nanorods. Instead, cellular uptake was studied in both these cell lines by confocal microscopy. Mm, with hybrid nanoparticles, and the results were compared with carbon nanorods. So here at a particular concentration of 0.4 milligram per ml, we can see that both the cell lines have taken the hybrid nanoparticles and carbon nanorods, and the hybrid nanoparticles had a brighter intense fluorescence in comparison with carbon nanorods, thereby making them as a potent bioimaging agent in bioimaging studies. So now, to improve the biocompatibility of these nanoparticles and to make them more anti-cancer and selective and targeting to A549 cancer cell line, we introduced several ligands in the cobalt oxide carbon hybrid nanomaterial. Several ligands that were used are folic acid, bovine serum, albumin, heparin, rhodamin, and transferrin, without an anti-cancer drug, doxorubicin. The particles were synthesized and the conjugates were the cell viability was performed for all these conjugates at different concentrations. The comparison results of the cell viability results at a higher concentration is shown here, and it showed that transferrin doxorubicin conjugation was the best and safe conjugate to be used with carbon cobalt oxide nanoparticles for A549 lung cancer targeting, and it had better biocompatibility in comparison with cobalt oxide carbon nanorod hybrids. So this can be the right conjugating agent to improve their anti-cancer therapeutic efficacy. Further studies has to be done to prove their mechanism by using confocal microscopy and flow cytometry. Thank you.
My name is Kristen Popowski, and I'm in the Comparative Biomedical Sciences program under Dr. Kay Chang. And for my poster today, I will be presenting my project, Fabrication and Characterization of Red Fluorescent Protein Labeled Nanoparticles. Colloidal drug delivery systems help overcome poor drug solubility and hydrophobicity by providing drug protection through nanoparticle encapsulation. This has been demonstrated most recently in the COVID-19 mRNA vaccines that encapsulated mRNA into lipid nanoparticles. However, these nanoparticle therapeutics can be further optimized by transitioning from a synthetic to a biological nanoparticle, such as extracellular vesicles or EVs. EVs are secreted by almost all cell types and contain various molecular cargo depending on parent cell origin, and numerous studies have demonstrated the therapeutic benefits of EVs as drug delivery vesicles. And so in this study, we utilize lung-derived exosomes to investigate biological EVs for protein drug delivery. And so in this pilot study, we fabricated and characterized fluorescently labeled red fluorescent protein, or RFP EVs, baselined to an RFP-loaded liposome. In Figure 1, we have transmission electron microscopy images of the native or of cell origin EVs, and in B, we have the RFP-loaded EVs. And so here we see that the nanoparticles maintain their membrane integrity and their spherical shape after fluorescent labeling. In Figure 2, we see nanoparticle tracking analysis of the native and red fluorescent protein labeled nanoparticles. 2A, we see a nice clean uniform peak of nanoparticle diameter, while we see a more heterogeneous diameter population in the RFP labeled extracellular vesicles and liposomes. Figure 3 are Western blot membranes of fluorescently labeled nanoparticles against RFP protein and a extracellular vesicle marker CD63. So we see that RFP is loaded in the EV lysate and liposome lysate while maintaining the EV phenotype, maintaining CD63 positive EV lysate. And finally, in figure 4, we co-cultured lung parenchymal cells with RFP labeled EVs or RFP labeled liposomes. And we can see in 4A that there is a much greater RFP expression in lung parenchymal cells that receive these EVs than the liposomes. And this is quantified in 4B, where we see this significant decrease in RFP uptake, suggesting that although nanoparticles were loaded with the same amount of RFP, the nanoparticle membrane is essential for cellular uptake, so that a lung parenchymal cell may favor a lung-derived nanoparticle than a synthetic particle for cargo uptake and translation. Future studies will utilize this electroporation method, and we will load it with a therapeutic cargo and test its effects in a diseased animal model for various lung diseases such as COVID-19, idiopathic pulmonary fibrosis or lung scarring, or COPD. Thank you.
All righty. Well, thank you very much for everyone who's been here this morning. That was a nice posters by both Kristen and Anitha. I put a link to actually to both posters. I thought it was only to Anitha's poster, but it was to Anitha and Kristen's posters. Those are both in the chat, so you can take a look at that and get to those. And anybody should be able to get there. If you have any trouble, please let us know. This is going to conclude this morning's session. We are going to start again at 1 o'clock with a Nadia Czech doing a live invited talk. Next, we are going to have a vendor presentation from Thermo Fisher.
Hello, I'm Tim Lunny, Applications Development and Marketing Manager at Thermo Fisher Scientific, and I want to tell you about the Nexa G2 Surface Analysis System, our next generation surface analysis spectrometer. But first, let's talk about why we need surface analysis. The surface of a material is the part that interacts with its environment. It governs how things stick together, takes part in chemical reactions, and interacts with light to define a material's appearance. So analysing the surface can be essential to understanding a material and why it may or may not perform as expected. X-ray photoelectron spectroscopy, XPS, is one of the main techniques used to understand surface chemistry, and XPS is the principal technique the Nexa series was built to employ. XPS can be used to investigate an ever-expanding range of materials. Over the years, I've analysed all sorts of things, from catalysts to touchscreens, from batteries to food packaging, even small sections of artworks to understand why their appearance is altering. But XPS isn't the only way to look at surfaces. This is why we built the system to be multi-technique, so that XPS can be seamlessly complemented with analysis methods like ISS, REALS, and UPS. It can also be configured with additional devices, like a Raman spectrometer. The Nexa G2 system builds off this innovation, improving XPS performance and increasing its multi-technique capabilities. Let's take a closer look at what we can learn using the system, walk through a typical sample workflow, and discuss some of the new features along the way. After you've started data collection using XPS, we can learn which elements are present at the surface. We can understand what their chemical state is, and we can determine their concentration. This standard XPS analysis could be extended to include things like XPS imaging, using the small spot capability of the system, or depth profiling, using an ion beam to remove material and progress from the surface into the bulk. At this point, it could be the end of the journey for our sample, or it could serve as a jumping off point to use one of the additional analytical processes that the system can be equipped with. Coincident Raman spectroscopy is one, which adds molecular and structural information to our dataset. As an example, when graphene is produced by chemical vapor deposition, there can be residue left over on the material's surface. By using XPS, UPS and Raman together, the cleanliness of the surface can be tested, and the chemistry and structure of the film can be monitored to ensure that the cleaning process doesn't damage it. All of this happens in situ, without moving the sample. In some cases, it may be necessary to affect the sample while it is in the system. The Nexa G2 system features an optional biasing sample holder to apply up to 4 voltages to a sample. This capability can be particularly useful for battery electrode analysis, where changes may occur as it is charged and discharged. There's also the option for the NX heater with full software control. This allows heating the sample up to 800 degrees Celsius, perfect for monitoring chemistry and structure as they change with temperature. To complement these new functionalities, we also have a new edition of our thermoscientific Avantage software. This upgrade updates the user interface, improves data handling, and includes the experiment control for the new heating and sample bias capabilities. One new feature that I really like is the ability to export data to maps, enabling the correlation of XPS data with imaging from electron microscopes, creating a virtual lab book based around your sample. Enhancements to performance make XPS acquisition notably faster. The Nexa G2 system can provide quick, comprehensive data sets in many analysis scenarios. There's plenty more to learn about the system. You can check out our datasheet to get detailed information about the Nexa G2, our white paper to learn about the analysis techniques available on the system, or contact one of our sales representatives to discuss your requirements. Thanks for joining me today to learn about the Nexa G2 surface analysis system.
It's like they're trying to make surface science too easy. Although it does look like a pretty rocking system. Our next talk is a student talk from Lakshmi Shivukula. I hope I pronounced your name right. And it is nanostructured surface-induced genetic response in Candida albicans. And Lakshmi is from UNCG.
Hello everyone, I'm Lakshmi Gayatri Chokula. Today I'm presenting my research on nanostructured surface-induced genetic response in Candida albicans. Candida albicans is an unicellular diploid yeast that exists in 3 different morphological forms such as yeast, pseudohyphae, and true hyphae. Each morphological form is different from one another in terms of shape as well as behavior. Candida albicans is a common member of natural human microbiome. Why is it important to study? Because it is an opportunistic pathogen. That means normally it is a harmless microorganism. However, it becomes harmful, especially in the people whose immune system is weak or compromised, thereby causing life-threatening diseases. It is a major cause of bloodstream-related as well as implant-related infections that leads to approximately 50% of mortality in the United States. The crucial virulence factor of Candida albicans that causes wide variety of infections is biofilm formation, where the cell produces a protective layer around it in order to protect itself from the external stimuli. These biofilms not only causes infections but also make the cell more resistant to antifungal drugs. Most importantly, this antifungal drug resistance is a global threat. There are so many surfaces that are available to control biofilm formation. However, bio-inspired nanostructured surfaces such as insect wings shown to be very effective in terms of controlling biofilm formation. These surfaces help the insect during self-cleaning because of their bactericidal properties. The nanostructured cones present on these wings directly pierce into the bacterial cell during the contact, thereby rupturing the cell, as you can see in this picture. So the cell rupture takes place on these surfaces because of the physico-mechanical interactions. Our lab has shown that these surfaces also rupture fungal cells such as Cerevisiae and Candida albicans, but the process is much slower compared to bacterial rupture. Also, the mechanism behind this rupture is not very well explored. So we predict that this physico-mechanical interaction influences the biological response within the cell. Therefore, the goal of my research is to study the genetic response of Candida albicans to mechanical stimuli during their interaction with nanostructured surfaces, thereby determining how such responses allow this pathogen to form biofilms. The experimental design includes the RNA was extracted from the control as well as the cells from the NSS using RNA extraction kit, followed by tag sequencing, which is a next generation RNA sequencing. The data obtained from tag sequencing was analyzed using bioinformatics tool to get differential gene expression. And the expressed genes were categorized into different pathways based on their function. In this, I used two positive controls such as sharing and anti-adhesion because the interaction was physico-mechanical. Here is the genomic data. This Venn diagram represents the total number of significantly expressed genes in each treatment. Though the cell rupture is a physico-mechanical interaction, we see less similarity between the NSS to the positive controls. It shows that this interaction is largely influenced by biological response of individual treatments. Among 178 genes that are expressed in nanostructured surface response, 101 genes are overexpressed, whereas 77 genes are less expressed compared to control. This is the pie chart that represents different physiological processes in which 178 genes from NSS response involved. This is a heat map that represents the gene expression, how it is different in control and the NSS response. To summarize the genetic response, we observed increased gene expression in carbon metabolism, mitochondrial biosynthesis, cell wall adhesion, and heavy metal ion homeostasis, whereas decreased gene expression was observed in cell cycle, MAP kinase pathway, DNA replication, and ergosterol biosynthesis. Decreased gene expression of ergosterol biosynthesis confirms the antifungal susceptibility of cells that are present on the wings, means the nanostructure surface interaction reduces the antifungal drug resistance. In this pathway, 11 genes were totally significantly downregulated in comparison with control. And these 11 genes distributed across the pathway and regulates this particular pathway at multiple sites. That ultimately leads to less production of ergosterol that makes the cell more susceptible to antifungal drugs such as polyenes. We validated this genetic response phenotypically, but before going to that, I wanted to introduce what is ergosterol and how it is related to antifungal drugs. Ergosterol is present in the plasma membrane of the fungi, which helps in maintaining the plasma membrane integrity. Also, it is a major target of antifungal drugs, especially polyenes. There are two different drugs such as amphotericin B and nystatin that comes under this polyenes class of antifungal drugs. The mechanism of action includes ergosterol, as I mentioned earlier, present in the plasma membrane. After addition of amphotericin B, it directly goes and binds to the ergosterol in the plasma membrane and leads to the cell membrane damage that ultimately leads to cell rupture. So to confirm these results, we tested this phenotypically, adding the amphotericin B to the control and treatment of two different concentrations and performed colony forming unit assay to measure cell viability. These are the results from the phenotypic validation of drug susceptibility. In the absence of drug, we did not see any difference in the cell growth between control and the nanostructured surface response. However, upon addition of 0.5 microgram per milliliter of amphotericin B, the cell growth in NSS stopped earlier compared to the control. Upon addition of 2 microgram per milliliter of amphotericin B, there is no cell growth at all in the NSS response. However, we still see cells are growing in the control. The same results represented in this bar graph, where in the absence of drug, we did not see any difference between the control and the treatment. However, after adding 0.5 microgram per milliliter, there is a significant reduction in the number of viable cells in the treatment compared to control. After adding 2 microgram per milliliter, there is no viability of cell in the NSS response, but we still see the cell growth in control. To conclude this, ergosterol biosynthesis in Candida albicans was negatively influenced by NSS response that demonstrates their susceptibility towards antifungal drugs. These results were validated and confirmed phenotypically that the cells on the NSS are more susceptible to antifungal drugs. The physico-mechanical interaction leads to the changes in genetic behavior of the cell. Finally, this understanding helps in developing an efficient antimicrobial surface to control the biofilm-related infections. So, ultimately the nanostructure surface interaction of the microbe that reduces the drug resistance and makes them more sensitive to the antifungal drugs. These results are validated using different antifungal drugs as well. I would like to thanks to my advisor, Dr. Denis Lajeunesse. Also, thank you everyone for listening.
Let's give Lakshmi a big hand. So Lakshmi, I've got a couple of questions. You showed these what appeared to be agar plates with your final growth, and it seemed like you put drops from a pipette onto the plate. How did the nanostructured surface fit into that? Was the nanostructured surface like on a really thin film on the plate?
No, actually we wanted to see the cells that are grown on the nanostructure surfaces. Means we incubated the cells for 2 hours on the nanostructure surfaces and then take the cells from the surface and drop them on the agar plates.
Oh, okay. So you took them off the nanostructured surface and put them on the plate. Okay, got it. Have you thought about trying to nanostructure your agar to grow them directly on it with some little spikes?
Yeah, actually the other student from my lab is working on it.
Okay, great. Let's see, I had one more question. How tall and dense do your little spikes need to be? Your cicada wing that you showed looked like they were about 50 nanometers in diameter, and it was hard to tell. I didn't know what the angle was, so it's hard to tell how tall they were.
Yeah, I think around 170 nanometers.
Come again?
Yeah, it's like the aspect ratio of these things are like around 2.5 and the height approximately 83.5 nanometers. And the width is like around approximately 170 nanometers. And the important feature of these rings is like these cones are like they have a cap-shaped structure on the top.
Okay. So how close together do they need to be? Do they need to be virtually touching, or can they be spread apart?
No, they spread apart with a distance of approximately 180 nanometers.
Okay. Does anybody else have any?
The distance is much less than the cell. So the cell and the distance between the cones is less than the size of the cell. So the cell doesn't go inside it.
Okay.
I mean, inside, it doesn't touch to the surface. It just touches to the cones. That's it.
Okay, so it's important that the cells are sitting on the little spikes to break themselves apart. Are there any other questions for Lakshmi? If not, let's give Lakshmi another big hand.
Thank you.
Our next talk is going to be from Hirandeep Reddy. He is from NCANT, and his talk is on improved density of gallium arsenide antimony nanowires on monolayer graphene SiO2 silicon for near-infrared photodetector applications.
Hi everyone, this is Hirandeep Reddy, and today I'll be presenting on improved density of gallium arsenide antimony nanowires on monolayer graphene for near-infrared photodetector application. As we all know that graphene is a thin atomic 2D material, and it has a strong ability to absorb light with good thermal and electrical conducting characteristics. Compared to silicon, graphene thickness is approximately 5 orders less, which excites the semiconductor industry prefer over silicon. And graphene has excellent thermal dissipation characteristics. Also, the carrier mobility of graphene is almost 250 times more than silicon, which boosts the performance of optoelectronic devices. Due to its mechanical flexibility, it is used for next generation wearable electronic applications. Here are a few applications where nanowire graphene based devices can be used in, like flexible displays, IR goggles, textile devices, and wearable devices. So coming to the growth mechanism, mostly the epitaxial growth of a nanowire uses the vapor liquid solid technique, and gold was used as a catalyst previously. But usage of gold catalyst created effects on the nanowires, which made a path for gold-free self-assisted nanowire growth, where group 3 elements like indium and gallium are used as a catalyst. So for the growth of gallium arsenide antimonide nanowires, we use gallium as a catalyst. However, the growth of nanowires on graphene follows the van der Waal epitaxy mechanism, which allows the growth of large lattice mismatch materials without creating excessive strain in the nanowires. Figure shows the VLS mechanism of growth of gallium arsenide antimonide nanowire. However, the growth of nanowires on graphene is challenging due to its low surface energy and lack of dangling bonds on the surface, which results in the formation of droplet with large contact angle, which is not favorable for vertical nanowire growth. So to overcome this, surface engineering of graphene is required. Our first approach is by using oxygen plasma treatment to improve the interaction of growth species on the graphene surface. So by oxygen plasma treatment, the vacancies like CH bond or OH bonds, which makes the surface hydrophilic. So with a weak plasma power and less exposure time, there won't be any impact on the graphene surface, like not significant impact on the graphene surface. I mean, figure shows the effect of water droplet angle before and after plasma treatment. Our second approach is by using high antimony compositional stem. Antimony's surfactant nature helps in wetting the droplet on the low surface energy graphene. By adjusting the antimony composition, it is possible to achieve the desired contact angle for the vertical nanowire growth. Also, higher antimony concentration at the nucleation step inherently reduces the lattice mismatch for improved van der Waals addition. So here is the schematic of gallium arsenide antimonide nanowires grown on graphene. So initially, graphene is transferred using the wet transfer process onto a silicon substrate. Then, the substrate is treated with the mild oxygen plasma. The growth was carried out with a high compositional stem for short duration, followed by the nanowire growth on the top. Then we have performed tellurium doped and core shell nanowires for device considerations. So growth was initiated by opening the gallium arsenic and antimony shutter simultaneously at a lower substrate temperature, which was immediately increased to the growth temperature by maintaining constant gallium flux. Growth recipe was optimized and implemented for core shell as well as for tellurium dope. So 10 minutes duration created short stem with large droplet at the tip shown in figure A, and 5 minutes duration as provided the vertical nanowires with low density along with crawling nanowires shown in figure B. So we can conclude that the antimony modulates the critical droplet contact angle at the nanowire tip with the reduction of antimony exposure time. So now we implement the same growth process on the plasma treated graphene to improve the yield of vertical nanowires. For that, we have optimized the plasma power and duration based on Raman spectroscopy and XPS characteristics. An increase in ID by IG and decrease in I2D by IG for RF power and duration of 1 watt 45 seconds and 2 watt 25 seconds suggests that the creation of a low defect concentration. And figure C and D shows the statistical data for different oxygen treated samples. XPS spectra of oxygen treated samples shows an additional peak of hydroxyl group, that is CO group, around 286.6 eV, with an increase in carboxyl group, COOH group, which can be seen in the tabular column. So these two functional groups are the key for enhancement of the wettability of graphene and helps in reshaping the gallium droplet. So by implementing the both optimized approaches, the growth was carried out on 1 watt 45 seconds and 2 watt 25 seconds plasma treated samples. So the 1 watt 45 second samples provided better vertical nanowire density as shown in figure C. Using 1 watt 45 second substrate, the growth was carried out for longer duration on intrinsic gallium arsenide passivated, tellurium doped, and gallium arsenide passivated tellurium doped gallium arsenide antimony nanowires. The maximum density obtained was approximately 7.5 per micron meter square. So the device was fabricated on sample G, which is gallium arsenide passivated gallium arsenide antimony nanowires, and sample I, which is tellurium doped gallium arsenide antimony nanowires. The wavelength dependence photocurrents shown in figure D and E suggests that the device can operate 1.2 micron. The responsivity and detectivity were estimated from the IV characteristics shown in figure 12 and achieved nearly 110 ampere per watt responsivity with 10 power 14 joules detectivity. For the tellurium doped gallium arsenide antimony with gallium arsenide shell nanowire device. With the changes in the growth parameters, we were able to enhance the density till at 17 per micron meter square, but the length was not sufficient for fabricating the device. In future, we'll be trying to optimize the growth conditions and increase the axial growth rate, which will be able to will be able to fabricate the device and will be aiming towards the telecommunication wavelength region. So here are the references. Thank you.
Hirandeep, a big hand. That was a nice talk. I've got actually a couple of questions for you. How big are your graphene sheets? A lot of times you see people, I've looked at graphene for people and they're always relatively small. So I was just curious, how big are your graphene sheets and how do you know if they're single layer graphene or if it's a multi-layer like a chunk of HOPG? You're muted. Hirandeep, we can't hear you. You're muted.
Sorry.
Don't feel like the Lone Ranger.
Sorry about that. So generally we grow on a 1-inch wafers. So we generally use around that like 1-inch graphene sheet.
So your sheets of graphene are 1-inch square?
Yeah, 1-inch square.
Wow.
And it's a monolayer, like we confirmed it using the Raman spectroscopy.
Okay. I'm always curious how people know when they have something that small because it's not like you can just look at it.
Yeah, the only confirmation is like we do the Raman spectroscopy.
Okay. On figure 8 and also figures 13 and 14, there were a bunch of islands. Are those failed nanowires? Or are those, because you also showed having little droplets of antimony? And I wasn't sure.
Yeah, that was initially we started to do with a higher exposure of antimony concentration. So with the higher exposure, we were observing short stems and longer droplet on the top.
Like growth almost sideways instead of up?
No, it was on the up, but the nanowire length was very small.
Okay.
So the droplet that was predominant. So we cannot see the nanowire growth. On the other thing, it's like completely a parasitic growth with only few nanowires growing with the shorter exposure of antimony concentration.
Okay, so when you're going to make your seems like you were, so I've looked at so many talks, I'm getting confused. Are so were you trying to make a I think I might be confusing you for your next, I am confusing you for the next guy who looks like he is working alongside of you because it looks like he was using the nanowires, but I don't want to scoop him. So at this point, I'm out of questions for you, but I do have a question for the next guy.
Thank you.
And yes, I'm cheating. I looked at all the talks ahead of time. So Toby has a question.
So out of curiosity, how your cartoon shows that you've got high aspect ratio nanowires, but I guess maybe I missed the length on them. Have you had a chance to measure lengths on your nanowires and diameters?
Yeah, actually, I've shown it in the figure 9. The maximum length that we got was around 1.2 micron, nearly like we looked it through SEM, and diameter was approximately 120 nanometer.
Okay, all right, thank you.
So on the order of 10 to 1. So
Yeah.
what sort of aspect ratio and density are you looking for with your nanowires?
Mostly like around 25 per micron meter square should be good enough to fabricate a device with good optical responsivity, optical characteristics. I mean,
does anybody else have a question? If not, let's give here indeed. Robin has a question.
Yeah, I'm the next guy you're trying to scoop in anyway.
Yeah.
So yeah, Hirandeep, about your nanowires. So you have a plasma treatment and high antibody incubation in order to facilitate the growth, right?
Yes.
So so you are using the high antibody incubation stem. So my question is, how it will impact the device performance, if you have an idea about that, because there will be such like significant amount of strain accumulation between the stem and your nano growth, right?
Yeah, but see, like for the droplet to have a proper contact angle, I'm using a high antimony there. So that will be not for longer duration, it will be a shorter duration, so that it will be getting like what I mean, like a small pillar, so that the nanowire on top of the stem can grow easily. So it's for a very short duration of time. I don't think it's gonna impact much of the optical property.
All right, thank you.
Are there any other questions for Hirandeep? If not, let's give Hirandeep another big hand.
Thank you.
And next we are going to have a vendor presentation from Teledyne.
Hello, my name is Doug Baker and I'm the Director of Sales here at Teledyne Hastings. First, let me say congratulations to all the presenters here today. Our company participates in several local events every year, but this is one of my favorites because of the interesting work that showcases the technical excellence of the researchers. For over 75 years, our company, located in Hampton, Virginia, has researched, developed, and built vacuum gauge and flow measurement and control solutions for a wide variety of applications, especially for academic research labs. Our newest vacuum gauge, the HVG 2020B, features an optional graphic display that allows the user to monitor pressure while observing pump down or rate of rise behavior of a system. The USB port can be used with our free Windows software or LabVIEW to collect pressure data. The 300 view mass flow controller is fast, accurate, and flexible. The optional color touchscreen display allows the user to quickly enter flow commands and see the results. And, like the HVG vacuum gauge, the 300 view mass flow controller features a USB port for easy implementation into experimental control and data acquisition routines. I would be honored to have an opportunity to tell you more about either of these products. I'm set up to do live Zoom demos for you. Just tell me when. Or if you're ready for pricing, we can send you a quotation including academic discounts. You can email me at dbaker@teledyne.com or live chat with any of our application engineers at www.teledyne-hi.com. Thanks for your time, and again, congratulations.
Okay, so our next talk is from Robin Pocarel. He is from NCA&T, and his talk is on separate absorption multiplication gallium arsenide, antimony, core shell nanowire avalanche photodetector.
Hi, I'm Robin Pocarel from North Carolina A&T State University. I'm currently studying as a nano engineer in fourth year of my PhD. Today I'm excited to present my current work on gallium arsenide antimonide core cell nanowire separate absorption multiplication avalanche photodetectors. The primary function of a photodetector is to convert an incoming optical signal into electrical signal. They are usually placed on the receiver front of signal transmission system, where they convert an incoming optical pulse into an outgoing electrical pulse, and they operate on a certain clock speed that is based on the speed of the photodetector. And projectors are usually made up of semiconductor materials, and they can absorb light when photons are incident on it. And when a certain electric field is imposed on them, they generate an electrical current in the circuit, and hence a photocurrent is produced. And avalanche photodetectors, they are a special class of photodetectors, and they can have extremely high sensitivity due to high electric field in the device, and can cause an avalanche multiplication of incoming photons. The motivation behind my research on core cell nanowire avalanche photodetectors are as follows. First, the core cell configuration allows the decoupling of particle light absorption and radial carrier generation, which is advantageous in increasing the device sensitivity. Consider a simple case of p-n junction in axial and core cell configuration. If we see the junction between P and N region in axial and core cell configuration, we have a large junction area which allows more light to be absorbed in the device, hence the increased sensitivity. The second advantage we have is we'll be having better control over the design heterostructure, especially if we are growing a lot of segments in the detectors. In core cell configuration, the control of the nanowire segment growth is much easier compared to axial configuration. And further, gallium arsenide antimonide region, which is used as an absorber material in our detectors, has a good absorption properties in near infrared region, which is very important for optical signal transmission as well as telecommunication wavelength region. And compared to indium gallium arsenide materials, which is highly used in state-of-art detectors, gallium arsenide antimonide has similar absorption properties, and it makes it as a good alternative material system and easier metal system to grow epitaxially because of having a single group element compared to indium gallium arsenide antimonide. And the use of separate multiplication and absorption region in avalanche detectors makes the detector less prone to multiplication noise, which is advantageous in getting a good sensitivity device. A simple schematic of the design heterostructure in core cell configuration is shown in figure in the left, where we have N gallium arsenide followed by intrinsic gallium arsenide and p-dope gallium arsenide, and finally the absorber gallium arsenide antimonide region in the outermost region. In order to get a very high electric field in the device, basically in the intrinsic segment where the carriers are getting multiplied, we have to have electric field greater than 10 to the power 5 kilovolt per centimeter in the multiplication region, which we confirmed using finite element method simulation using COMSOL multiphysics software. We can see that the junction between N plus region and intrinsic region is having an electric field in excess of 10 to the power 6 kilovolt per centimeter, which is necessary criteria for getting avalanche mechanism in our nanowires. The SEM images of the designed heterostructure is shown in figure in the left, and average nanowire length of 2.4 microns and diameter of 205 nanometers is achieved for the designed heterostructure. A crucial step in designing a photodetector is the tuning of absorption region band gap, which allows us to define what wavelength of light the photoreactor operates on. For our avalanche devices, we have a gallium arsenide antimonide material system as an absorber, and tuning the antimony percentage in the absorber region is necessary to get a certain wavelength of absorption. By tuning the antimony to around 10% incubation, we are able to get excellent absorption at 1064 nanometer wavelength, which is a technologically relevant wavelength for data communication. Figure A and B here shows the room temperature and low temperature at 4K PL peaks of the gallium arsenide antimonide photoreactor device, which shows a distinct PL peaks in room temperature as well as 4K for gallium arsenide antimonide and gallium arsenide bandgap emissions. By varying the antimony incorporation, we are able to get the bandgap tuning in this material system. In order to confirm the avalanche characteristics in our device, the temperature dependence of IB characteristics is necessary. Basically, for an avalanche photodetector, the breakdown characteristics or the breakdown voltage, it should increase with the rising temperature, because with the increase in the temperature, the randomness of the carriers in the device will increase, and they cannot gain sufficient energy to cause an avalanche compared to lower temperature for same electric field. So we should expect to see an increase in breakdown voltage with increase in temperature. So in our ABD devices, we observed an increase in breakdown voltage up to 200 Kelvin, and after that we observed a decrease in the breakdown voltage. This is basically attributed to the increasing tunneling current with increase in the temperature. It's giving a combination of general and avalanche breakdown at higher temperatures. While up to 200 Kelvin, the device showed an avalanche characteristics. So based on the avalanche multiplication at 1064 nanometers wavelength of light shining, we're able to get gain in excess of 75 at 200 Kelvin, and again in excess of 140 around 77 Kelvins. IV characteristics of the device showed unity gain around 5 volt reverse bias, which is basically the pulse through of the device when the multiplication region basically enters a full depletion state. And after that, the gain increases exponentially with the reverse bias. We are able to demonstrate power dependence of photocurrent for a reverse bias up to 30 volts, after which the breakdown occurs in the device. And with the increase in reverse bias, the gain is found to increase until the saturation of the gain reaches at certain illumination power. In conclusion, we have demonstrated and confirmed the avalanche mechanism in our nanowires up to 200 Kelvin temperatures. Again, in excess of 70 was estimated at 1064 nanometer wavelength and temperature of 200 degrees centigrade at a reverse bias of 20 volts. Our unity gain responsivity of 0.2 amps per watt was estimated at 5 volt reverse bias, and we're pretty excited about this preliminary result we have gotten, and we plan on improving the device performance further by decreasing the hysteresis we are observing right now in our DC IV strips. We plan on optimizing our pattern growth, which we have already started and demonstrated as more than 60% yield on pattern APDs. So further optimization shall lead to a more stable device performance. Also, for demonstrating avalanche mechanism in our nanowires at temperature higher than 200 kelvins, an optimization of a barrier layer is important to suppress the tunneling current at higher temperatures, which we can do by introducing a barrier layer such as aluminum gallium arsenide in our material suitably, so that we can suppress the tunneling currents. With this, I want to thank my funding agency NSF for funding this research. I want to acknowledge research facilities at the Joint School of Nanoscience and Nanoengineering and North Carolina State University for making this research possible. I want to thank my advisor, Dr. Santi Iyer, for guidance and support on this project. I want to acknowledge Dr. Zali for technical assistance in our labs and all my groupmates for continuous support in my project. Thank you, and I'll be happy to take any questions.
Let's give Robin a big hand, big virtual hand. It was a nice talk. I have a question about your avalanche characteristics. So you showed a graph that showed that it was really good at liquid nitrogen temperatures. So at 77 Kelvin, everything is wonderful. And your reverse bias goes more negative as the temperature goes up to 200 Kelvin. And then there were a couple of data points on there that showed 225 and 250, and they looked like they were trending back in the right direction towards a more or a less negative reverse bias. So is that a real effect? Is that noise in the data? I mean, do you get like this sort of a loop where it gets worse and then it starts getting better again? If, you know, does this, you know, what would happen at say 300 Kelvin?
Yeah, that's a nice question, Charles. APD, they are supposed to show higher breakdown voltage with increase in temperature because the randomness of carrier would increase with the increase in temperature. But at higher temperatures, what happens is we also get increased current in the device due to thermal energy. So avalanche mechanism basically should operate on the impact dilution process, which is which should not be affected by the thermally generated carriers because they don't cause any avalanche. They just increase the randomness of the carriers. So if we have a combination of avalanche plus Zener breakdown, which is caused due to this tunneling currents, Zener breakdown as compared to avalanche is caused by the tunneling currents. So these thermal carriers, they introduce tunneling current in the device. So if we have a mixture of those both mechanisms, then there is a chance we don't see avalanche mechanism or we see a mixture of that. So that's what is happening at the temperature above 200 Kelvin. So we are seeing a combination of both mechanisms at once, so that our breakdown voltage is not following the trend. It stops after 200 Kelvin because the thermally generated carriers are dominating now.
Okay, so I just had a quick comment too. This isn't really a question, but I noticed that your electric field intensity is approaching that we use to do field emission. So you're at 10 to the 7 volts per meter, which is right high. Mm-hmm. So have you ever thought of has anybody thought about, or I'm sure somebody's thought about this, clearly this is something that can survive near field emission like extraction fields. So have you had any thoughts about using an array of nanowires to do field emission, to make emission of electrons so that you could excite something?
We have not really thought about it, but I know we have pretty high electric field in there. So basic criteria for avalanche mechanism in gallium arsenide nanowires is we should have an electric field in excess of 10 to the power 5 kilovolt per centimeter. So this is a little bit in excess of 10 to the power 6 kilovolt per centimeter, which can be one of the reasons we are seeing tunneling in our nanowires above 200 Kelvin. So I'm not thought about that possibility you just said, but maybe we can think about it, you know. We don't know. We never know. I don't know. Like we might be accidentally discovering something else.
All right. Are there any other questions? Chris?
We're being excellent talk. That's really, really cool. For the intrinsic, the PIN, the pin junctions inside your nanowires, you mentioned one way to fight the tunneling effect at higher temperatures was to put buffer layers. I guess one question I have is what kind of buffer layers would be compatible with the epitaxy of gallium arsenide, and how would you grow those in the nanowire?
One of the material I was thinking of is aluminum gallium arsenide, which can cause an upset in conduction band, so that we can tune down the flow of carriers, so we can control their speed of causing an avalanche. So by that way, maybe we can suppress the tunneling effects in our nanowires, because we have been successfully able to grow aluminum gallium arsenide for passivating the cell, but we have not used it really to cause a barrier in the design structure. But yeah, certainly we can go that way. We have not thought about other materials so far, but maybe we can do the second way I'm thinking of is by modulating the doping, by doing a gradual increase of doping in the charge layer, so that it can modulate the speed of carriers causing an avalanche.
Okay, interesting. Yeah, those are two interesting strategies: the grading and, of course, certainly the extra aluminum. So cool. Thank you, Rabin. Thank you very much.
Thank you, Joe.
Are there any additional questions? If not, let's thank Robin one more time. Thank you very much. This is going to conclude our Thursday sessions for the Carolina Science Symposium. We will be back again tomorrow morning at 9 o'clock. Thank you all for coming. It's always good to see everyone here, and I want to give a big shout out to Shanti for always making sure that she has some good students come here from NCA&T. Good morning, everyone, and welcome to day 2 of the 2021 Carolina Science Symposium. I thought we would start off with just a couple of minutes of history, because I'm a big history fan. The Carolina Science Symposium has actually been going on for quite a long time. We started in 1998 as the Mid-Atlantic AVS, and it was held at the MCNC out at RTP in the Research Triangle Park. In 1999, it was merged with the MRS, Materials Research Society North Carolina, was merged with the Mid-Atlantic American Vacuum Society meeting, and it was still held at MRS. In 2003, the name was changed to MRS ASM. In 2005, it was first held at North Carolina State, and we started holding it at the McKimmon Center in 2014. This is our second year being virtual. We're going to try really, really hard not to be virtual next year, because part of the fun of doing one of these is being able to network and talk with people in person at the conference, often during the poster session. So hopefully we'll be back at the McKimmon Center next year. There is a survey that I'm going to give everybody a link to, a shared with participants folder on a Google Drive that's going to have a copy of the survey in it. I'd like for or the assessment form, I'd like for everybody to complete that. There's going to be a drawing. We're going to give away some money. So please fill out an assessment form and turn it in this afternoon. With that, let's go ahead and introduce Lars. Lars Kachor, I hope I pronounced that right, is from Tescan. He has a material science background. He did a lot of TEM work when he was a student, and then professionally he has worked for Olympus, Zeiss, and now Tescan. And I'm sort of feeling his pain, because I've had a similar career path, except instead of going to a smaller instrument manufacturer where there's a little less stress than a big one, I decided to come and work here. And Lars is nodding his head like he knows exactly what I'm talking about. So with no further ado, let's listen to Lars talk to us about dynamic micro CT.
Yeah, so thank you, Charles, for this nice introduction. So, and good morning to everyone from Germany. Actually, currently I'm sitting here in my home office in Germany. And thank you, of course, for giving me this great opportunity to introduce you to this exciting dynamic micro CT technology. So my name is Lars Oliver Coucher. I'm a sales development manager at Tescan, one of the big 5 electron microscopy manufacturers. And I'm supporting my colleagues regarding this quite new technology in our portfolio. We push the temporal and spatial resolution for true in situ experimentation. So what does it mean, dynamic micro CT? And what do I mean by true in situ? So in this presentation, I want to show you the advantages of performing true uninterrupted in situ experiments in your lab. So in general, dynamic micro CT means a 3D record of a complete dynamic process over time. For example, here, it's the compression of a metal form. It is often called 4D, but for me as a physicist, it could have much more dimension as space and time. For example, force, pressure, electric current, or temperature. So let me start with an example of a highly dynamic process. So in this experiment, we dissolved a multivitamin tablet in water. We've recorded the complete process in 3D by rotating the sample continuously. Almost 40,000 2D projections were acquired with a temporal resolution of less than 6 seconds for one 360-degree turn. More than 100 turns were acquired in total, which means a lot of data. Here you see virtual 2D cuts through the reconstructed 3D data. Before starting with dynamic micro-CT, let me outline my presentation. Some of you might not be familiar with micro-CT and how it works. I will compare the time-lapse imaging and true in situ imaging. You will learn about the ingredients you need for doing dynamic micro-CT. And in the end, I will show you an example where temporal resolution meets high resolution. So applications for micro-CT are very manifold. Actually, there's no application which doesn't need a micro-CT. It is a non-destructive and complementary technology to electron microscopy. So maybe you will find your application here. If it's not there, please contact us so that we can perform your sample scans, and we put this here on this list. I will show you today some material science examples, some geoscience or building material examples, but you can clearly see that there are some moving images, and this is actually where we perform this dynamic micro-CT. So many of you uses already SEMs or even FIPSEMs. By this application example, I would like to emphasize micro-CT as an extension to SEM. So this is an application where the customer looked at carbon fiber reinforced polymer. They drill hole into multi-layers and see the effects of it. So it's a work done by the American University of Sharjah in the United Arab Emirates. So with an SEM, you can only look on the surface. This is in comparison, this is a 2D cut through a 3D volume acquired with the micro-CT. And you can clearly see the single carbon fibers and the polymer matrix. You can even see some very small voids between these carbon fibers. So again, micro-CT is a non-destructive technology, a method to look inside your sample. You can even see a large field of view, a large sample. So with this volume, we scanned 1 cubic millimeters, which is in comparison to a FIPSEM volume, very, very large. We scanned this at 400 nanometer voxel size in less than 9 hours. It's a typical overnight experiment. And of course, what you also can do with the micro-CT, you can do multi-scale imaging by changing the magnification down to sub-micron resolution. The results can be easily analyzed in 3D, of course. For example, this cracks where we looked in the detail on these cracks in the sample. You can segment the crack, look on it, see the orientation, measure the orientation, the volume, and so on. And you can even perform some advanced 3D analysis by measure the fiber orientation and give them a false color to see how well they are aligned inside the sample. So before getting too far ahead of ourselves in this exciting world of dynamic imaging, we need to make sure you all have a reasonable understanding of the basic of micro-CT. So how does micro-CT work? The principle is shown here. We have an X-ray source generating X-rays. We have a cone beam. We use white X-rays. We can change the spectrum by changing the energy and the power and by using filters to adapt the best contrast in our images. The sample is rotating inside the beam, and then there's a detector, and this detector converts the X-rays into an electrical signal. We acquire a set of 2D projections, usually thousands of 2D projections, and depending on the density of the material or the thickness, you can see bright and dark areas inside your images. You all most probably know this from a medical CT scanner or medical X-ray image. So these 2D projections are now reconstructed into a 3D model. And this can be rendered, or you can do virtual cuts and so on. So actually, you've got the 3 steps of micro-CT. It's the acquisition, the reconstruction, and the visualization and 3D analysis. So again, the advantage of using CT is that it's non-destructive. The world is not only three-dimensional, it's multi-dimensional, it's dynamic. And if you look at the ratio of publications in 4D versus 3D X-ray tomography, you see a significant increase in 4D time-lapse studies over the last decades. So time-resolved X-ray imaging informs us how materials form, deform, and perform. And why isn't it done more regularly? Actually, it's hard to perform. And there's just a finite number of PhD students, of course. The challenges are at every step: the acquisition, how to set up the in situ experiment, the reconstruction, the visualization, and of course the analysis. And many of the steps above are challenging enough in 3D. So let me now compare the in situ versus the true in situ. So graph B shows just a standard interrupted in situ experiment, which is performed in the standard micro-CT system. Here, the temporal resolution is mostly unimportant, but the process has to be stopped, which leads probably to sample relaxation, shown here in this graph. And if you expect a main event during this experiment, you have to cautiously approach this event. On the right side, you see the dynamic micro-CTs, the true in situ, where we do an uninterrupted scan. So we perform multiple scans during the complete process to acquire the complete process in 3D. So we have all events happen during this process recorded. And dynamic CT is the only way to get the most complete true in situ results out of your experiment. To start us off, let's look at the first example. It shows some exciting work we are doing with collaborators from Rush Medical University in Chicago, where we've performed in situ and continuous compression of additively manufactured titanium serial spacers. So the end goal is to examine the deformation of both the spacer and the vertebra as they go undergo loading. So for this test, we performed uninterrupted scan at 34 micrometer voxel resolution at more than almost 40 seconds temporal resolution for a total of 100 rotations of the sample. On the left, you see a video of the continuous rotation of a Demon load stage enabled through a no cable wrap interface. On the right, we see a series of virtual cross sections from the dynamic CT data. And this was the first time Rush could see the process without any relaxation effects during the scan because of an uninterrupted 3D imaging. So the key features to enable routine dynamic true in situ studies, it's of course, you need a good hardware, an optimized hardware. Of course, you need your in situ stage for a flow or mechanical experiment. You need stage designs for a fast, continuous, endless rotation. You need high power X-ray sources for high brightness or high flux. And you need, of course, fast readout detectors because you are handling short exposure times here. And on the other side, you need, of course, the software to control the system. And remember the 3 steps of microscopy: acquisition, reconstruction, visualization. You've got open scriptable environments, so that makes your life in the lab really easy to set up your scan. And the stage and the sensors can be read out by the system and to coordinate all the data you acquire. And of course, we have also some nice software features. I would call this now event detection, which I will show you in the following examples. So hardware, software, but the synergy between the hardware and the software, this is the key component to enabling and dealing with dynamic imaging. So it's not trivial to do continuous imaging and except to be able to make sense of it after the fact. So again, we acquire the complete process in 2D. We acquire all the 2D projections here during the scan. For example, process 1 is some continuous process, or you've got a process 2 where we have some events happen, maybe this in this a crack or something like this. We acquire the complete process in 2D by an uninterrupted acquisition. and when to reconstruct this data. So actually you can do it by automatic reconstruction. For example, every third turn you do a reconstruction. You can even combine the reconstructions here to reduce the noise in the images. You can move the reconstruction windows here to increase the temporal resolution. And you can, of course, also extract the stable voxels for doing masking processes, which is usually done for flow experiments inside the experiment. You can see, by the way, the Deben stage, and where we performed this in situ experiment, this compression of this limestone. And we read out now the signal of the stage. It's shown here, the force time curve. And you can see that there's some significant drop down here. And this is actually where this crack occurs. But if you perform now this experiment, when did this event happen? That's the question. We read out the signal of the sensors so that we know now the exact time point where to move the reconstruction window to really see the status before and after the crack. So, and where to find the event in all this data? That's really the great question. And so how we are going to analyze all these events. So in this example, we'll look at the metal form compression at different time points. So it's a strut bending here. You can see here, the black areas is air and the bright areas, it's actually the metal form. And during the time this metal form, this strut here is bent so that it moves here into this black area. And we do now detect all these flip points and localize them. We know exactly the location where it happens and also the time. So this and all these positions of the kinds are thus known. So let us have a closer look on this metal form application. Metal form is an important component in a number of designs, most notable for reducing weight while maintaining strength and as an energy absorption material in crumble zones in cars or trains. So an understanding how these structures change under load can be very useful, especially for refining simulations and models. In this case, we have compressed an aluminum form, and from the 3D renders, you can already see some significant change in the structures, which also correspond to a notable signal change in the force curve shown on the right. A commercially available compression stage from Deben was here used, and you can control and read out the motors and sensors during the scan, as the in situ stage is connected via slip ring connections to the PC. This also enables an endless rotation of the stage during the scan, so no cable winding around the stage. So let's have a closer look on the event when the force curve drops down at almost 400 seconds. So having recorded the complete process uninterruptedly in 3D, we can easily look at special or all events happen during the experiment. This isn't possible by performing an uninterrupted scan in a standard CD. So here we are looking at the event when the load curve falls at almost 400 seconds. By moving the reconstruction window to that time point, we can see the strut just starting to neck. Moving the reconstruction window further in time, the strut is necking, and finally the strut failed. So the ability to link the physical deformation so closely to the actual loading behavior is very useful for better understanding of the details of mechanical performance. So in a bit more recent work with form, we partnered with the folks at Math to Market and performed some simulation based on dynamic CT data. So I won't go into all the details, but the lower right movies show renderings from both the dynamic CT data on the left and the simulation on the right. There are some differences in the strain stress curve, but the overall behavior between the experimental results and the simulation is quite similar. Oops, sorry. So in fact, in this experiment, the dynamic CT results helped us to derive the appropriate material characteristics and initial boundary conditions used in this simulation. We were able to apply those to other samples and continue to have very good agreement in the results. At the last example showing the combination of high temporal resolution and high spatial resolution. In a collaboration with Purdue University, Indiana, US, they want to understand how water is taken up in a tablet, as this has an impact on the drug delivery. In their setup, they take a needle with water and acquire the process with the camera. By using this method, only surface information is obtained. So why isn't it done before with the micro-CT? Because the tablet disintegration is very fast. And the full integration of the tablet takes minutes, and you cannot slow down or interrupt the process. So we put the tablet on a tube and control the water flow with a medical syringe pump. You may think that the cables and tubes cause a mess. So look how we set up the experiment. So here's a look into the interior of the micro-CT. So you can see on the left, you can see the X-ray source and the detector and the stage. And we place the complete in situ stage or the complete in situ rig on top of the stage. The connections of the syringe pump were made through an in situ integration kit and slip ring connections for endless and uninterrupted rotations. Here are the scan setups. So 50 rotations, uninterrupted, continuous, 4 seconds temporal resolution. So this is the time for one rotation at 12 micrometer voxel size. These are the first results showing the inside of the tablets during the 3 minutes water uptake. On the right side, you see a virtual cut showing the crack generation and propagation. The data was 4D analyzed to show the effects of water uptake over time in detail. To see the crack propagation in detail, we performed high resolution scans before and after water was uptaken. To understand the complete process, it is important to know the microporosity with its wall thickness. You can see clearly the active ingredients and how the crack moved around it. The high resolution scans of the initial state and the end stage were made with 400 nanometer voxel resolution. So I hope you enjoyed the introduction of dynamic micro-CT today and some of the application. To close up, I just want to reiterate that our goal is to make dynamic CT imaging a commonplace and a routine technique in your lab. All our products have been engineered with this goal in mind. And by coupling the hardware, software, our know-how, the blood and spheres, the experiments we put inside this, this technology, hopefully we can enable a new era of dynamic micro-CT. So thank you for your attention and come and visit us in Ghent. Thank you.
Let's give Lars a big virtual hand. So I have some questions for you, and these are maybe kind of in the weeds because I'm a imaging guy. Granted, I'm an SEM guy, but imaging with electrons and imaging with photons seems a lot alike. So you talk about resolution and you say submicron. How submicron are we talking about? The best you showed was about 400 nanometer voxels. How far can you push it?
So we can go down to less than 600 nanometer spatial resolution. So that means actually voxel size about some hundreds of nanometers, or
Okay.
even below hundreds of nanometers. Yeah.
So you showed a picture that had a little hole drilled in it, and they had looked like it was an SEM image, and then you showed another image of the that one. So is this something, a technique that you could use to identify a region of interest where you might want to do further processing to the sample or sample prep so that you could put it in a higher resolution instrument like an SEM or a TEM?
Charles, that's a really great question, because actually this is something I haven't mentioned in my presentation. This is what we call correlative microscopy. You can use the micro-CT to find the needle in the haystack, to find the feature in your sample. Then we know the coordinates, and then we can make a target sample preparation for doing the FIB-SEM or even SEM EDX analysis, for example, and something like this. Yes, we can. And this is something we want to also release, I think, in the near future.
Yeah, that was going to be my next question: is how long are we looking for a integrated instrument that will give you micro CT and sample prep and SEM all in situ?
Yeah, so it's So I'm sales, I'm not product management, so don't ask me, please. So I would say it should be. So right now we have, I think we have also examples for doing this with some kind of workaround. The technique is available, but now we have to connect it to make it simple for the user to perform this kind of correlative microscopy with the systems.
Okay, I got another couple of questions, and I'm going to turn it over to anybody else that has a question. What's your X-ray source energy? Just out of
we go so from 30 kV up to 230 kV.
Okay.
And it depends on which system. So that's all 160. It's a standard kV. So for 160 is for the high resolution instrument, and for the large sample tools, there we go up to 230 kV and up to 300 watts. So that's a lot of power. That means large samples and high throughput.
Yes. How do you decide how fast to scan? So I'm guessing that this material depends on the material, because you showed several examples where you gave a amount of time to do a scan. And so how do you decide how long to scan to get a reasonable signal to noise? Is that something you just try, or is that something you can calculate?
There's the experience actually. First of all, you have to know how fast is your process. Usually this is the limitation, and then decide where do I get the best results out of this. You can perform, for example, in when you've got a stable matrix of material, for example, rock samples, then you can perform high resolution or high quality scans in the very beginning. And then you perform your experiment, your flow experiment, for example, and then you can combine the high quality image with the flow inside this sample, and combine the good resolution with the would say bad or fast resolution.
Okay, great. So and it was actually a wonderful talk. I really like pretty pictures and pretty movies. So I really ate this up. Does anyone else have any questions? Looks like Toby's got one.
So out of curiosity, what data set sizes are you dealing with? I know for a full 360 scan, just a single rotation, you're dealing with, like, let's say 20 to 100 gigs worth of data. Are your data sets significantly larger, or is it because your exposure time is significantly lower, it's a little bit smaller?
So actually the data from, so that's a good question. The data from the acquisition is much bigger than the data for the reconstruction, because actually we do not acquire only one image, we acquire several images for one position, actually to integrate these images to get rid of noise inside the images. So that's why this the raw data of the 2D projections, it's more by maybe factor of 3 or 4 or something like this. The data of the reconstruction, of course, it's 100, I would say the hundreds of gigabytes or 100 gigabytes, something like this.
Okay, well, thank you. It's a wonderful talk. I guess my slightly off topic or follow-up question is, do you set up multiple recipes to do multiple scans, or is this the same scan just repeated multiple times?
So we actually, that's our strength. So it's some kind of an outcome of our system. So we can perform dynamic micro-CT. That also means that we have got short scan times. So just if you want to scan one sample, then we can do this in a short scan time. But we can stack the samples, for example, and do a batch acquisition of the stack of the samples in a really short time. So it's also possible, yes.
Right, wonderful. Thank you so much. It's wonderful.
Does anyone else have a question? If not, let's thank Lars one more time. That was an awesome talk, Lars. Thank you so much for being with us this morning here, this afternoon where you are. Because Lars is talking to us from his office in Germany. All right, with that, we're going to move on to a vendor presentation by Allied High Tech.
Hi, this is John Criswell. Welcome to Manufacturing Marvels. For more than 36 years, the Allied High-Tech Products Corporation has offered customers superior quality products for metallographic sample preparation and analysis with experienced technical assistance and warm, friendly service. Their measure of success has always been the customer's complete satisfaction. Allied is a vertically integrated company, meaning the entire product development cycle is executed in-house at their Southern California headquarters. Vertical integration provides for more intelligent product design, better product quality, faster turnaround times, and the ability to customize products whenever needed. Allied's team of mechanical and electrical engineers designs their equipment using state-of-the-art software. After component fabrication, machines are assembled and tested at their facility to ensure maximum performance and dependability. Their applications laboratory develops individualized sample procedures for customers using Allied's equipment and consumables. Materials engineers create comprehensive reports offering detailed step-by-step instructions for a wide variety of standard to challenging materials. Their technical support team is available to assist customers in selecting the right product for their material. With the largest inventory of its kind, Allied offers a wide variety of high-quality consumable products for use with their equipment. Their next-day order processing supports the immediate needs of customers worldwide. Allied has shown proven success, expanding their facilities 7 times and now offer more than 40 machines for sectioning, mounting, grinding, polishing, and precision milling. With unparalleled customer service and nearly 5,000 products to offer, it's no wonder that industries such as aerospace, defense, automotive, education, semiconductor, and medical rely on Allied. Visit Allied at alliedhightech.com. This is John Criswell for Manufacturing Marvels.
Okay, next on the agenda is a student talk from Hao-Yu Tong from Duke University. And Hao-Yu is going to be talking to us this morning about controlling the voxelized attenuation of 3D printed physical phantoms for computed tomography with a single material.
I'm Hao-Yu from Duke University. Today, my presentation is controlling the voxelized attenuation of 3D printed physical phantoms for computed tomography with a single material. So first, let's come to the base of the X-ray attenuation. When the light passes through an object, the part of the light will be absorbed by the object, and this can be characterized by the linear attenuation coefficient. For the CT, each widely used imaging method in the clinic, it can generate the 3D volume and also the cross-sectional image, which makes the doctor easy to see the interest area inside the body. And the unit that the CT uses is a hot field unit, HU, which we can just simply think it as the attenuation with respect to water. So as we can see in the example CT image here, for the dense part, which mainly the bones, it will become brighter in the CT image, while for the light parts, the soft tissue or the air, it will become more dark in the CT image. So, but we know that X-ray imaging may still have some drawbacks. It may be harmful to human body if high dose is used. So that means we cannot use human people to do the research. So that's why we have the physical phantoms. It's used to simulate the patient. So this currently, we use physical phantoms to evaluate and calibrate the imaging system. The phantoms can be scanned regularly and to compare with the standards and other machines to make sure the imaging system is working appropriately. So the requirement for the physical phantoms is that we wanted to have similar contrast level with respect to human body. We want it to be stable, reproducible, and have realistic anthropomorphic structure. Another thing we wanted to have is we want it to have relatively low cost. However, for the commercial phantoms, which in the picture here, the usually we have a relatively simple structure and doesn't really match the real anatomy of the human body. And the cost of these phantoms are also pretty high. 3D printing may be a potential way to solve the problem. 3D printing can replicate the complex structure of the human anatomy. It also enables the low batch size projection, which makes it easy to fabricate the realistic task-oriented phantoms. So the goal of our projects is to fabricate a phantom with realistic structure and contrast similarity with respect to human. We first have a brief introduction to the fused filament fabrication. Basically, we have the filament, which is the thermoplastic. We will let it go through the heated nozzle, so the thermoplastic will be melted and deposited on the hot bed. The process will be repeated layer by layer. So if we look at one layer of the printing process, it will first print the outline, which is called the shell, and then it will come back and print the inside part of it, which is called the infill. And this is a 20 infill percentage illustration. The infill angles and the pattern, which controls how the lines is joined inside the shell. So if we increase the infill percentage from 20% to 60%, we can see we actually draw more lines inside the same area, which increase the density of the object. So the first thing we want to do for print a phantom is we want to achieve a uniform background. We actually test two sets of things here. The first thing is the infill angles. As we can see in the left three figures here, if we use a two angle for the printing, we can see in the figure B, which is the city image, that the pattern is pretty obvious under CT. But when we increase the infill angles to 9, we can see the city image have a more uniform pattern than the two angles. Similarly, for the infill pattern, we can see that the rectilinear pattern is more uniform than the other two patterns. But we still need to admit that it may still cannot be compared to the commercial uniform phantom. After achieving a uniform background, the next thing we want to do is control the contrast of the printed object. We try to do this by changing the infill percentage, which basically we doping air into the object. So as we can see in the figure C, which is the resulting city image here, that when the infill percentage is pretty low, for example, 20%, the pattern of the print is pretty obvious on the city image. But when we increase the infill percentage to about 6%, we can see it will have a relatively uniform pattern under the city image, and the standard deviation is also much lower compared to the 20%. So by using this method, we can actually build a relationship between the contrast and the infill percentage. Also, usually in the soft tissue, 200 HU value will be the typical range, and this can be achieved by using an 80% as a background and to increase the dense parts infill percentage to 100%. This method, changing the infill percentage, gives us the base of our method, which we can change the contrast levels. So the next thing we want to do is to combine multiple levels of contrast in one object. This is just some illustration of 3 different methods we tried. The first thing is the conventional method, which is the shell. So first we will print outer shell, fill the outer part, and then come back to print the inner shell and fill the inner part. Be sure the inner part and outer parts will have different infill percentage, since we want to achieve different contrast levels in the 2 parts. However, if we look at the CT image, we can see that it has a very bright boundary between the inner part and outer part, which is not what we want. So we want to eliminate this effect by using no-share method. But the boundary still exists. So the method we finally come up with is use the backfilling method, which basically we will first print the background, and then we will come back and print another layer on the background, which is called the backfilling. By using this method, we can actually achieve a smooth transition between the inner part and the outer part. It may still have some problems for the backfilling method. As we talked at first, that in order to achieve a suitable soft tissue range, we may need to have an 80% infill percentage for the background. And to make sure the phantom is uniform, we need to have at least 60% for the backfilling region. But the thing is that if we combine these two things together, then the backfilling parts will actually extrude, more materials will be extruded in the backfilling part, which will actually increase the height, cause an uneven layer. It will finally hit the nozzle and crash the print. So in order to solve that, we need to change the extrusion multiplier. The default value is 1. By changing the extrusion multiplier to 0.25, we actually decrease the amount of filament that is extruded in the backfilling region, which can help to solve the uneven layer issue that's caused by the backfilling process. So as we can see in the figure A here, that by changing the extrusion multiplier, we can actually change the contrast levels in the backfilling region. And we kind of just build another relationship between the contrast and the extrusion multiplier. After achieving this, the next thing we want to do is to combine multiple levels of contrast in one object. So we designed the pi object. But if we use rectilinear pattern for both the background and the backfilling region, we can see it will generate a relatively high contrast boundary between two levels of contrast, which is not ideal. But if we use fast honeycomb for both the backfilling and the background pattern, it will have the dark line artifact, which is generated in the printing process. So finally, we decided to use a rectilinear pattern for the background and the fast honeycomb pattern for the backfilling region, which gives us a more uniform background without the artifacts. So after figuring out the settings, we will now trying to print the actual phantoms. This is the contrast detail phantoms. As we can see in the picture that different size and levels of contrast can be achieved in the phantom. There may be some deviation exists. This is due to the inaccurate motor movement because we actually extrude a very tiny amount of filament in the object. And we also try to print the liver phantom. As we can see in the figure that the irregular shape can be achieved by using this method and the details can be represented clearly. In conclusion, we are able to achieve 8 levels of contrast within one object using a single material. The anatomic liver phantom with similar contrast levels can be printed. But this method may still have some limitations. As we talked before, even we try to maximize the printing parameters such as the infill angles and infill pattern, the result object is still less uniform than commercial phantoms. The resolution of the printer may still be relatively low. and there is some deviation between desired and actual contrast level in the small print region. This is because we just use a desktop printer, which is pretty cheap. So we assume that if we use a printer with smaller nodal size and finer motor control, it will help to solve this problem. Another problem with our method is we only use one single material. So the HU value range that we can achieve is relatively narrow, so that it may be hard for us to mimicking bone or iodide contrast. So in the future, we may make use of the multi-material printer so that we can print the phantom with different kinds of materials, which the phantom can be used for dual energy CT. So that's all for today's presentation. Do anyone have any questions? Thank you.
Very, very nice talk. Let's give Hao-Yu a big hand. That was awesome. In fact, it met part of what I think of as the mark of a good talk. Every time I came up with a question, you answered it in the next thing that you said or on the next slide. So you killed a lot of my good talk questions, although I do have some questions for you. What's the difference between a physical phantom and a standard? Is a phantom more like a reference in that a standard is a single material and you calibrate based on the absorption of that single material, and a phantom lets you evaluate multiple things? Is that the way that works?
Yes.
Okay, so I got that right.
And yeah, and also phantom have different size, which you can use to test the limitation of the imaging system or something like that.
Okay, so yeah. And it's also would be nice to use a phantom as to mimic what you would actually try and look at. I sort of got that out of your talk. So one of the questions I had was, if you had a more high-end printer, how hard is it to expand to multiple materials? Can higher-end printers have multiple nozzles and print with different materials in the same place and give you different contrasts?
So I haven't really looked into that. So what I know is currently there are some like we don't really need that much kinds of material, right? So basically, if we're trying to use soft tissue, it's just some common filament PLA, something like that. And the other things we may need is just the iodide contrast or the calcium-based filament, which we can use to mimicking bone. So basically, if we want to have bone and soft tissue in one object, then we only need a printer that can print two material, which is the very basic multi-material printer that can do these things. And I know there is also a printer, which is still a desktop printer, which can print up to 5 material at once. So I don't think it's a problem for finding a printer that can print multiple material, but but the printer that I talked about are more like the desktop printer. I'm not exactly sure for the very finer control printer.
So do you guys are you guys trying to get funding to buy a higher end printer to expand this? Just totally curiosity.
Yeah, currently no. Like currently we are not having enough funding to do this. So that's like the limitation.
Yep, funding is often the limitation. Yeah. So it looks like Marcio has unpaused his video and he has a question.
Yeah. So if you're going to choose a material, a different material, what criteria are you going to use for that? And how are going to be, what's your expectation to extend the range of contrast? Okay, so
so basically so if we use some, we previously tried to use some calcium base, which is doped with calcium carbonate, the filament. So the highest H value of that can be about 300 to 400, something like that, which is not really similar to the bone. But if we use some copper-based filament, the H value can be up to like 3,000, something like that. So like we can find different kinds of dopers in the filament, which a lot of this filament are already like commercial filament. So we can just use that. Otherwise, we can like for the fused filament fabrication, it's also relatively easy to dope your own material into the filament, like through trying to make your own filament, which like it's also be fine. So my idea is that we may find since for this method, we are just using the backfilling part for the different materials. So I was trying to find a filament with higher levels of contrast, so it can still generate a relatively high range of contrast in the backfilling. So
how's your contrast change with the orientation of your filling? Do you have any idea, for example, if you have a phantom and you have an image in one plane and then you rotate a little bit?
You mean if I rotate the image, will the contrast change? Sorry, I'm not exactly sure I understand your question. Can you repeat that again?
So if you have your phantom model, right?
Yes.
And you do you scan how sensitive it is if you change the rotation, and your filling has some orientation too, right?
Okay, so I don't think changing the rotation will change the contrast, because you can just think it as a sort, like, because the layer thickness of the printing is pretty low, and the thickness, the slice thickness of CT is much higher than the printing thickness. So like if we try to, like in the actual CT image, we try to kind of rotate it or like not aligned very well. That's happened before, and the contrast level didn't really change.
Okay. Thank you. Nice talk.
Thank you.
Andy, you have a question?
Yeah.
The question is, how large can the test pieces be made, and what do you think? Do you think the results will scale with size?
Okay, so the things currently for our print, the test piece, the size will be limited to the printer size, right? So the printer size, usually the printer size, the printer bed size, I cannot give you a very accurate number, but it should be about like about an A4 paper size or something like that. So which kind of that size, like maybe slightly larger than that, but similar. So this, and the height of the printer bed should be about 20 to 30 centimeters, I would say, for the height. So that means we can only print a relatively small organ or phantom compared to the human body. But I would think we don't, but that thing is like you can just print some small objects and group them together too. And this is just the limitation of the current printer that we use. And if you think for the result that will be scaled with size, I'm not sure what do you mean the results. So if we just print a larger piece which have which is thicker or larger, for the parts that we print, the density won't change because the infill density is still the same. So, but like the overall, so we do CT because we generate the sliced image. So it's like the sliced image has contrast in it. But for the overall attenuation, because it's thick, so if you're doing the X-ray, if it's thicker, then the contrast will be higher, but that's different image methods across that. Yeah.
I think that's the last one. All righty. Well, with that, let's thank Hao-Yu once more time. One more time. That was an awesome talk. Thank you very much.
Thank you.
The next talk that's coming up is from Jijo Christa Justice. I hope I pronounced his name right. I probably mutilated it. He is in the Materials Science Department at North Carolina State University, and his talk is on age hardening of supersaturated non-crystalline aluminum 5 vanadium alloys.
Hello everyone. Today I will be talking about investigation on microstructure, corrosion, and mechanical behavior of supersaturated nanocrystalline aluminum 5 vanadium alloy after age hardening. My outline is as follows. I will be introducing about this work. Third, material preparation and techniques involved for this work. Third, choosing different aged condition. Fourth, characterization on these aged condition specimens. Fifth, mechanical and corrosion performance on these aged condition specimens. Sixth, corrosion phenomena and inhibition mechanism. And seventh, I will be concluding my work. Researchers have shown that supersaturated nanocrystalline aluminum alloys have the potential to exhibit high strength and high corrosion resistant property. But if this material is exposed to high temperature, for example, if we want to have the precipitation hardening in this material, then it raises concerns for two reasons. First is the stability in grain structure at elevated temperature due to the high driving force of grain growth. Second is the decomposition of supersaturated solid solution at the high temperature. Since this high energy ball milling used for this work is a non-equilibrium process, the decomposition at high temperature is inevitable. So this work will answer whether it is feasible to enhance the strength of this material by introducing the precipitate, as well as at the same time whether it can preserve the corrosion performance. High energy ball milling used for this purpose was used to alloy aluminum and 5 atomic percent of vanadium, and 280 RPM speed was used for, and the milling was done for 100 hours. After that, the powders were consolidated at room temperature at 3 GPa pressure. These consolidated samples were then heat treated at 3 different temperature, 150, 200 and 250 degrees Celsius for comparison. These specimens were then characterized using the techniques such as SEM, XRD and TEM to identify the phase as well as the microstructure modification and the surface phenomena, while Vickers hardness was used to obtain the micro hardness. After the ball milling process, particles showed the refinement of less than 100 micron size. And this particle refinement also depends upon the solute content added, as well as the properties of the solute. After the consolidation of this powder particle, we observed a homogeneous distribution of vanadium across the surface, across the microstructure, as well as the bright phase was observed, which is Fe-rich particle introduced during the milling process. And the TM micrograph also showed the dark gray phase of nano size, which is a C-rich phase introduced due to the stearic acid used during the milling media to prevent the agglomeration of the powder particles. The other TM graphs with the inset of SAD pattern shows that nanoscale grains have been obtained, and the grain size distribution showed that the high energy ball mill specimen showed 29 nanometer average grain size. Hardness was registered after the heat treatment for all the aged specimen, and it was seen that the peak aged condition decreased with the increase in the aging temperature, as well as the peak aged condition was obtained quickly with the increase in the aged condition. While the base alloy is the unaged condition showed over here, which was around 300 HV. The highest peak hardness was obtained at 150 degrees Celsius, which is 15% higher than the base alloy. And after this, the few 5 specimens were selected for the further characterization. And those are the base alloy, that is the unaged condition as a reference, then the peak aged and overaged conditions of 150 and 250 degrees Celsius. XRD graph as well as the SAD pattern confirm that the precipitate formed after the heat treatment are the AL3V precipitate, as well as We also calculated the solid solution of vanadium after the heat treatment, and we could see the intents of the decomposition with the exposure of the temperature, where in the initial stage, the base alloy, after the high energy ball milling, we observed 3.1 atomic percent of vanadium in the supersaturated solid solution, and that was 10 raised to 6 times higher than the thermodynamic value. But with the exposure to the heat treatment, we are seeing that the 250 degrees Celsius overage condition shows the lowest solid solubility of vanadium, and it got affected compared to the others. Whereas the grain size distribution of this specimen showed that they are still exhibiting the nanocrystalline size, and the 250 degrees Celsius overaging condition showed the highest grain growth of 68 nanometer compared to the others. With the help of the TEM, we also try to understand the precipitate morphology and distribution, and we observed a spherical precipitate all over this matrix, and the intensity was correlated with the exposure time and the temperature. We could see a high amount and the high density at 250 degrees Celsius overaging condition compared to others, whereas for the overaging condition of 150 degrees Celsius, we observed the coarsening effect of the precipitate. Comparing the hardness value with this microstructure, it is not possible that the hardness value should decrease even when the small-sized precipitate was formed, but the drop in the hardness value could be due to the high grain growth and the decomposition of the solid solution, which we have observed compared to the others. Comparing the corrosion performance, we saw that after the high energy ball milling, we obtained a better corrosion performance compared to the pure aluminum. And once it was exposed to the different heat treatment, at decaged condition of 250 and 150 degrees Celsius, the corrosion performance was showing the similar as the base alloy. It shows that it was preserved up to some extent. Then once it moved to the overaged condition, the 150 as well as the 250 degrees Celsius showed the degradation. As we can see over here, the lower E-core value, that is the corrosion potential, as well as the high corrosion current density compared to the others. Studying the surface phenomena through TEM, we saw that the passive film kinetics was not changed after the heat treatment, and it showed the same thickness, that is 5 to 6 nanometer. As well as we also found in all these specimens, we saw that the vanadium enrichment was observed at the oxide metal interface, and this is one of the factor which has increased the corrosion resistance of this base alloy as well as the other aged condition compared to this pure aluminum, where the synergic effect of the vanadium enrichment on the surface as well as the supersaturated solid solution with the nanocrystalline grains has provided the good corrosion performance compared to the pure aluminum. We also made an attempt to show how the secondary phase, once it is exposed on the surface, provides a heterogeneity and promotes the localized corrosion. Here we have shown that there are two sections. First section shows when this surface was not exposed to the aggressive environment like chloride environment, while the second section shows after the immersion in the chloride environment how the surface reacts and how the corrosion occurs on the surface. In the first section, we are seeing that the sea-rich phase as well as the precipitates are exposed on the surface, and due to that, we are seeing a thin discontinuous oxide film over that cathodic surface compared to the homogeneous passive film on the matrix. While once it is exposed to the aggressive environment, we are seeing that carbon-rich phase is showing a galvanic interaction with the matrix, where the presence of oxygen at the interface shows that the reaction, oxidation reduction reaction has started occurring at the interface as well as the top center of this phase. The third section shows where the stable pit has formed on the surface, and At that stable pit, we are also observing that vanadium enrichment is seen at the interface, and this vanadium has covered this carbon-rich phase. Concluding all this observation, a schematic diagram was prepared where we saw that this phenomena where the C-rich phase is exposed on the surface and a thin and discontinuous passive film was formed. And we also is observing that there is a galvanic interaction at the interface of phase and matrix. But once it is exposed, we also observe there is an enrichment on the surface. And this enrichment actually provides an additional barrier to enhance the corrosion performance. Also, once this vanadium is enriching and covering the C-rich phase, it also lowers the electrochemical potential difference between the secondary phase and the matrix. Thus, it also provides sufficient time to the alloy for repassivation. That's how the corrosion performance can be enhanced for this material, even though we are having the secondary phase on the surface. Summarizing the work, we have seen that nanocrystalline and improved solid solubility was obtained after the high energy ball milling. Once the heat treatment was conducted, we saw the spherical geometry of precipitate having the size less than 7 nanometer, and that also in the overage condition, which shows the stability of the precipitate. As well as we also saw the enrichment at the oxide metal interface and the galvanic interaction occurring due to the secondary phase. Those are the C-rich phase and the precipitate. The positive outcome from this work is the corrosion performance was preserved even at the peakest condition, even at the precipitation hardening, even though the metrics showed the heterogeneous behavior. As well as we also saw that why this corrosion performance was enhanced, that is because of the synergic effect of the vanadium enrichment acting as a barrier, which actually delayed the oxidation reduction reaction on the surface and provided the sufficient time to the alloy to repassivate. Also, the solubility enhancement in the high energy ball mill alloy, as well as the nanocrystalline structure. All this impacted in increasing the corrosion performance and the preservation of this corrosion behavior of this alloy, even though it was exposed to the high temperature. Thank you.
Theory, my video started. Let's give Gijo a great big hand. That was a really nice talk. Again, he answers most of my questions. Define, Gijo, are you here? Can you define high temperature? Are we talking about like a cooking oven, 350 to 375, or like an oxyacetylene torch at a couple thousand Celsius? Or
actually, the melting point of aluminum is 660 degrees Celsius. So for aluminum, 150 as well as like I went till 250 degrees Celsius. Till there, usually people do the precipitation hardening in this alloy.
Okay. Well, that's what I expected. I didn't think you were going to torch temperatures because that should cause the aluminum to melt. And generally speaking, once you get to about half of the melting point, you start losing strength.
Yes.
You showed a graph that showed the percentage of the vanadium decreased with aging. So this is how much of it is precipitating out versus how much goes to the surface. You showed lots of pretty pictures where you had like X-ray maps that showed vanadium right along the surface and what appeared to be precipitates. Do you know how much is precipitating out versus what's going to the surface? And I have to follow too.
I have not calculated the volume fraction of how much the precipitate is occurring, because there is another complexity coming into picture. That is, some of the vanadium will be in the unalloyed form and some will be in the supersaturated solid solution. So to figure out exactly how much the vanadium has precipitate is difficult. But we can also get a comparative result, like relatively how much it could have come out, and that is still pending.
Okay. Do you have any idea why the vanadium wants to go to the surface? My zeroth order guess would be that there was to be some sort of thermodynamic reason or a reduction in surface tension. Do you have any idea?
So the precipitate was all over the matrix. So when we analyze the corrosion always occurs on the surface of the alloy. So whatever was exposed on the surface, we were interested to know it's how this precipitate or the secondary phase, such as C-rich phase I have shown, how it reacts with the matrix and how galvanically it acts and how much impact it is occurring on the surface.
Where do you see an application for these sorts of alloys?
So this study was conducted for the fundamental understanding. If you see, this is a binary alloy where we cannot use this for the practical use, but we can understand the individual contribution coming from the alloying element. And once we understand that, we can commercialize this. And then practically, if we want to go forward in the particular field, we can use it in the automotive industry specifically.
Okay, well, that's, unless it's really obvious to me, I'm always going to ask about practical applications because that seems like to me a fundamental thing. There is a question from Andy for Jijo. How are the TEM samples prepared, and if FIB is being used, and it looks like it, do you see any gallium decoration of the aluminum grain boundaries?
Yes, that's a good question. Actually, we were like struggling whether actually that was a precipitate or the gallium or the platinum effect. So this TM was prepared through the FIB technique, where the gallium was used to bombard and remove the material. So what I did was I confirmed that the bright spots which I obtained was precipitate by using the line scan in the EDX as well as the SAED pattern.
Marcio has a question.
I'm not a material science guy, but I'd like to know if there are other alloys with the same behavior, or this is just one special case.
Yes, not much has been done about the precipitation hardening in this supersaturated solid solution because SGBM is a non-equilibrium technique. So it is not feasible that precipitation can sustain for a long period of time. So, but there is some literature which have shown that the exact same spherical precipitate have been formed on the matrix due to the supersaturated solid solution.
Are there any other questions? If not, let's give Jijo another big virtual hand.
Thank
Very
you.
Nice talk. Our next presentation is a vendor presentation by Physical Electronics.
Hi, I am Ben Schmidt, a staff scientist at Physical Electronics, and I'd like to give you a quick overview of who we are and some updates to our products. PHI has been a leading manufacturer of surface analysis instrumentation for over 50 years. We offer several products for XPS, Auger, and TOF SIMS analysis, with multiple analytical and sample processing options available depending on your applications. Today we're announcing two new products, the VersaProbe 4 Multi-Technique XPS and the NanoTop 3 Parallel Imaging MSMS, and I'll discuss those in a little more detail shortly. First, I'll talk about the VersaProbe 4, which is the latest generation of PHI's highly successful Multi-Technique XPS system. It has a new look and a variety of new hardware and software features. A new analyzer lens technology provides 2 to 3x improvement in sensitivity over the previous generation, and for customers with our previous VersaProbe 2 and VersaProbe 3 systems, it is possible to upgrade to the new lens for higher performance. With the VersaProbe, an array of excitation sources, ion guns, and sample treatment and transfer options are available to support your material characterization and problem-solving requirements. And a key feature to all the PHI XPS systems is the scanning X-ray microprobe. And one of the things we can do with that is create fast X-ray induced secondary electron images called SXIs. And we can use these SXI images for sample navigation to find areas of interest and have confidence that we're analyzing exactly where we intend to. Here's an example of small area XPS analysis on a particle of activated carbon. The SXI image shows localized bright and dark regions that are about 30 microns diameter. We can click directly on the image where we want to collect the data. XPS surveys were collected from the marked locations with a 9 micron diameter X-ray beam, and we can see there are increased areas of silver concentration in the bright areas of the SXI. So it looks like we do have some heterogeneity on this sample. And normally the SXI has a maximum size of about 1.4 millimeters, but with some new software updates, we can extend the capabilities of the SXI to create large area SXI and chemical maps. Shown here, we have imaged a 5 by 5 millimeter area of a pattern sample. And like on the previous slide, contrast in the SXI can guide us to areas of interest. We can also overlay chemical maps, as shown on the sample on the right, which is a silicon sample with patterned titanium features. So you have the SXI in black and white, titanium is shown in red, and then silicon is shown in blue. We also offer our Quantes system, which is a combined XPS-HAXPS system, or hard X-ray photoelectron spectroscopy. This contains two monochromatic X-ray sources, aluminum K-alpha and chromium K-alpha. Chromium has a photon energy around 5400 eV, so we get about 3x greater depth of analysis. Shown in this example, we have a 25 nanometer SiO2 film on silicon. With aluminum X-rays, we can only detect the top oxide layer. With our chromium X-rays, we can also detect the silicon metal signal from the substrate. And this allows us to analyze buried layers and interfaces without sputtering. Plus, there are some other benefits that were shown here. For some materials that do require sputtering, an advantage of the chromium X-ray source is that the information depth exceeds the depth of damage commonly observed with ion gun profiling. As shown here, we are investigating a buried tin oxide layer. With the aluminum X-ray source, we quickly see chemical reduction of the oxide, so it is difficult to tell whether the reduced state is real or a consequence of ion sputtering. With the chromium X-ray source, we can detect tin at earlier sputter cycles and maintain the spectrum of the original oxide chemistry. Another new product we're announcing is our NanoTOF 3 TOF SIMS Parallel Imaging Tandem MS. With the MS-MS, you can get unambiguous peak identification using a second collision cell and spectrometer. There is also improvement in spatial resolution down to about 50 nanometers with the bismuth LMIG. And when analyzing rough samples, we also have an improved charge neutralization capability using a pulsed dual beam technology. Switching over to OJ, the 710 scanning OJ nanoprobe has additional analytical options available such as EDS, BSC, and EBSD for bulk chemical analysis and crystallographic information. You can also fracture the sample or perform fib cross-sectioning in vacuum, giving you more options for correlative analysis. So thank you for joining today. If you'd like more information or would like to contact us, please visit phi.com, where you can also find links to our YouTube and LinkedIn pages, information on upcoming webinars, tutorials, and more.
Next talk is from, and I'm probably going to brutalize your name, and I apologize in advance, Chaturanga Witharamej, and he is a student at NC State, and his talk is going to be on the investigation of corrosion behavior of in situ consolidated aluminum to atomic percent vanadium alloys.
Hello everyone, my name is Sandamal Vitharamge. Today I'm going to talk about the corrosion behavior in situ consolidated aluminum to vanadium alloy. So here's the outline of the presentation. First of all, I will introduce the background of this work and then objective of this work, then the experimental setup that I have used, and then the results. So under the results, I will mainly focus on the alloy characterization and corrosion behavior of the alloy and the passive film characteristic and the pit morphology. Finally, I will conclude the work with the mechanisms. So here's the background. So when it comes to the aluminium, so aluminium is the third most abundant element on the Earth crust, and it's a lightweight element, and it has excellent corrosion resistance, but the yield strength of pure aluminium is significantly lower. So because of this lower mechanical performance, people tried to develop aluminium alloys by adding different elements to pure aluminium. So there are certain applications like aerospace applications and automobile applications with these aluminium alloys. So aluminium alloys are also lightweights and they have like excellent strength to weight ratio. But the thing is, so the corrosion resistance of aluminium alloys are significantly lower compared to pure aluminium. So because of this limitation with the lower corrosion resistance, people try to develop new aluminium alloys using different techniques. So here's the motivation of this work. This diagram shows the pitting potential as a key parameter of corrosion performance, and the weaker hardness as a key parameter of the mechanical behavior. So here is that conventional aluminum alloys like commercial aluminum alloys are locating left bottom corner on this diagram, which shows lower performance, whereas aluminum alloys that are being developed using a technique called high energy ball milling shows outstanding corrosion and mechanical performance. Among these high energy ball mill aluminum alloys, so there are like several candidates like aluminum nickel, aluminum niobium, aluminum vanadiums. They are showing outstanding corrosion and mechanical performance compared to conventional aluminum alloys. So among these aluminum alloys, so we selected a high energy ball mill aluminum vanadium alloys because there are a few reasons like strength to weight ratio is high, excellent corrosion resistance. These two factors are common for all these candidates, but the thermal stability of the vanadium aluminum system is significantly higher compared to other alloys, and also vanadium has lower molecular weight compared to other transition elements, so which is benefited to have high strength to weight ratio. So because of these reasons, so we selected to investigate aluminum vanadium system further. So even though aluminum vanadium shows an outstanding corrosion behavior, so the mechanisms for this corrosion resistance improvement is not understood. So therefore, our objectives are focused on understanding the corrosion mechanism of aluminum vanadium alloys. To achieve these objectives, so we perform several experiments starting from aluminum and vanadium powders. So we mix aluminum vanadium powder based on our formula. So here's a jar. We added our aluminum and vanadium powder into jar with a stainless steel bowl, and we added process controlling agent to eliminate the cold welding during the ball milling, and then we seal these processes. These processes are done inside the glove box. Once it is sealed, so we place these jars on the ball mill, and we perform the ball mill. So after ball milling, we got pellets which has 1 to 5 millimeter dia. So these pellets were further investigated using SEM, TM, XRD, XPS, and some different kind of electrochemical tests. So moving forward to the result section, here's the microstructural features of the alloy. So we noticed that the formation of iron-rich particle in the microstructure. So these are coming from milling media during the milling. So we use TM to see the characteristics of the alloy. So based on this TM analysis, we noticed that the formation of highly dense secondary phases. So using XRD analysis, we confirm these aluminum-3 vanadium intermetallic phases. And then we did a selective area diffraction pattern to confirm that the formation of solid solution of vanadium in aluminum. And also we calculated the grain size of the alloy. So based on that, we confirmed the formation of nanocrystalline structure of this alloy. So moving forward to the corrosion behavior of this alloy, we use 3 different techniques. First one is potential dynamic polarization. You can see the potential dynamic polarization curves for both pure aluminum and Al2B. So when compared with pure aluminum, so we notice that the pitting potential of Al2B is significantly higher compared to that pure aluminum. And also aluminum 2 vanadium alloy has a very big passive window with a lower corrosion current density. So with that, it is clear that aluminum 2 vanadium alloy has outstanding corrosion performance compared to pure aluminum. So we use electrochemical impedance spectroscopic analysis to understand the corrosion behavior over the immersion time. So based on this EIS analysis, we concluded that localized corrosion resistance improvement and the enhancement of the passive film stability of aluminum to vanadium goes to enhance the corrosion performance of the alloy. So finally, we did Modt-Schottky analysis to understand the semiconductive behavior of the passive film. Based on this analysis, we concluded that the donor density of Al2 vanadium alloy is significantly lower than that of pure aluminum. This shows that the enhanced passive film stability in aluminum to vanadium. So then we characterize with the passive film using XPS sensing. Here you can see the 4 different immersion conditions that we used. So based on these results, we concluded that the presence of both metallic and oxidized vanadium in all the immersion conditions, and also during that immersion time, this oxidation state of vanadium is changing. Besides that, we noticed that the passive film growth over the immersion time. So using SIMS analysis, we did that initial SIMS analysis before the immersion and after immersion. We noticed that before immersion, the presence of vanadium, the presence of enrichment of the vanadium underneath the passive film, whereas during the immersion, so this enrichment shifted to the top surface. So moving forward, so we characterize the passive film using TEM. So you can see the formation of uniform passive layer to form the substrate. Besides that, we notice that the enrichment of vanadium underneath of the film, passive film, which is further supported the observation that we observed from this SIMS analysis. So here's the pit morphology. So we can see that the pit formation, this pit formation is responsible for iron rich. So iron rich particle cause that the pit formation, and we notice that the enrichment of vanadium underneath the pit also, and also it is clear that the deposition of vanadium on iron rich particle also we observed. So based on these observations, I would like to conclude the mechanism of aluminum to vanadium corrosion. So in the microstructure, we can see the iron-rich particles. So those are cathodic to the matrix, and then cathodic reaction will take place on iron-rich particle and initiate the alkalination, which is causing to reduce the stability of the surrounding. And also we can see parallelly that the oxidation of Al3V in this area. So very interestingly, we notice that the enrichment of vanadium underneath the passive film and underneath the film. So the presence of this vanadium caused to oxidize during the immersion, and this oxidized vanadium is deposited on iron-rich particle, which goes to inhibit the cathodic activities during the corrosion process. So those are the main mechanisms that we observed in this system. So with these observations, I would like to conclude my presentation. Thank you for your attention.
That was an awesome talk. Let's give a big hand. So I have a couple of questions. You talk about the introduction of iron from the milling balls. Is a potential solution to that to use milling balls that are made out of, say, some sort of hardened vanadium or a hardened vanadium rich iron, so that you get mostly vanadium out of that? And how much does that actually hurt you?
So basically this milling media made out of stainless steel. So that's the main reason that we are like seeing that iron in our microstructure. If we can, actually we never thought of replacing the milling media. So if we can have something like from out of vanadium, so that detrimental effect in the microstructure may be reduced. Yeah.
So, because I can imagine using, you showed like a chart that showed vanadium and molybdenum and nickel and niobium. I'm not as familiar with niobium, but I know that you can make nickel really hard. I'm not sure about moly. Usually, I'm not sure if it's used for hardening or not, but it seems like you could make the milling balls out of whatever material you were using. And another quick question is, what would be the relative cost difference versus using vanadium or moly or nickel or niobium to make these these sorts of alloys?
Yeah, vanadium actually pretty expensive, but the thing is that we are like adding 2%, which is like if you take like 25 grams of that, maybe like it would be like less than 1 gram of vanadium powder. So that's why we are like thinking that the overall cost of the alloy would be it's not going up. So compared to other elements, actually we didn't do that cost analysis for others. Basically we focused on that the enhancement of the corrosion properties of these binary alloys.
Well, I was curious, so I looked it up. Nickel, believe it or not, is the cheapest at about $4 a pound, and the other ones are all about $20 a pound. Go figure. So another question that popped into my mind was when I'm looking up costs, it talks about high purity vanadium versus commercial vanadium, and commercial vanadium is 95%. They didn't say what the other 5% would be. What is the issue with having a few percent of impurities in your starting materials? How bad is that? Do you think that will hurt you?
Yeah, I mean, if you have impurity on that initial like powders, so that will be incorporated in the microstructure. For an example, I would say we added process controlling agent during the milling to avoid the cold welding. So that will cause to incorporate carbon inside the microstructure. So if you have like carbon, or if it is like incorporating any other element, that would be detrimental because of the galvanic interaction between the alloy and that secondary phase. So the effect of this secondary phase would be different depending on the size and the electrochemical nature of these secondary phases, things like that. So anyway, so as a summary, I would say if you have like secondary phases, so that could be like detrimental to the corrosion of the alloy.
So do you think this is this something that might be scalable to commercial applications?
Yeah, of course. I mean, this composition we just did, and then you already saw that the in situ consolidated small pellets. From these pellets, we don't have potential application. We just focus to understand what's the corrosion mechanisms. But when it's come to the application of these alloys, so we are like currently focusing on doing cold spray using this alloy powder. So something like if you have like aircraft which has like kind of corrosion, we can try to do technique like we can use technique like cold spray to minimize the corrosion of the alloys.
Thank you very much. Does anybody else have a question? Chris has got a question.
Yeah, so excellent talk. I have hopefully a quick and easy question. So I noticed on your corrosion studies, when you were looking, you found the pitting around the iron.
Yeah.
First question is the iron just from the ball milling? Is that where you're getting the iron from in your sample?
Yeah, that's what we believe, because we have stainless steel. From there, we from our studies we concluded this iron is coming from this milling area.
Makes sense, yeah. So I mean, there's various ceramic balls you can also switch to. I don't know if that's compatible with your system, but for your corrosion studies, did you only see effects around the iron nanoparticles? Did you see anything else caused by the sodium chloride environment?
Basically, we do have some other phases like in AL3V intermetallic phases. They are in like nanoscale. Let's say the average size of these precipitates would be 10 nanometer or something like that. So it's like kind of challenging to understand the exact effect from these things. The reason is that the nanoscale precipitates. So we should have something like high resolution technique to understand the corrosion mechanism of corrosion effect of these intermetallic phases. So
Yeah,
iron is like, they are like in microns level, few micron size. So that's why we can easily check the corrosion effect of these secondary phases like iron, because they are size of that.
It's excellent work. It's not easy. Anything corrosion is difficult. So.
Yeah. Yeah.
Well, let's all give, and I'm probably going to brutalize your name again, Chaturanga. Am I pronouncing that right? Or are you like Sandomal? No wonder. I'm looking. They're giving me a piece of paper that's got one name on it. I know him as Sandomal.
So I used to use my second.
This is always the danger when you get a piece of paper that's got stuff on it that may not necessarily match what people do. And I encounter this all the time because I host things like this on a routine basis. So my total bad, Sandomal, I didn't recognize. I thought, I know this guy, but I don't recognize that first name.
So that's my first name, Betty.
Yep. So thank you once again, Sandomal. We are going to have a couple. We're going to have a couple of posters coming up, but I do want to remind you that I just shared the link again that has a link to all the posters so that you can look at the posters at your leisure. And it's also got the survey. We would like for everybody to fill out an evaluation. We're going to have a random drawing and give away some money based on people who fill out the evaluation form. So please go ahead and do that.
Good morning, my name is Kendall Dawkins, and today I'll be presenting my work on a gallium arsenide and timonide-based photodetector with silver nanowires as transparent electrodes. In this work, we showed the fabrication and the characterization of a fully nanowire-based near-infrared photodetector. The one-dimensional nanowire photodetectors, when compared to their bulk counterparts, can yield higher light sensitivity, and this can be due to their large surface dividing ratios and their quantum size confinement. Also, due to the presence of surface trap states in the nanowires, this can actually prolong the photocarrier lifetime. For our work, the photodetector consists of a transparent top electrode of silver nanowires, with the active region being gallium arsenide and timonide nanowires, with a silver epoxy used as a back contact on the nanowire device. As you can see, and what I will show you later, that the introduction of a silver nanowire as the top contact layer using a simplified method, simplified drop casting method, can actually lead to a stronger suppression of the dark current, which can yield higher device figure merits. As far as our spiral design and what we did, gallium arsenide and timonide nanowires were grown on silicon substrates, which were first cleaned using a piranha and hydrofluoric acid solution to get rid of any impurities or any organics that were seen that could be possibly on the silicon substrate. The gallium arsenide and timonide nanowires was grown using a gallium-assisted vapor liquid solid growth mechanism, using a solid source MBE. And we was able to vary the fluxes, the arsenic flux and the timonide flux, to grow our nanowires at 620 degrees Celsius. After the nanowires were grown, the self-catalyzed nanowires were dipped in a hydrochloric acid solution for about 30 seconds to remove any surface oxides, and were blown dry using nitrogen gas. Then to create the entire device, the ensemble nanowires were spin coated. SU8 2002 series polymer solution was spin coated on the nanowires, and then they were etched. The SU8 was etched using DRIE system to expose the tips, as you can see in figure 3. This shows a nice picture of what the device looks like after the SU8 has been etched away to expose the tips. And then table 1 and table 2 shows our parameters for setting up these spin coating steps, and the DRE parameters as well. Far as the silver, the introduction of the silver nanowires as a transparent electrode, using a silver nanowires were purchased from ACS Chemicals, and they were suspended in IPA solution. The silver nanowires were then deposited on top of the nanowire tips, and then were partially melted at 200 degrees C to form a consistent mesh, which reduces the sheet resistance as well, and also nanowire to nanowire resistance. In our first experiments, we used a spin coating method that was described in a lot of papers and in the literature. But what we found was, when it comes to our devices, as you can see in figure 6, once we spin coated the devices, it will run over into the silicon, where we was trying to make our back contacts. And I don't know if you can see, but in figure 5, there is a sight line that leads outside this yellow ring, right here. And this is what we were seeing in our devices. So this can actually cause shortage in our devices. And beforehand, we also did the transmitted studies, which were still on par with what we saw in the literature, but this shorting was a major problem for us. So then we saw that we can possibly use a drop casting method. It's a simple method that was able to coat the silver nanowires on top of the nanowire tips, and we were actually was able to show similar good transparency in about the 90% transparency, but we was also able to get our sheet resistance down with the introduction of different more layers or coats, as you can say, of silver nanowires. And far as our device characteristics, our IV characteristics, we show a IV of gallium arsenide antimonide PIN gallium arsenide antimonide nanowires using gold contacts, which were deposited using physical vapor deposition, and then using our method of just using silver nanowires as a simple in a simple deposition method, and just heating the nanowires to create that mesh. And as you can see, when compared to each other in Figure 9 and Figure 10, the dark current in Figure 10 is substantially less than the dark current in Figure 9. As you can see here, about an order about 8 magnitudes, and we was really excited about this result because this dark current can actually lead to deter device characteristics such as responsivity and the detectivity as well. So this is some of our preliminary results, and thus we're using this method for all our devices, and to see how can we further optimize our figure merits when we are looking for increased photo gain and photo current for our devices. And as far as inclusion, as you can see, there is an enhanced photo current in this case when compared against the two, about 2 magnitudes. And then, far as our conclusions, we are able to say, hey, this seems like a good and inexpensive method to not only decrease the dark current and possibly increase our figure merits, but this can also be a inexpensive way to create gallium arsenide and antimonide based nanowires when we use the silver nanowire solution instead of the gold. So I would like to thank my group members and my advisor, Dr. Iyer, and also my group member, Priyanka. And then we also like to acknowledge the Air Force Office of Scientific Research grant as well. Thank you.
Hello, my name is Saeed from the Material Science and Engineering Department at North Carolina State University, and I'll be discussing decoupling proton and cation contributions to capacitive charge storage in bernesite and aqueous electrolytes. Bernesite is a layered transition metal oxide with an interlayer spacing large enough to accommodate various species, such as water and different cations. Because it's relatively affordable, non-toxic, and exhibits a high specific capacitance, it's very attractive material for high-power electrochemistry energy storage and desalination applications. Previous work on the capacitive response observed in bernesite during cation insertion is attributed to the hydrated interlayer, which mitigates the structural transformations that occur in bernesite. While much of the work previously has been performed on the cation contributions, the role of protons in this capacitive behavior have not been closely examined. In this study, we'll use electrochemical characterization with buffered electrolytes, along with electrochemical quartz crystal microbalance measurements and atomic scale simulations to show the presence of proton-coupled electron transfer reactions, which initially increase the capacity but lead to severe film degradation and poor cyclic stability in bernesite. Bernesite is comprised of layers of edge-sharing MnO6 octahedra with an interlayer containing water molecules and cations. In this case, the cations are potassium ions. The morphology we observe can best be described as nanostructured and tissue-like when we synthesize this using electrodeposition. So in this study, bernocite thin films were prepared via chronoamperometry electrodeposition onto gold-coated glass substrates. Electrochemical quartz crystal microbalance, or EQCM measurements, was one method we used to investigate the role of protons, and this allowed us to probe the nature of the intercalating species within the bernocite interlayer. Another method we used was electrochemical techniques, specifically cyclovoltammetry, where bernocite films were cycled in a potassium sulfate electrolyte with the addition of different concentrations of buffer within the electrolyte. And the idea here is that the buffer provides additional protons capable of being involved in the charge storage process while not changing the pH of the overall system. And this will allow us to more easily deconvolute the proton contributions from the cation contributions in this overall capacitive process. So cyclic voltammetry was performed in potassium sulfate with no buffer, 20 millimolar buffer, 50 millimolar, and finally 100 millimolar, with the response showing an increase in specific current and capacity, as well as the onset of additional redox peaks at low potentials as buffer concentration increases. These peaks are hypothesized to be the result of p-set reactions from the additional protons provided by the buffer. To analyze these CVs further, we deconvoluted the Faradaic peaks in each of the CVs from the total CV and found that these peaks increase with increasing buffer concentration. In addition, their contribution to the overall capacity also increases with higher buffer concentrations. Overall, the rectangular potential independent current is still the main contributor to the capacity in all of the samples. We also analyzed the effect of buffered electrolytes on the long-term cycling stability of bernocite and found that although the initial capacity is higher in buffered electrolytes, the unbuffered system has much better cycling stability. With the addition of buffer, we see a severe degradation both in the capacity and in the film itself, as seen by the SEM and optical images. EQCM was performed to further understand the charge storage and degradation mechanisms by probing the mass changes of the electrode. We see that all electrodes show mass loss during oxidation and a gain during reduction. However, the addition of buffer leads to a significant hysteresis, indicating low reversibility. The mass change is also the greatest in the unbuffered electrolyte, suggesting that it exhibits the most potassium ion intercalation. By calculating the mass to charge ratios, we can see that there is much less participation of the potassium ions and more participation of the protons and water in the buffered electrolytes when compared to unbuffered electrolytes. Lastly, molecular dynamic simulations were used to provide atomistic insights into the role of protons and show that proton intercalation can lead to the formation of oxygen vacancies, suggesting that dissolution is an energetically accessible process via electrochemical cycling. Overall, the study demonstrates that cations are the dominant contributor of capacitive charge storage in bernocite, while protons contribute slightly via p-set reactions, which ultimately lead to degradation and poor cycling stability of the film.
Thank you all for attending this morning. That was a poster by Saeed Saeed. It was a nice one. We're apparently having some troubles with the link. I'm trying to copy the view link to send to everybody, but apparently that's not working. During the break, I'm going to get together with some people and try and figure out what to do about that, and we'll have a solution before the afternoon session starts. With that, we're going to conclude the morning session. The afternoon sessions should start right at 1 o'clock. We look forward to everyone coming back and seeing us here at 1. So with that, we'll take a break and we'll see you all later. Good afternoon, ladies and gentlemen, and welcome to the afternoon session of the 2021 Carolina Science Symposium. We're going to start off this afternoon with a live talk from Nicole Cates and Lauren Miklo, and their talk is on industrial scale nanofabrication, and they are from Smart Materials Solutions.
All right. Thanks, Chuck, for the introduction. As Chuck said, I'm Nicole Cates. This is Lauren Miklo. The two of us make up 2/3 of the company at Smart Material Solutions. So the third person we work with is Stephen First, who's just down the hall. And we're going to be talking about industrial scale nanofabrication. So nanofabrication is pretty well established in that people can make and demonstrate that nanopatterns can improve a ton of things. And we'll talk about some of those. But what we want to do is see what you can do when you can scale that up to the industrial scale. Instead of making, millimeters squared of a nanopattern, what happens when you can make square kilometers? So we're going to be talking about our process. A lot of this project, the work we're going to be talking about is funded by the US Army, NASA, and NSF. And you'll see our contact information here, but we'll provide it again at the end in case you want to get up with us. So before we talk about scalable nanopatterning, I wanted to step back and talk about scalable patterning, just at the large scale. And one thing that Lauren and I have in common is that we both do a little bit of pottery on the side. And when you're molding ceramics, you have a lot of ways to pattern it. You can pattern it at very low speeds, doing intricate hand carving, like you can see here. There are higher speed processes, like using a stamp and stamping a pattern, moving it over, repeating in a so-called step and repeat process. Or you can do very high speed patterning, where you use a roller mold and you can very quickly roll out a pattern onto large areas. So with these higher speed processes, you can achieve very large area patterning. And I think one great example is the Alhambra in Granada, Spain. So I spent 3 years living in Spain, and I was constantly struck by the beautiful, intricate Moorish architecture like you see here. But what a lot of people don't realize is that this architecture, although some of it was done by hand, a lot of it used stamps and roller molds to mold plaster. And that's how you're able to make entire buildings and entire complexes that look something like this. So you can clearly do some amazing things if you can scale up your patterning. So the question then becomes, what can we do if we do the same thing with nano patterning? There's a ton of applications that can take nano patterns, and when you make them over very large areas, you can do a lot with them. These are just a few of the examples. You can make display films that make your mobile phone or your TV brighter and more efficient, less likely to have glare from the sun, things like that. You can improve optics for augmented and virtual reality. You can make metamaterials that manipulate light. There's plenty of applications in clean energy or in surfaces that manipulate the way they interact with their environment. For example, dust mitigating films are a big thing for lunar applications. And there's also advanced wetting films, like films that can be anti-fogging or self-cleaning. So we're going to talk about a couple of these later on in this talk and what we're doing to solve some of these problems.
So that brings us to our scalable nano patterning process, nanocoining. Similar to clay fabrication, it begins with a low speed step where you're doing a patterning of a stamped tool. In this case, it's a diamond die that's being milled using a focused ion beam. That die can then be used to stamp in a sort of very fast step and repeat process where you're indenting a metal mold at 50,000 times a second to replicate this pattern 500 times faster than electron beam lithography could create this. And you're doing this into the outside of a cylindrical mold, so you can transfer that via a high-speed process of roll-to-roll nano patterning. The diamond die can take a variety of form factors, including nano features and micro features, or a combination of those in a hierarchical pattern. And we could even make an arbitrary feature that's our logo. By mounting the diamond die to an ultrasonic actuator that's operating at 55 kilohertz, we can indent a mold 55,000 times a second. And this actuator is operating in an elliptical path. And at the peak of that path, it's making contact with the part and plastically deforming it, creating that inverse pattern. And by doing this in a spiral pattern, we're able to rapidly pattern the outside of the drum. And if we carefully control the feed speeds, we can tile our indents. And what this means is that the features from our first indent are aligned with the features in our second indent. And by controlling those feeds, we're also able to move up one feature height and tile our first indent's features to the features in the 24,000th indent. Doing this allows us to pattern a few different form factors. We can pattern a cylindrical drum that's self-supporting, or we could do it into a sleeve that goes onto an air mandrel and can be easily moved from one system to another. And we can also take those sleeves and use them as flat shims to do more batch processes as opposed to roll processes. And nanocoining gives us a few advantages, namely that it's high speed and seamless for those drum molds. We also get 3D feature shape control with the fib milling of the diamond die, and it's chemical free, so there aren't any etching processes because it's a mechanical deformation creating the pattern. So we aren't removing material, but we are moving the material. This does translate to a few challenges that we faced. If we don't apply enough force when we're indenting, you can get an incomplete indent. And this means that we aren't getting one-to-one replication of the feature from the diamond die into the metal mold. We also face roll alignment challenges. If we don't perfectly align the features in the die relative to the crossfeed direction, we can get a weird tiling error. If the diamond die, if the feature breaks off, then that void is replicated in every subsequent indent. And you can also get a speed mismatch. If the diamond die is moving faster or slower than the cylindrical mold, you're scraping along the part and creating a smearing effect. But we have been able to overcome a lot of these challenges and create indents like the one that you see here. These are 3 micrometer pitched features, and it's very difficult to tell where one indent ends and the next indent begins. But when we scale down, we run into a few challenges due to hardware limitations. We don't have enough resolution on our spindle to register these 300 nanometer features. So our resolution isn't small enough to line up that first indent to that 24,000th indent anymore. But the good news is that we've overcome some of these previous challenges well enough to be able to find new challenges to try to overcome.
So once we have a nano pattern mold created with this indenting process, we've now taken it and used it on roll-to-roll processing setups. To do this, we take a smooth film, and it's a thermoplastic film that can be deformed under heat and pressure. So we bring this film into contact with the mold, the nano-patterned mold, and we apply heat and pressure. And then when we remove the film, we're left with the inverse pattern on the polymer film. So this is a great method to take our process and scale it up and make it even faster. So here's an example of a mold of ours on a setup at microcontinuum. And you can see it rolling off our polymer film here. This process was used recently, actually just a couple weeks ago, to pattern over 500 feet of film at microcontinuum. So we're pretty excited to really demonstrate the scalability of this process. We've also done some roll-to-roll nano patterning with a UV process. This process is very similar to the last process, except that we apply a smooth film that's coated with a UV curable polymer precursor. We bring the material in contact with the mold. We apply a UV light that cures the polymer and therefore solidifies it. And then when we remove the film, we're left with a nano patterned polymer film. And this is an example of about 60 feet of polymer film that we patterned using this method at UMass Amherst. This is an example, this is an SEM image of this patterned film. And although we don't show the results here, one of the big projects we did was to compare the feature shape in the final polymer film with the feature shape in the metal mold and the diamond die to understand how the shape changed for each step of the process. So using this, we can create films for a variety of applications, one of which is advanced optical films. And on the left here, you see one example. These are anti-reflective moth-eye films. They have features, pillars, or holes on a periodicity of about 200 to 300 nanometers. And on the top, you see a strip that has been nano-patterned, and on the bottom, you see a smooth strip. And the result is these nano features enable a reduction of the Fresnel reflection. And you can see that the bottom part of the film has a substantial reflective, substantial reflectance, whereas the top has a much reduced reflection. We can also make optical films that are microlens arrays or gratings, and these usually involve periodicities of about 500 nanometers to several microns. And you can see the diffractive effect in this microlens array film. Another project we've been working on is plasmonic metamaterials. Specifically, we've been working on a metal dielectric metal stack where the top metal film is a metal mesh layer with, it's a patterned metal film. And this can be used for absorbers that are very strong, have like very strong absorption peaks that are tunable based on the dimensions of the structure. So taking our drum mold and processing metal involves a couple of steps, depositing many layers, as well as some etching steps. But we have been able to show that we can create large area plasmonic metamaterials using this structure, this process. And on the top, you see an example of our patterned metal film, and on the bottom, you see a cross section of the device. Here you see a photo of one of the devices we've done. It's about 6 inches by 6 inches. We're working on scaling this up to full roll-to-roll production with the current project we have with the Army. And another thing we're pretty excited about is with these structures, we've used FTIR to measure the IR absorption. And we see that the simulated peak positions shown here with stars line up very well with the observed peak positions. You do see 2 extra peaks in the absorption. That is due to absorption of our dielectrics, so we're not concerned about that. And we also see that we can tune the position of those peaks by tuning the thickness of the dielectric cavity. So we're pretty excited to be able to show strong and tunable absorption with these metamaterials.
The next application area is dust mitigating surfaces. This is part of a project that we're working on with the University of Texas at Austin for NASA, focused on lunar dust diffusion. A main factor for focusing on lunar dust is that it's very abrasive and can damage electronic equipment. It can cover solar cells, and it can also create a haze in the cabin when it's tracked in with the astronauts. So by focusing on creating a pattern that can mitigate dust, we're able to lightly, I guess without adding much payload, reduce the dust diffusion of surfaces. And this is a smooth film on the left versus a pattern film on the right. And the factor that contributes to this effect is the reduced contact area. On the smooth side, the dust lays flat on the film, and there's a high contact area between the two, and therefore it takes a lot of energy to remove the dust. By applying a pattern, we're able to reduce the contact area and therefore the adhesion forces. And we can minimize this by creating very sharp features where there's a drastically reduced contact area between the film and the dust. So in summary, we're using these nano-coined seamless molds for roll-to-roll nano patterning. We can use these in a variety of application areas, including advanced optical films, plasmonic metamaterials, and dust mitigating surfaces. So thank you.
Yeah, thanks. We'd be happy to answer any questions if there are some.
Okay, so I should have asked for a drum roll before we started. My bad.
I've never heard that joke, but I like it.
Let's give them a big hand. So I have some quick questions. How bad does misalignment, you showed, it's hard for me to imagine how you're going to get everything exactly perfect. And you showed situations where you had patterns that had some errors in them and some that weren't perfectly aligned. And how much does that really hurt you when you're trying to do dust mitigation or wetting or reducing reflection? I mean, does that really make that much difference if one of them's off by just a little bit?
It can, less so in the sort of dust mitigating applications or the wetting applications, but your eye is really good at picking out those minor differences, even if you can't see it in a microscope maybe. So they kind of add up. If you're looking at an anti-reflective film, that small roll alignment can really contribute to a reduced performance. Yeah.
And that leads to another question, which is how regular are your patterns on a really long scale? So, I mean, we see microscope pictures that are small scale. How good is it as the scale gets up? Because I know that there are often issues when you scale things up from a stamp to a roll to a whole rolled film.
Well, in terms of feature to feature position, it's very good. We have very good large scale reproducibility. We've, for example, looked at the beginning and end of about a 60-foot print of roll to roll imprinted polymer, and it looks pretty much the same beginning to end, or left side to right side. But we have had people ask, well, can you line up a pixel with a feature over the size of the TV? And no, that would be very, very difficult.
Does anybody else have any questions?
Yeah, hey, Chuck, I got a question.
Actually, Roberto's got one.
Yeah, so how great presentation. I loved it. It was really cool to see all the stuff that you're doing on the fib. One thing, what's the lifetime that you're getting on your dyes?
You want to answer that?
It depends on how large the features are. Some of the 300 nanometer features, if they're very tall and skinny and fragile, it could be in one mold, we lose like 5 or 6 features, but that's enough to where you see that error every time. And kind of once you start to lose features, then you're kind of reducing the strength of the whole die, and then they all kind of start to domino. But for the larger, like 1 micrometer features, we have dies that we've indented many 6-inch wide molds, and the features are still perfectly intact. So it really depends on the feature size.
Okay, and are you getting, do you have any issues with pickup?
We do. Once again, it kind of scales. So those smaller features, they kind of get clogged more easily, whereas the wider features, you have a bigger gap in between the features. But we have worked on methods of kind of mitigating that are kind of proprietary.
Okay, thanks. That's it for me.
Chris?
Yeah, I got a couple questions. So kind of related to Roberto's question, I know you're using diamond for obvious reasons. Is it possible for some of your applications to use other materials that are less brittle than single crystal diamond?
Yes, and in fact, we've explored a couple of things with, I would say, not too much success, but we're definitely open to ideas. Really, the reason we use diamond is because it's pretty tough, but always open to new ideas.
Yeah, it's a cool area. So another question is, can you guys do anything? Can you pattern glass? Have you explored patterning glass?
Can we say this?
I don't know.
I would take that as a
I'll
yes.
say we can accidentally pattern glass, but we've not intentionally done it.
I would imagine Corning would love to talk to you guys about some things. And I guess my last question is, this may make no sense, but is it possible when you're doing the roll to roll, can you shift your patterns by nanometers, tens of nanometers to make kind of barcodes or other kind of complicated, nano QR structures or things of that sort?
So I'm going to let her answer this, but I will quickly say that we can change exactly what we're indenting on the diamond, but we're kind of limited to, say, maximum 20 microns by 20 microns area. Beyond that, you have to do really creative things to indent.
Yeah, if you change the speeds, we're kind of limited to a constant speed, but I guess if we put in a lot of effort, we could make a like variable speed indenting. It would just require a decent amount of development.
Yeah, they have done things like where they purposely tile the features halfway between the previously indented
That's what you
features.
see.
That's actually, yeah, what
the
you see
background.
here.
Oh, cool. Yeah.
So it's one die that's just been interwoven. So you can kind of change the offset that way, but you're still kind of limited to fixed values.
Yeah.
Yeah. This fascinating stuff. It's really excellent talk and awesome research. So thank you guys.
Thanks.
Does anyone else have a question? If not, let's give Lauren and Nicole another big hand. And now it is time for a vendor presentation from Smart Materials Solutions. So I think we're going to get to see a summary of what we just saw.
Yes.
Smart Material Solutions, Inc. is a startup in Raleigh, North Carolina with expertise in precision manufacturing, nanofabrication, metamaterials, and clean energy. SMS is backed by the National Science Foundation, the U.S. Army, and NASA to develop nanocoining, a rapid nanopatterning process to create seamless cylindrical molds for roll-to-roll nanoimprint lithography. As part of an NSF grant, SMS collaborated with the Center for Hierarchical Manufacturing at the University of Massachusetts Amherst to replicate a nanocoin drum into more than 60 linear feet of nanopatterned polymer film. SMS has partnered with Microcontinuum to produce anti-reflective films via roll-to-roll processes as part of an ongoing Army SBIR grant. Work is also being performed with the University of Delaware and Microcontinuum on an Army SBIR for highly scalable mastering and roll-to-roll processing of tuned spectral absorbers. The molds can be created in a variety of form factors, including seamless sleeves and seamless drums for roll-to-roll nil, flexible shims for batch processing, and small cylinders for test patterns.
All righty, our next talk is going to be from Venkata Vukam. She is a student here at North Carolina State University, and her talk is on enhanced corrosion performance of selectively laser melted 316 stainless steel via feedstock modification.
Good morning, everyone. My name is Venkata. Today, I'm going to present a topic called Enhanced Corrosion Performance of Selectively Laser 316 Stainless Steel Produced by Feedstock Modification. So additive manufacturing is an emerging technology that builds 3D components layer upon layer. In our research, we are using selective laser melting, one of the additive manufacturing techniques, which also builds components layer upon layer as shown in the image below. Additive manufacturing has several advantages, like it's a single-step process which can build complex designs, and it has design freedom, and we can only print on demand from macro to micro size components with minimal waste, and it's a very cost-effective process. Owing to these advantages, additive manufacturing is excelling in several industries, which includes medical, motorcycle, motor vehicle, aerospace, academics, architecture, etc. Some of the images shown here are the applications of additive manufacturing components in health industry and in aerospace industry, etc. Apart from advantages, there are also some limitations in additive manufacturing components. For example, inconsistent properties. Component of selectively laser melted 316 stainless steel was reported to have superior corrosion performance than raw 316 stainless steel, was reported by some authors in literature, whereas other authors have reported a degraded corrosion performance of SLM316L compared to raw 316L. This inconsistency could be due to porosity, as shown in the images here. These are the defects like porosity, gaps, voids, keyhole pores, lack of fusion pores, etc. And also it could be due to microstructural heterogeneities. To overcome the limitation of inconsistent properties and produce a component with high density with minimal or eliminated manufacturing defects, one need to optimize the manufacturing parameters, but optimizing parameters according to the shape and size of the component, every shape and size of the component will end up doing an ample amount of work. So instead, suitable post-processing treatments are performed in AM components. However, post-processing techniques are expensive and also time-consuming. So to overcome all these limitations, a strategy was implemented in our research also, that is modification of feedstock powders. So in our research, the starting powders are 316 stainless steel, that is the focused alloy, and chromium nitride was the additive that is chosen to modify the feedstock powders. So these powders were sent to high energy ball milling and ball milled for a certain period of time and made sure that the additive has been deposited on the surface of the powder particles. And then these powders were sent to selective laser melting, where we get a solid component printed. So the feedstock powder characterization was performed using SEM, scanning electron microscopy, where the modified feedstock powder showed deposited chromium nitride particles on the surface of the 316L stainless steel powders as confirmed from SEM EDS. Now, the selectively laser mental components with and without chromium nitride had been tested, corrosion tested using cyclic potentiodynamic polarization, which showed significantly improved corrosion performance with chromium nitride addition in terms of higher pitting potential and faster repassivation potentials, and also with minimal current densities. These tests were performed in 0.6 molar NaCl solutions. In order to confirm if the consistent properties are consistent throughout the bulk, the corrosion testing has been performed on top and bottom side of the specimen as shown in this image, and it is observed to be consistent throughout the bulk. So after the corrosion testing, the post-corrosion characterization was performed after PDP and later SEM. The later SEM showed that SLM316L without chromium nitride addition showed aggressive corroded pit, whereas with chromium nitride addition, there is no corrosion that is observed. However, there are minimal crevice corrosion that is seen, and that is shown in this image here. Also, the post-corrosion characterization was performed using potentiostatic polarization in both the specimen 100 millivolts below the breakdown potential, which revealed that the peaks of the increase in the current, peaks of increase in the current indicates formation of metastable pits, and these metastable pits in SLM316L were also observed in SEM as shown in the images below. Whereas with chromium nitride addition, there were no peaks observed indicating no metastable pits, and the later SEM did not show any signs of corrosion. So from this, it can be confirmed that with chromium nitride addition, there is significant improvement in corrosion resistance. But now the question is why the corrosion resistance has been improved with chromium nitride addition. That could be because of several factors like modified passive film characteristics or microstructural differences or grain refinement or any other microstructural refinement that is coming because of chromium nitride addition, or the influence of chromium or nitrogen coming from CR and chromium nitride addition. So starting with passive film characteristics, authors have performed XPS and SIMS on both the specimen, a passive film of both the specimen after immersing in 0.6 molar NaCl for 24 hours. And it was found that there is no obvious difference between the passive films of both the specimen irrespective of chromium nitride addition. So ruling that out, moving to microstructural differences or refinement, the authors have started with XRT, where the phases were identified on different regions of the specimen as shown in the top, bottom, on as printed areas. And it is found that there is only austenitic single phase found throughout the specimens in all the regions. The SEM image showed that with chromium nitride addition, there is significant improvement in the grain refinement. The different grades of shade represent different grains, and it can be seen that grain refinement has been significant with chromium nitride addition compared to without. And those samples were etched, and a cross-section of the samples were observed, which reveals the melt pool structure of both the specimens. And the analysis revealed that there is no difference in the melt pool dimensions. They were pretty similar with addition of chromium nitride. And the further etching showed the popularly known cellular structure in as both the SLM printed specimen. These cellular structures can be either viewed as equiaxed cells or columnar cells, and in both the specimens, both the forms of cells has been observed. Apart from that, when the accelerating voltage during SEM was reduced to 3 kV, a new cellular structure inside each cell was observed, which is called as subcells. As shown in this image, inside each cell of equiaxed or columnar cell, there are subcells that are observed. Moving into details of subcells, both the specimen exhibited subcells in both forms of cellular cells. And with chromium nitrate addition, it is observed that there is significant refinement in subcells. That is, the average subcell size is 0.05 to 0.15 micrometer square in SLM316L, whereas with chromium nitrate addition, it improved to or refined to less than 0.005 micrometer square. Comparing these cellular structures with the post-corrosion characteristics we observed before, a closer magnification of the PET formed in SLM316L reveals the same cellular structure where the cells were aggressively corroded and the cell boundaries were intact. Whereas with chromium nitrate addition, there is a reverse phenomena that was observed where the cell boundaries were intensively corroded and cells were remained intact. So further investigation was moved to TEM. From TEM, it is observed that the cellular boundaries were nothing but the dense entangled dislocations where a series of nano inclusions were observed. However, nano inclusions were not only observed at the cellular boundaries, but also observed inside the cells. These images shows the columnar cells in both the specimen of SLM316 and SLM316 with chromium nitrate addition. And it is also observed the same subcells that are observed in SEM were also observed in TEM, similar to it. And it was also confirmed that there is definite refinement of subcells with chromium nitrate addition compared to SLM316L. So TEM EDS has been performed on both the specimen in large areas, which showed that in the same regions where there is dense entangled dislocations, there is also solute segregation of chromium, nickel, moly, and sulfur in both the specimen, and also there is depletion of Fe. However, the nano inclusions composition that was identified was different for both the specimens. In SLM316L, there are sulfur-rich inclusions, that is, the composition of nano inclusions is silicon, oxygen, manganese, and sulfur-rich, calling it sulfur-rich inclusions. Whereas with chromium nitrate addition, there were only inclusions of silicon, oxygen, manganese, and also some inclusions were rich in chromium. So the difference in these chemical composition of the nano inclusions, that is the presence of sulfur-rich nano inclusions in SLM316L, could be acting as a potential sites for corrosion initiation. Talking about that in detail, talking about the commercial 316L, that is broad 316L, the presence of MNS inclusions and the depletion of 200 to 500 nanometer of chromium depletion around these MNS inclusions is the regions where corrosion initiation takes place. Whereas in SLM316L, due to very high solidification rates, the density and size of MNS inclusions are refined or may be completely absent. Therefore, the next possible sulfur-rich inclusions could be the reasons or the initiation sites for corrosion. In our research, we have identified that manganese, silicon, and sulfur-rich oxide inclusions has been acting as the corrosion initiation sites. Moving to influence of chromium or nitrogen, literature shows that with increase in nitrogen percentage, there is significant improvement in the corrosion performance, even up to 0.15% of nitrogen. Authors have also confirmed the participation of nitrogen in the form of NH4+ using XPS in the specimen that has nitrogen greater than 0.2%. However, in our research, we did not identify any peaks of nitrogen containing compounds or ions, because our nitrogen percentage is still less than 0.2, that is, it is about 0.165, whereas in SLM316L, it is 0.082. This indicates that there may be participation of nitrogen in forming a better compact passive film, but it wasn't identified through XPS. In summary, it can be said that with the addition of chromium nitrate, there is significant refinement in corrosion performance. and it could be attributed to refinement in grain size or subcell size. And also, more importantly, the elimination of sulfur-rich nano-inclusions that were observed only in SLM316L. And also, the improvement in corrosion performance was attributed to higher percentage of nitrogen in SLM316L with chromium nitrate addition. We would like to thank everyone for supporting and funding this project and for the research. Thank you very much for listening. Thank you.
All right, let's give a big hand to Venkata. So one of the questions that pops into my mind is that, so the nano inclusions look really dark. Actually, you answered that question as I came up with it. So where do you think the silicon, manganese, and oxygen are coming from? That is, how pure is your powder? Where can these impurities be coming from?
Generally 316 stainless steel will have a lot of elements which includes nickel, moly, chromium, etc. And oxygen could be coming because we were milling in argon atmosphere, but definitely there will be some contamination. So I think oxygen is coming from there.
Okay. So how pure is your starting material? How pure is your powder?
Like, are you asking with respect to oxygen?
No. With just you've got a powder that's 316L. It doesn't have a whole lot of extra impurities in it. Like, for example, I know that you don't want aluminum in your 316 stainless.
Yeah, we don't want that. I think it's pretty pure. So the powders generally that we buy will be compatible with the additive manufacturing machine. Accordingly, the grades will be distributed by the company. So we have purchased M100 EOS 316 stainless steel for particularly selective laser melting. So I believe they are pretty pure.
Okay, yep. How long do you have to ball mill this stuff? So you talked about ball milling. How long do you have to do that?
Yeah, we actually didn't publish this work yet, so I didn't want to put all that data, but I can tell it now. So it's about like 5 hours we milled it at very low speeds.
Okay.
Yeah.
And this is probably beyond the scope of your talk, but is there any clues about how to prevent porosity in situations like this? Because I've had people who come to me with laser melted from powders and electron beam melted from powders, and they always have porosity. Are there any solutions that anybody's come up with for reducing porosity? I'm guessing that you can probably never completely prevent it. But I know, for example, if you're trying to make an airplane part, you don't want the airplane part to be porous and have it fail while you're in mid-flight.
Exactly. Yeah, that's one limitation I was also talking about. And I also agree with the statement that porosity cannot be eliminated completely. There will be definitely some micro porosity present. So the presence of porosity could be from different reasons, like the quality of the powder and also the flowability of the powder, SLM processing parameters, that will be about a dozen of them. So everyone need to optimize all these to eliminate the porosity. So my work precisely says that instead of optimizing all these, just add an additive. And although there is some minor porosity, this additive will take care of it by improving the corrosion, by not deteriorating with the porosity.
One more quick question. You were talking about the NH4 will help reduce corrosion. So do you think so when you're ball and milling this, you're doing it in air, right? Or are you doing it in some special atmosphere?
It was an argon atmosphere.
Okay, so there's no water. So it's not like the NH. I was wondering where the hydrogen's coming from. And how would you measure? I mean, I know that measuring hydrogen on a micro or nano scale is really difficult because hydrogen doesn't make an X-ray. So if you illuminate it with an electron beam, even in a TEM, you can't pick up hydrogen because it just doesn't make an X-ray. So you've got all these little tiny inclusions. How do we find out if those are have any hydrogen in them which would help with the corrosion prevention? If you don't know the answer, you don't know the answer, it's okay. I mean, that could be I don't know, that's a subject for future research kind of an answer.
Yeah, but I'll still tell you like what answer I know. I'm not sure if you're asking if there is hydrogen in the inclusions or in the passive film of NH4 plus.
Yeah, or do you think there's any hydrogen in the inclusions? That's really what I was asking.
I really don't know. Like you said, it is very hard to find out from TEM. If there is, it is there. If there is not, it is not.
Fair enough. Does anyone else have any questions? I don't see anyone, so unless somebody jumps up real quick. So
Actually,
thank you
I
very
have
much.
a quick question.
Okay.
If
Thank
you
you,
have one
Nicole.
more second.
We do.
I am Nicole Hedges. I am not a materials person, but I'm more of a process person. And I was curious, what was the decision for choosing the chrome nitride in the first place as your additive?
Yeah, like I said, literature shows that with increasing the nitrogen percentage, generally the corrosion resistance of stainless steels is improved. So for adding nitrogen into stainless steels is difficult. So we are adding through the additive, and we also choose an additive that will mix during the manufacturing process, instead like segregating or agglomerating in the matrix, like in the microstructure, because that will again cause localized galvanic corrosion. So we wanted additive that can mix into the matrix, like the melting point of chromium nitride would be around 1400 degrees centigrade, and selective laser melting temperature is around 2000 or a little bit higher than that, 2000 degrees centigrade. So when we add chromium nitride, it's gonna disperse into the matrix and distribute our nitrogen well. And also chromium is added because it's one of the elements to improve corrosion resistance too. That's how stainless steels are like high corrosion resistant, high chromium content.
Great, thank you.
Does anyone else have a question? If not, let's give Venkata another big hand. Thank you, that was awesome.
Thank you.
Our next talk is from Priyanka Ramaswamy. She's from North Carolina A&T, and her talk is going to be a study of dopant incorporation in tellurium doped gallium arsenide, arsenic, antimony, I'm having a hard time talking, nanowires using a combination of XPS, UPS, and contact or conductive AFM and scanning Kelvin probe AFM.
Hello everyone, I'm Priyanka Ramaswamy doing PhD in Electrical Engineering at North Carolina A&T State University. Today my presentation is on study of dopant incorporation in tellurium doped gallium arsenide antimonide nanowires using a combination of XPS, UPS, and CAFM SKPN. Grade 5 semiconductor nanowires have significantly attracted researchers due to 1D architecture, quantum confinement effects, and a higher tolerance for strain mismatch that allow greater freedom in bandgap engineering of material systems in a variety of different nanowire architectures to meet the demands of next generation optoelectronic devices. Dopant incorporation in a well-controlled manner is essential to produce abrupt interfaces, to modulate work function, and to realize advanced devices in nanowire configuration successfully. Unfortunately, the thin film studies on dopant incorporation and carrier concentration cannot be directly translated to nanowires due to the dopant's influence on the growth kinetics and different growth mechanisms along with the axial and radial directions. Commonly used measurement techniques in thin films for the determination of carrier concentration, namely Hall effect, field effect transistor measurements, require highly sophisticated lithography steps. The uncertainty of the gate capacitance and contact resistance in the case of nanowire FET can further limit the accuracy of carrier mobility and concentration values. In recent years, several characterization methods have evolved for the assessment of dopants in nanowires. These are secondary ion mass spectrometry, off-axis electron holography, and atom probe tomography, where all these techniques are found to be destructive. In this work, we evaluate the carrier concentration and incorporation of tellurium dopants in gallium arsenide antimonide nanowires grown using gallium-assisted molecular beam epitaxy with variation in gallium telluride cell temperatures from 500 degrees Celsius to 570 degrees Celsius respectively using X-ray photoelectron spectroscopy, ultraviolet photoelectron spectroscopy, conductive atomic force microscopy, and scanning Kelvin probe microscopy, as they do not involve any contact fabrication. The intrinsic and tellurium doped nanowires were grown in an EPI 930 solid source MBE system with world arsenic and antimony as the group 5 constituent cracker sources. A CM image of intrinsic and tellurium doped gallium arsenide antimonide nanowires was shown. Here R represents intrinsic gallium arsenide antimonide nanowires N500, N550, and N570 refers to the tellurium-doped gallium arsenide antimonide nanowires grown at gallium telluride cell temperature of 500 degrees Celsius, 550 degrees Celsius, and 570 degrees Celsius. Generation of photoelectrons in XPS, the kinetic energy of the emitted electrons irradiated with soft X-rays from the sample is analyzed. The result of the complete transfer of the X-ray energy to a core-level electron is the emitted photoelectron. The working of UPS is similar to XPS but irradiated with a UV source. The work function of the material can be evaluated using UPS. XPS UPS measurements were performed with a thermoescalab 250Xi using monochromated aluminum K-alpha X-ray source and helium-1 photon source respectively. In this figure, XPS core level spectra of gallium 3D, arsenic 3D, and antimony 3D are shown. Here, the absence of tellurium 3D peak in the N samples suggests that the concentration of tellurium is less than 10 to the power 19 per centimeter cube. The XPS lower detection limit of tellurium is in the mid 10 to the power 19 per centimeter cube. It is further difficult to detect the dopant concentration in the range of detection limit in a ternary alloy. Hence, XPS surface analysis only provides a qualitative comparison of the dopant level. The shifts of gallium and arsenic associated 3D peaks toward higher binding energies indicate increased free electron density induced shifts of the core elements. These peak shifts reflect corresponding shifts in the Fermi level higher in the band diagram, as the binding energies are measured relative to the Fermi level. Therefore, the N550 sample is found to be heavily doped as compared to the N500 and N570 samples. Here the atomic ratios of gallium over arsenic for tellurium-doped gallium arsenide antimonide samples is found to be around 1, while antimony over arsenic is found to be around 0.07. UPS. Left column indicates the low binding energy slope, whereas the right column indicates the high binding energy slope of the UPS spectra of intrinsic and tellurium-doped gallium arsenide antimonide nanowires. The lowering of the work function manifested by a positive shift in the binding energy of the UPS spectra of tellurium-doped gallium arsenide antimonide nanowires grown at the gallium telluride cell temperature of 550 degrees Celsius revealed the sample to be a heavily N-doped sample with a carrier concentration of 2.8 into 10 to the power 19 per centimeter cube. The electrical characteristics have been investigated using CAFM, a technique in which the electrical current passing through the tip and the sample is recorded. A current map of the surface of the sample at a given bias gives us a single slice of the conductivity of the sample. Titanium iridium conductor tips with a tip radius of 25 nanometer has been used. To illuminate the sample, a laser of the wavelength of 860 nanometer was used. Current mapping under a DC bias of 600 millivolts is done. Top contact is the AFM tip to the top of the sample, and the bottom contact is the gold-coated contact connected to the silicon substrate. In this, the left column depicts the topography of an array of vertically aligned tellurium-doped gallium arsenide antimonide nanowires, while the right column shows the corresponding current mapping of the doped nanowires. It is evident that the N550 sample is more conductive. From IV characterization, an estimated carrier concentration of 7.1 into 10 to the power 17 per centimeter cube, 3 into 10 to the power 19 per centimeter cube, and 3 into 10 to the power 18 per centimeter cube are determined for the tellurium-doped gallium arsenide antimonide nanowires at gallium telluride cell temperature of 500 degrees Celsius, 550 degrees Celsius, and 570 degrees Celsius, respectively, from console multiphysics fitting. Along with console fitting, Padovny straighten fitting has also been carried out, and this has been discussed in detail in our paper that has been published in Scientific Reports Journal. The graph shows that the values obtained from console and UPS concur very well. SKPM scanning of the nanowire samples was carried out using lift mode, which uses 2 separate passes per scan line. The sample topography is measured in the first pass, while the surface potential is measured in the second pass. From the SKPM surface potential images, an increased contact potential difference between the nanowire and gold surface can be observed in the tellurium-doped samples, which reflects decreased work function with gallium telluride cell temperature. Conclusion. The values of carrier density from UPS concur very well with CAFM values. The change in surface potential observed in dope nanowires and SKPM characterization also provided strong evidence of tellurium incorporation. Therefore, a combination of contactless methods, that is, no fabrication of contacts being involved, such as XPS, UPS, CAFM, and SKPM, or other convenient techniques for the assessment of dopants in nanowires that are critical to bandgap engineering design for the application of optoelectronic devices. And these are the references. I would also like to thank CSA's organizing committee for giving me a wonderful opportunity to share my research work. Thank you.
Bianca? I have several questions, and my questions are going to be kind of technical and AFM oriented because I'm an AFM guy. Was the AFM tip coded for conductivity when you were doing the conductive AFM and the SKPM?
Yes.
What was it coded with?
The tip which we already used, it was titanium iridium coated tip. So
you got
which was
one of the Asylum special titanium.
Yes.
Okay, great.
Yes,
Yep.
yes.
I guess it's iridium on top of titanium on top of silicon.
Yes, yes.
The titanium is a gluing layer, just for your information. Did you test the tip afterwards? Because I've had issues with those tips actually losing their conductive coating.
Yes, I did, because if you compare this kind of coated tips with the conductive tips like platinum, for example, here if the coating is being gone, what happens is you can easily see there'll be no current passing through. So for us, I have done several measurements for myself and also for my colleagues, and I have seen the tips definitely wears out, but after I would say 5 or 6 measurements. But when it wears out, you will easily see. And also with AFM image itself, you can find, there'll be kind of, a drag kind of images will be there. So when you see all those dragging kind of image, that shows that tip is wearing out or it has worn out.
Okay, good answer. For the SKPM, one of the questions I always have when people do lift mode is, did you try lift mode with a tip that is not electrically active? Because every time I do lift mode, I try to put in a different tip that's not reactive to whatever it is I'm lifting and looking for, to make sure that I get nothing but noise. Because if I've had it happen where I've lifted and I've gotten signal even with a tip that shouldn't have given me any signal. And that makes me question whether or not the lift data is correct.
Oh, unfortunately, I haven't really tried that. So I have been using this titanium iridium tip for these measurements. Probably after your question, I can give a try.
Yeah, I would try with a regular tip, because it's has been shocking to me when I've done lift and I've found that the lift image looks the same no matter what kind of tip I put in there. That tends to suggest to me that I can't believe the lifted data.
Oh, really? Okay.
That doesn't happen often, but I've seen that happen before. So which is why I've gotten serious about doing that. Good, bad, or indifferent. The rest of your talk was so good. I didn't come up with any other questions because it seemed like you knew exactly what you were talking about.
Thank you.
Is a great compliment. So it looks like Philip might have a question because his video just popped on.
Right. Yeah. Yeah. Me and Chuck both do AFM. So my question is also related to the AFM, specifically on slide 10 on the conductive mode. What's the significance of those? You said N550 was the most conductive, but do you know why that specific sample was? And also, what's the significance of the actual image that you got itself? So, I saw that, you showed where there were spikes of higher current. If you did the same pass, would that look exactly the same? What's the action item from that experiment? What do you do with that?
Okay, so this conductive CAFM, what it gives is, as you say, it gives you the conductivity of the whole nanowires. With 550, I see more current, and I would say because of more doping, that is, it is N doping, so more electrons are present for conductivity. So hence we see more current that is being passing through through this N550 material because of high doping concentration in that nanowire. And this CAFM image, not just that, it can be even used for doing IV, because we cannot be, do IV on all 1,000 pixels that we take image, right? So these points where you see all those lights coming up, like with the current mapping, so these points shows that where currents are passing through. And especially with my nanowires, we have vertically aligned nanowires. So the nanowires are not continuous. It's like a forest of trees that has been like standing vertically closer to each other, but not in contact to each other. So it's not like a thin film. So I need to really find the spot where the nanowires are. So this CAFM image, especially for the nanowires where I can target individual nanowires to do IV measurements.
Interesting. Yeah. And so do you have any issues with, I mean, I imagine, are the wires like pretty like well bonded? Do they stay in stationary? I imagine if you were doing contact AFM, like wires like that might move a little bit. Does that give you any problems?
Yeah, as sort of a corollary to Philip's question, how do they move around when you're trying to image them?
So far, I have never came across that issue, because if you look at my AFM image, the topography, it is having the, a hemisphere kind of image. So which shows that it's not dragging, the nanowires are not dragged by the tip. It is standing still.
Interesting. Thank you.
As a quick follow-up question, how big is the tip relative to the size of the nanowire?
So the tip radius is 25 nanometer radius, and the diameter of the nanowires are like in the range of 100 nanometers. So that is one of the important things we need to follow. So with respect to get high resolution image, we need to select the right tip radius so that we can get good high resolution image. So if you consider my image, I mean my nanowires, they are in the range of 100 nanometer diameter, and the tip radius is 25 nanometer. So you can easily say that each, I'm getting IV only from one particular nanowire, like single nanowire, and the tip is not covering a whole bunch of nanowires out there, because the tip radius is very small compared to the diameter or the radius of the nanowire.
So just as a quick comment for you, I think you can actually do an IV curve at each point in the image with the Asylum microscope, but it would take a lot of time.
Yes. The thing, yeah, that is there. I do that's called force map, if I'm not wrong.
That's correct.
So I did try. The thing is, we would be getting only the laser. Getting the dark is kind of difficult, if I'm not wrong, because I did try that IV map, with each pixels and everything. Mm-hmm.
Nobody said it would be easy.
Oh, it's a time-consuming one as well.
Well, good, better, and different. They don't give away PhDs for doing stuff that's easy.
Yeah, that's true.
Are there any other questions for Priyanka? If not, let's give her another hand.
Thank you.
Our next talk is from Hannah Margavio. She is a student here at North Carolina State in the Department of Chemical and Biomolecular Engineering, and her talk is going to be on low temperature thermodynamically favored area selective deposition.
Hi everyone, my name is Hannah Margavio, and today I'll be talking to you all about area selective atomic layer deposition and how we can achieve that through simultaneous deposition and etching. In 2020, it was found that out of all the energy produced globally, electronic devices actually consumed about 1% of all of that energy. And based on the current trend of doubling energy use every 3 years, it's actually predicted by the year 2040, electronic devices will now consume about 20% of the energy produced globally. So instead of looking for more ways to produce more energy, we really need to be focusing on making energy efficient semiconductor devices. And before going into too much detail, I wanted to cover some background into one of the most widely used techniques in semiconductor processing, and that is atomic layer deposition, or ALD. And ALD is a technique for growing conformal thin films where gaseous precursors are dosed sequentially onto a surface in an AB type fashion. The resulting half reactions are self-limiting, and also produce solid thin films on the surfaces. And one of the most widely studied ALD process is that of aluminum oxide using trimethyl aluminum and water as precursors. So I just wanted to briefly explain how this works before going into area selective deposition. So we have here on a silicon surface, say a hydroxyl termination, and the trimethyl aluminum is dosed and chemisorbs onto that hydroxyl termination, and the hydroxyl groups and the methyl groups react to produce volatile methane. So methane leaves as a byproduct, and so we're left with this new methyl terminated surface. And now we can dose water onto that surface, which then reacts with the methyl groups to produce methane again, until we're left with our original hydroxyl terminated surface. And so when you hear people say ALD is a cyclical process, this is what we're talking about here. So getting back to the original question, how is ALD used to improve the energy efficiency of devices? And to answer that question, let's first consider the example of copper interconnects, which are present in most semiconductor devices. And these transmit signal to and from different device components. And here I'm showing a very well-aligned copper feature on top of copper channels that are below it. But in reality, there is going to be some degree of pattern misalignment. And this is really due to the stochastic nature of photolithographic patterning processes. And one manifestation of pattern misalignment is edge placement error, which I've shown here, which can lead to things like open circuits, excess resistance, and just overall power loss that's going to contribute to energy inefficiency in a device. So photolithography, which is typically used to make these copper interconnects, is a top-down patterning method, of materials. And the way that it works is that a photoresist is first spun onto some sort of surface that we want to pattern, and then a mask is applied. And this mask is going to contain all the details, all the information concerning that pattern. And so the trick here is you have to line up the mask with the features below the surface that you're trying to pattern with respect to. So this photoresist is either cured or etched away, and then another one or several etching processes can be used to remove that exposed metal so that we're left with our final pattern. And like I said here, the information contained, or the information about the pattern, so the way the pattern aligns with the underlying substrate, is dependent on how well you align that mask. And the challenge here is with the continued downward scaling of device components, the margin of error for pattern misalignment is becoming stricter and stricter. So area selective deposition poses an alternative patterning method where the information about the pattern is contained in the surface chemistry and does not rely on a mask. So with ASD, which stands for area selective deposition, we're utilizing differences in surface chemistry, say this AB type surface chemistry, to direct self-aligned bottom-up thin film growth in a desired region. So in this presentation, I'm going to show you all a new mechanism for ASD that achieves selectivity through simultaneous deposition of one material and sacrificial etching of a neighboring material. So the semiconductor industry has been studying tungsten for a long time. And tungsten metal can be grown by atomic layer deposition using silane and tungsten hexafluoride gases as precursors. So in the first half reaction, a tungsten silicide surface is exposed to the tungsten hexafluoride, which chemisorbs onto that hydrogen terminated surface. And then the tungsten fluorohydride surface that's left behind is further reduced by the next silane dose. So the silane is continually taking away the fluorines from the surface due to this formation of the very, very strong silicon-fluorine bond. And so it's going to leave tungsten metal behind. And a few things to note about this ALD process is that tungsten actually grows linearly after its nucleation period at a rate of about 0.65 nanometers per cycle with a temperature window of 200 to 300 degrees Celsius. And I think it's worth noting here that tungsten nucleates preferentially on a hydrogen terminated surface as opposed to something like a hydroxyl terminated surface or condensed silica surfaces. So contrary to atomic layer deposition, we can also remove material at the nanoscale by chemical vapor etching. And so I want to go ahead and point out here that there's a difference between atomic layer etching, which is cyclical, self-limiting removal process, and chemical vapor etching, whose rates are highly variable with temperature. So tungsten hexafluoride, which is used as a deposition precursor for tungsten, can actually also be used as an etchant to etch away titanium dioxide. So for this case of etching, the tungsten hexafluoride is first going to form a tungsten oxide layer at the surface of the titanium dioxide. And this tungsten oxide layer is going to be subsequently fluorinated as the tungsten hexafluoride is dosed to form a tungsten oxyfluoride, which is volatile, and it can leave the surface as an etch product. So one benefit of using a CDE process over an ALE process is that we can tune the etching kinetics of titanium dioxide pretty easily by just changing the processing conditions like reactant exposure or even temperature. So as it turns out, we can actually combine these two processes of tungsten deposition and TiO2 etching because, number one, they both use tungsten hexafluoride as a precursor, and their processing temperature windows overlap with each other, and both reactions are calculated to be thermodynamically favorable within the same temperature range. So really for temperatures above about 75 degrees Celsius. And so this bottom plot on the right here is illustrating the simultaneous mass gain associated with tungsten growing on aluminum oxide and mass loss on a TiO2 surface using the exact same reaction conditions at the same temperature. And I just wanted to note here that this data was collected via in situ quartz crystal microbalance studies. So when we combine these two reactions, we can actually achieve up to 10 nanometers of selective tungsten growth on hydrogen terminated silicon by simultaneously etching titanium dioxide, which is patterned on an adjacent SiO2 region. And I wanted to go ahead and point out that all of these STEM images and EDS maps were captured on the Titan STEM, which is owned by AIF, of course, and the FIB liftouts were prepared by the QuantaFib, also at AIF. So at this point, we thought that it might be possible to generalize this mechanism for achieving selective deposition by combining deposition and etching processes that share one or several precursors, and that can be performed under the same processing conditions. And so obviously this is going to necessitate that the two processes have overlapping temperature windows of energetic favorability. So what's going to happen here is, first we're going to start out with our pattern sacrificial material. And then as we dose our precursors, the desired material begins to grow in the regions where the sacrificial material isn't present. And selectivity is maintained beyond the window of tungsten's inherent preferability towards nucleating on the hydrogen terminated silicon, because the sacrificial material is consuming the deposition precursors in a way that is avoiding tungsten nucleation on top of the sacrificial material. And we think that this process can be extended to several different chemistries. And so part of my future work is to identify different material sets that can work with this mechanism and to really explore how the balance of the deposition and etching kinetics is going to lead to better or worse selectivity. So to summarize everything up here, our main goal with this project is to address device feature edge placement error and the electrical inefficiencies associated with that using a new mechanism for bottom-up area selective deposition that uses simultaneous deposition and sacrificial etching to achieve selectivity. And again, these two reactions can be combined. If the deposition and etching reactions share a common precursor, we can demonstrate them in the same temperature range and are calculated to be energetically favorable or just experimentally demonstrated. And we believe that this mechanism can be extended to other material systems to hopefully open up the toolbox for the number and types of materials that can be patterned in a bottom-up self-aligned way. So before I close, I just want to give my thanks and gratitude to the Parsons Group, along with the Semiconductor Research Corporation, SRC, for funding this project, and our industry liaisons at IBM, Intel, Tokyo Electron, and TSMC. Thank you all very much for attending my talk today, and I would be happy to take any questions.
Okay, let's give Hannah a big hand. Hannah has joined us from the Varios Lab. So Hannah, I've got a couple of quick questions. All right, first question I have is, all right, and I admit that I'm a babe in the woods when it comes to this sort of thing. I really don't know. How long does it take to clear out the gas that you were using to deposit or etch before you can start the next process, and how do you know?
Yeah, so that's actually a really great question and something that I've looked into pretty extensively. So it takes about 60 seconds for the operating pressure to reestablish in the chamber. So when you dose your precursors, the way we can tell that it's fully evacuated from the chamber, or at least mostly evacuated from the chamber, is when you dose the precursor, you see a pretty large or pretty small pressure spike that's measured using either a barytron pressure gauge or a convectron pressure gauge. And so we sort of, when we're drafting up these recipes, we look at the pressure reading as we dose, and then when we shut off that valve that's dosing the precursor, you'll see the pressure start to drop off and then sort of stabilize. And so for silane and tungsten hexafluoride, that takes about 60 seconds, but other precursors can take as little as 30 seconds, some can take 45. So that's how we, that's how we determine that.
Have you ever thought about putting a residual gas analyzer on there to find out if it's all gone?
Yeah, so another reactor in our lab has a residual gas analyzer on it. But that's mostly used for detecting product species from half reactions, but we have not attached an RGA for the purposes of evacuating the chamber.
Okay, one more quick question. Actually, first I've got a comment. Feynman would approve of your bottom-up approach.
Yes, thank you.
So if I understand this right, you have the sacrificial layer of TiO2 on there, and you etch that, and then you deposit tungsten. So you do an etch and then deposit, etch and then deposit. Once the deposition is complete, let's say that you've got as much tungsten deposited in your trench as you want, but you still have TiO2 on top of your little lines. Can you continue the process to just the etch process without the deposition process, to just continue removing that TiO2 to get rid of all of it if it's not something that you want to have there? I mean, is this an iterative process that you can just keep iterating until you get to where you want?
So in a short answer, yes, it's an iterative process. And I wanted to go ahead and point out that it's not necessarily etching, then deposition, then etching, then deposition. This is all happening at the same time because that tungsten hexafluoride is simultaneously acting as a deposition precursor and as an etchant. To answer your question of, all right, we have all the tungsten that we need, but we still have some TiO2 left. There are a couple things that we can do to get rid of that remaining TiO2. One kind of utilizes the chemical vapor etching nature of the TiO2 etching reaction, which again is highly dependent on temperature. So we can actually speed up the rate of etching by increasing the chamber temperature. So that's one option. Another option is to just keep the same processing temperature, but instead of dosing tungsten hexafluoride and silane, just dosing the tungsten hexafluoride to try to etch away that precursor without depositing any more tungsten. In this case, we might still get a little bit more deposition if the silicon diffuses up from the substrate through the tungsten, and then the tungsten hexafluoride can be reduced by the silicon and the substrate. So to answer your question, I would start by raising the temperature of the chamber.
Okay, looks like Nicole might have a question.
Yes, I was curious. I can understand the idea of wanting self-aligning for removing some of your misalignment, but it seems like it is dependent on how well your sacrificial layer is aligned. How are you getting that sacrificial layer, and how is that not causing the same edge misalignment that you're trying to avoid in your deposition?
Yeah, so that's a great question. I guess there are a couple points to make here. Number one, the focus of my project is not necessarily how do we get the best sacrificial material, but I will go ahead and say that the TiO2, for instance, we selectively deposited that using a different ASD mechanism or a different selective deposition mechanism, but also tools like nanolithography, ion milling, that's pretty sufficient for our purposes because the sacrificial materials we're working with aren't something crazy like niobium or something. It's stuff like TiO2, alumina, silica, hydrogen terminated silicon. So materials that have been studied for long enough to where their patterning methods are pretty reliable. That's pretty much what we're studying. That's a great question though.
Does anybody else have a great question? Because that's all we want. Chris always has great questions.
No, they're not great questions. So Hannah, first, obviously, awesome talk, a really fascinating combination of chemistry, thermodynamics, material science going on. So I have a couple at least one ignorant question. This kind of self-alignment, this optimization of the mask, the first important step of lithography, is this compatible, this kind of ALD deposition chamber compatible with like reactive ion etching chambers as well? Can it be combined into the semiconductor manufacturing process without too much difficulty?
Oh yeah, absolutely. One of the systems in our lab is actually equipped with remote radio frequency plasma. So there are definitely cases where people have done selective deposition, for instance, selectively depositing nitrides using this exact mechanism could, in theory, be done by igniting ammonia or using nitrogen plasma. Probably would want to use nitrogen plasma so you could lower the temperature. But yeah, people have definitely done that.
Cool. My next question, you hinted at other material systems you guys are looking at. Are you able to talk about that, or is that still being published? Or
so I can go ahead and give one example. We believe that it's possible to selectively deposit aluminum fluoride by simultaneously etching zinc oxide using trimethyl aluminum and HF pyridine as precursors. And so that process, I think, is going to be a little bit tricky just because the zinc oxide, I imagine, will want to convert to aluminum oxide upon introducing that trimethyl aluminum onto it. So you would lose selectivity pretty fast. So that's one example of that. I guess another example would be we could possibly extend this chemistry, this fluorosilane elimination chemistry, we could possibly extend it to molybdenum as well. And instead of using tungsten hexafluoride, we could use something like molybdenum pentafluoride or maybe some subfluorides, since it's a pretty rare earth material.
you guys keep the H&S up all night, don't you?
Oh yeah, you bet. Frank and I are very close.
Hannah, awesome work. Thank you.
Thank you so much.
All right. Does anybody else have a question? I'm amused by keeping EH&S up all night.
Me too.
I take the opposite approach. I try to have absolutely nothing dangerous in any of my labs. Does anybody else have a question? If not, let's give Hannah one more big hand.
Thank you.
And then we're going to have our last vendor presentation by Pfeiffer, and there's 2 videos there. But before that starts, I want to remind everyone that there is going to be an award presentation after the vendor videos. We're going to try and get all the awards together, be ready to present that immediately after the last 2 vendor presentations. We're giving away a lot of money, so stick around. And now we'll start our Pfeiffer vendor presentation.
Chuck, don't forget about the survey too.
Oh yeah, everybody don't forget to fill out a survey because there's a drawing for that. We're going to do a raffle. And so make sure you filled out a survey. If you haven't, go ahead and do that now.
All right, this next video does not come with all the movie level technology. So basically, I'm Fred Stevie, I'm going to narrate for you. This is a particular turbo pump. And if you see what they're showing right here, they found a way to make it smaller. It's called the Hi-Pace 80 Neo, more compact, less weight. And they're showing that it's smaller than their competition in terms of size, therefore easier to mount. And there's some other capabilities with it. The lubrication, the bearings have been improved, rotor temperature measurement, and performance range. So there's another technology they've added to this. Normally, if you take a turbo pump apart, you'll see little holes that have been drilled, and that's to balance the turbo pump. This particular one is using a laser to trim very precisely so that the rotation and the balance can be as precisely balanced as possible. The ones on our XPS run at 1500 Hertz, that's 90,000 RPM. So if you can improve that balance by making that more precise, then you're going to be better off. So that is the Hi-Pace 80 Neo. And there'll be one more video coming up.
My name is Brandon Frazier, and my company is All Scientific. We support the Mid-Atlantic, the Carolinas, and the Southeast from a sales perspective, but our service reach goes a little bit beyond that to almost the whole East Coast. Our products run the gamut, from the $10 vacuum clamp to the multi-million-dollar atomic layer deposition system. And at All Scientific, we bring a lot of technical experience to bear in backing up those products and helping customers with a solution. We're not your typical manufacturer rep. We like to get involved in the applications and bringing solutions to customers, installation if needed, and post-sale support. All Scientific is really strong in product and technical expertise for thin film coatings. We work with a lot of OEMs who build coating systems. We work with end users who produce coatings in the lab. We have a range of components that can be used in optical coatings. PicoSun's relatively new to our product lineup. They make atomic layer deposition systems. If you need a coating that's pinhole free and conformal, that's really a good solution to look at. We began representing VAT in 2017, and they're the #1 name in vacuum valves worldwide. Ibarra is one of our longest running product lines. We represent their components division, which is primarily dry vacuum pumps, turbomolecular pumps, and point of use abatement systems. With Edwards, we're involved with our CTI and Polycold divisions. This is cryopumps, cryochillers, and cryocoolers. Ancorp is a Florida-based manufacturer. They do vacuum components, high vacuum and UHV chambers, and they have excellent ball valves. I'd been reading Harold Kaufman's literature and books for years, so it was really awesome when they asked us to represent them. That was a huge moment for All Scientific and for me personally. All Scientific is the exclusive US distributor for Intellimetrics, so we sell and service this product nationwide. On behalf of everyone at All Scientific, I'd like to thank those that organized the meeting and for allowing us to participate as a sponsor.
Okay, I have got some awards. I'm going to go ahead, unless there's an objection from anybody that's on the committee, I'm going to go ahead and start giving them out. Giving out a lot of awards. When your award is announced, if you are okay with it, turn on your video, because we'd like to highlight you, but we don't want to embarrass anybody. The AIF Best Paper Awards, these are 2 awards for the best paper published during the year that acknowledges the use of the analytical instrumentation facility. And this is sponsored by the AIF, and they're $200 a piece. And they go to Alex Sain and Srivatsan Ramesh. So congratulations to Alex and Srivatsan. You're $200 richer. You go.
Thank you.
You are welcome. Thank you for being so smart and publishing good papers. We really appreciate that. The next awards are for the student oral session prizes, and these are the oral presentations. There are 4 sessions total. We're giving an award for the best oral presentation from each of the sessions. The winner from session 1 is Younghwan Lee. These are $100 awards each. So Younghwan, if you're here and you can, there we go, there's Younghwan, although he doesn't seem to be highlighted right now. Robin Pocarel won for the 2nd session. Congratulations, Younghwan. It was an awesome talk.
Thank you very much.
Robin Pocarel is the winner from the 2nd session. If Robin is here, there he is.
Thank you so much. I'm so excited and happy.
Hua Yu Tong is our winner from the 3rd session. Very good. And I got to say, I didn't see any bad papers. They were all good. And Hannah Margavio won from the 4th session. The best overall oral prize, and this is for the best oral presentation across both days, and this is sponsored by the AVS Mid-Atlantic, and it's a $500 award, and that one goes to Younghwan Lee. So let's put Younghwan back up on the screen because he should be a very excited individual because he's already won $600. 2nd place oral, which is a $300 award, goes to Hannah Margavio. So Hannah, you should be really happy. The 3rd place oral, there are 2 awards. One goes to Muhammad Shamshi or Malad, and the other one goes to Yao Li. Congratulations, Malad. Congratulations, Yao.
Thank
if you're
you.
Here. I have to admit that I haven't been keeping up with the attendance. Our student poster awards. First prize goes to Kristen Popowski, and this is sponsored by our vendors, and it's a $300 award. So first prize for the student poster goes to Kristen Popowski. 2nd place prizes, there's $100 each. There were 4 awards. We only actually had 4 posters this year, and I have to admit that it's really hard to imagine how to do a poster for a virtual presentation, a virtual conference. It's much easier to do a talk. The Saeed, Kendall Dawkins, and Anitha Jaya Palan all won 2nd place prizes, and those are also $100 a piece, and they are sponsored by the vendors. The NNF Best Student Presentation Oral or Poster, and this is the best student presentation that used NNF facilities and acknowledged them, and it's sponsored by the NNF. And that was also won by Younghwan Lee. Younghwan should be extra happy now because there's another $200. He's got a big grin on his face. The ASM Hans Stottlemyre Award, which is the best presentation that shows X-ray diffraction techniques, is also won by our friend Younghwan. Younghwan is the big winner today. We have 2 more raffle winners, and I have not gotten those yet. So Roberto's supposed to send those to me, and he may have sent them to me in chat. Yep. Raffle winners are Hannah Margavio and Hirandeep Reddy. So Hannah and Younghwan were the 2 big winners today. I want to thank all of the students who presented and showed us your work and are here doing quality work. We're really, we wouldn't be here if it weren't for the students. We're really happy to be able to put on this conference every year and have a nice little local conference where everybody gets to show what they're doing. I think it's good for cross-pollination so that you can see what your colleagues are doing, and something that one of them says or presents might strike something in your brain that makes you go, whoa, I can apply that to my work. So I think that's a really good thing. I have discussed this with Fred just a little bit. We're going to try really hard to do this for real next year in person because the virtual conference does leave a lot to be desired. And part of the fun of going to a symposium is being able to network and talk with people at lunch and talk with people at the poster session. And you just don't get that in a virtual situation. But this is better than nothing. So I want to, to finish up, thank everybody for coming to the symposium this year. We are planning on having another one same time next year. We hope that everyone who presented this year, if you have not graduated, you should look at submitting and presenting again. And don't forget to acknowledge the AIF, because there were a couple of best paper awards that I had to throw out because they didn't acknowledge us. So please remember to do that. And everybody, thank you for coming. And we're going to conclude our conference at this time, and we will see you all next year.